Well, thank you, Calvin. I appreciate that introduction. And I'd like to extend very warm welcome to all of you on behalf of the University of Illinois, Urbana-Champaign. Whether you drove down Neal Street to be here today, or you came across the globe, or you're out there and somewhere in the world watching this be live streamed, thank you for joining us today. We're so pleased. I'm a biochemist, but I understand there's some very significant luminaries in this room and out there around the globe who are watching today. And we know how precious your time is, and it's a testimony to how important this day is in the discussions. I'd also like to thank Calvin Drogemeyer for his vision to organize this summit, and to the NSF for their strong support and partnership. Now, I know I'm biased, but I can't think of a better place to develop a plan to advance understanding of something as very important to every person on the planet as the Earth system. The University of Illinois was founded to serve the state, the nation, and the world. And we have such a strong history of work in high-performance computing and related systems like ILIAC 4 and Plato. We're also home to remarkable expertise in the Department of Climate, Meteorology, and Atmospheric Sciences that works across the scale from global climate to severe local storms. We're the university that brought you pictures on the internet, hacked photosynthesis, unlocked the secrets of superconductivity, and helped to keep dozens of communities safe from COVID. We know how to conduct research that changes lives in positive ways. And as Vice Chancellor for Research and Innovation, I've had the privilege of helping our faculty, our research staff, our students unleash their creativity, whether that's to explore the vastness of the universe or better understand the behavior of subatomic particles. Here at Illinois, we strongly support bold thinking and collaborative research. As Kelvin said, it's in our DNA. Kelvin and I are both alumni of this place, and I think we didn't even realize how it imprinted us back then, and it's just really been a part of the way we've grown. Now, I know that a lot of people talk about interdisciplinary research, but not just any institution can point to being the birthplace of large-scale interdisciplinary research, and we can. The legendary Beckman Institute on the north side of campus, which was founded in the 80s by Arnold Beckman, a true pioneer in work that crosses disciplinary boundaries to address large-scale challenges, is just one example. It's the first example where he had the idea to put engineers, biologists, and psychologists in the same space and watch new frontiers emerge as they collide. In fact, we're gathered here with another interdisciplinary institute. You heard from Bill Gropp last night, who oversees the National Center for Supercomputing Applications, or NCSA, which has been supporting large-scale collaborative research for almost 40 years. So projects at scale, no problem in Champaign-Urbana. At Illinois, we're not just leading flagship NSF projects like 3 AI institutes or a science and technology center. We're also leading projects that support the nation's research community, like the recently announced iBiofoundry or NCSA's Access project. You know, as a scientist, I'm intensely interested in the health of the planet, but also I'm very excited about the topic of the summit because of my family business. I grew up in the Pacific Northwest. My family helped pioneer the salmon industry. I worked in Alaska in the Puget Sound on my dad's fishing boats, and I know firsthand how important accurate projections and simulations can be for weather forecasting and understanding the environmental implications of a changing climate. And I know with our friends, our colleagues down in the southeast, what a terrible, devastating storm. And I think as you gather here today from around the globe, we think about these just disaster zones and how we can make a difference. So with that in mind, I especially like how the idea of running fine scale resolution Earth system models is more than a scientific endeavor. It puts the needs and the challenges of the stakeholders who rely on model information at the very front of the process as really drivers of the agenda. So I want to thank you again for joining us today. I hope you have a great summer. I know it's going to be very productive. And now I have the pleasure of introducing my boss, Dr. Robert Jones, who became the 10th Chancellor of the University of Illinois, Urbana-Champaign on September 26, 2016. He serves as essentially the CEO of this flagship land-grant university. He's also a scholar in crop sciences, plant physiology in the College of Agricultural, Consumer, and Environmental Sciences. He's the first African-American scholar appointed as Urbana's chancellor in the institution's history. He's one of the longest running chancellors or presidents in the nation. And he is the longest running in the Big Ten, where he serves as the de facto chair of the chancellors and presidents. He's currently the chair of the board of directors for the Association of American Universities, which comprises the 70 universities that we consider the leading research institutions across America. And he's also served as the past president of the American Public and Land-Grant Universities, APLU. So please join me in welcoming Chancellor Jones to the podium.
Oh, no need to do that. You just scare people away, so you can leave it down. Okay. Let me start by saying good morning to each and every one of you. It is certainly a great honor and a pleasure for me to be here with you this morning and to welcome you that are from other parts of the U.S. If this is your first time to Urbana-Champaign, we're so pleased to have you here in this bit of paradise between the soybean fields and the corn fields. We think it's the most appropriate place in the world to be if you're going to be doing innovative research, multidisciplinary research, thinking about climate change and how we need to think beyond just demonstrating and documenting the problem to building resilience through greater predictability. In a nutshell, folks, that's why we're here. And that's why I am so pleased to be with you this morning. I have to deviate here and just highlight two individuals that have really been involved with one only a short period of time, but both of these folks are what I call icons in why we're gathered here today. And of course, Kelvin Drogemeyer, that I had the great pleasure of meeting first of all, when he was in the White House Office of Science and Technology Policy, and I would be remiss if I didn't say unequivocally, he was the one individual that was appointed during that time period that I had the great pleasure of being with at APLU and seeing the enthusiastic welcome that colleagues across all of higher education, all of the land-grant universities applauded his appointment to lead that critically important unit. And we kept in contact. We had Kelvin on campus here for a while and just was profound and providing an opportunity for his alma mater to understand firsthand what his agenda was going to be at OSTP. And we were very, very proud and still are very, very proud of you, Kelvin. So much so that rolled the clock forward a few years, we hired him. What else was there to do? And I can tell you, I've been around higher education for 47 years. And I'm getting a little long in the tooth, but I don't think Kelvin is as old as I am. I never seen a faculty member more excited to be back on a university campus than this guy was and still is. I mean, he just exudes this enthusiasm about the work that we're partnering to do. And Kelvin, I just want to personally thank you because this is a first big step in doing something that he and I and Susan and others fundamentally believe in, that land-grant universities have to step up and play a major role in finding solutions to one of the biggest challenges this world faced. And we've got to go beyond just documenting his impact. You only have to look at what transpired with Helena in the last few days. And if you're a climate denier after all of that, when the news start to use words like biblical crisis of biblical proportion, you know that that is something that's really devastating. And so, Kevin, I just want to say publicly in front of our colleagues in the room and those that are listening around the world, Thank you for your leadership. Thank you for your innovation. We couldn't have not be more proud to be with you. And we look forward to what we, the collective we, will build together. And I'm going to emphasize that we piece, that collective piece before I take my seat. And the other guy that I've been looking forward to seeing, I haven't seen him since I left SUNY Albany in 2016. So I had the great pleasure of hiring him, stealing him away from Howard. He did bring the partnership with Howard University with him. That is Dr. Everett Joseph, who's that in-card now, if I got that right. And Everett, I haven't seen you since I left. Does my heart good to see how you've prospered and moved on in the world. And so I don't feel too bad about stealing you from Howard now. So proud to have you with us today. Now, I got to get back to my notes since I got two versions of this. I'm not sure which one let's go with the short, the Reader's Digest one, okay? So again, as I said, we're here to address what I think all of us would agree is one of the most compelling international challenges of our time. And it does require international collaboration, bold thinking, and transformative approaches to find a solution. And that is what I am here to remind you of, folks. This is not business as usual. This has to be business as unusual. And business as unusual, when you're trying to solve some of the global challenges in our society, you got to think beyond the ordinary, how you typically are doing things. In fact, we have a framework here that we call BOLD. Boldly Illinois is the words that we use for our strategic plan. But I can tell you some of the opportunities and some of the challenges we faced have created a situation where we're adding a modifier to bold. We have to think beyond bold, folks, if we are going to be successful. So I look at this effort as being beyond bold, beyond the ordinary. And it's going to require that kind of collaboration to be successful. And another framework, way of thinking about this is we have, as Susan said, absolutely in our DNA is a multidisciplinary approach. But I can tell you from where we sit, and this university has demonstrated this time and time again here in the state of Illinois, where we are doing what my friend down, president of Vanderbilt, calls radical collaborations. Because what we're facing, folks, is too big for any one university, any one agency, any one nation to solve alone. So we have to have this radical collaboration that cuts across all the sectors where each entity brings something to the table. Because one of the things I know about collaborations, particularly if they're going to be radical, where you are partnering with folks in ways that you haven't done before, it's got to be based on two big issues. The first one is mutual trust. There has to be a certain level of trust. Otherwise, you just don't get off the ground. And the other one is mutual benefit. And you can't tell me resolving the issue of climate change and predictability and resilience is something that everyone will benefit from. And so I could go on and on about this, but I just want to emphasize a couple of more points. As Susan indicated, this issue of climate change and its impact on our society is not something that's foreign to me. I spent 34 and a half years of my career at the University of Minnesota. I was hired to be part of a multidisciplinary team. Minnesota was one of the forerunners in bringing these multidisciplinary teams as a part of hiring strategy. And I was hired as the crop or the corn physiologist, as a part of a team of corn geneticists, molecular biologists, corn production people, and a corn breeder. I was the physiologist. It was my role, and the project that I set up, that I led for 34 and a half years, was to try to elucidate the impact of heat stress. Global climate change wasn't even a word that had been coined back in caveman days when I started my research project. But essentially, it was the same thing. I focus on that primarily because what I heard from the growers, the corn growers in particular, it's been really hot here in August, or because the season for growing corn differs in Minnesota than other parts of the Corn Belt. What impact is this going to have on my yield? Because a number of them knew from experience that high temperature during that 14-day formative period where the kernels are pollinated, if you have any kind of stress during that period, guess what, folks? Your yield could be reduced 40, 50, 60%. So I dedicated 34 and a half years of my life trying to understand the underlying physiological, molecular biological, hormonal mechanism that causes one of the principal field crops in this part of the world to be disrupted by high temperature. And now we can call it global climate change. And I'm very, very happy with the fact that we were able to understand the underlying mechanism. And now a lot of the crops, the major agricultural crops have, through gene editing, are much more tolerant to high temperature. And ironically, what causes high temperature impact is also the same mechanism that drought stress. It precipitates the same cascade of physiological responses. I said all that not to brag, but I am one leader of a university who understands firsthand how important this is. This is absolutely critical, folks. And I can't think of a better group of folks to take the leadership on coming together to build out this new approach and to do what's necessary to help us move ahead. So it would be certainly amazing if we could run the climate models at the resolution of weather models and being able to predict the kind of events we just saw unfold in a timely fashion to order to mitigate the damage. I can tell you insurance, assurance, the agriculture sector, infrastructure, transportation, all of those entities are waiting for you, for us, to find a solution to this global problem. And I could not be more proud of the Department of Atmospheric Science and NCSA, who have come together today to host this event, which is sponsored by NSF. So on behalf of all 59,238 students at this university, we have the largest enrollment in 150-year history, and all 9,008 first-year students, and our amazing 2,000 plus faculty members. Welcome to Illinois. We're so proud to have you with us today. Thank you very much.
Wow. Wow, wow, wow. Chancellor, thank you so much for those wonderful, wonderful remarks. See if I can get this back. It's just remarkable when you have a leader at a university that can just talk about this sort of thing and not have to think about talking points. This is inside of the leadership of this institution, not just the chancellor, but Susan as well, and our faculty and other folks around here. I mean, this is really just deep within us. So I'm really, really grateful, and I think you see the extraordinary leadership we have here and the support that we've received. So let me just add my welcome and good morning to you. It's wonderful to have you on the campus. It's a privilege for me and an honor to welcome you to the University of Illinois. How many of you have not been here before, that this is your first time on campus? Wow, fantastic. Well, a special welcome to all of you. I hope you have a chance to tour campus. It's a beautiful time of year to do that. It's a gorgeous campus. We are in kind of the southern part of the campus with the research park just to our west and a lot of things to the north. The big flying saucer thing that you probably saw used to be called the Assembly Hall. It's now the State Farm Center. I really hope you do have a chance to explore campus and enjoy the time that you have here. I also want to give a big shout out to those of you online who were able to join us virtually but not join us in person. Really are excited to have you here to be full participants in the effort. Of course, my name is Kelvin Drogmeyer. I have the privilege of being a professor in the Department of Climate, Meteorology, and Atmospheric Sciences here at the University of Illinois, Urbana-Champaign. Privileged to be back at my graduate alma mater, which I have deep love for after 38 years at the University of Oklahoma. And I have to confess, I feel a bit like President Kennedy did back in the day, many decades ago, when he hosted a group of Nobel laureates at the White House. And so first time that had been done, and he said this, and I quote, and I feel exactly that same way right now. He said, I think this is the most extraordinary collection of talent, of human knowledge that has ever been gathered at the White House, with the possible exception of when Thomas Jefferson dined here alone. And I feel that same way with all of you. You're an extraordinary group of thought leaders from around the world. You've taken time out of your day, time out of your very busy lives to come here and be with us. It's also a really exciting time in the history of science more broadly. We've seen amazing developments in the last several decades, right? The internet being developed, exascale computers, CRISPR and 5G, and AI and GPU computers, and drones, and our understanding of the planet and beyond. We've gathered here today to really talk about a very special and important topic. And we have a goal here. And the goal, of course, as the Chancellor and Susan both said, is trying to estimate the future of climate more effectively and with greater detail than ever before in history, and in ways, and this is really important, more useful than ever before to those who depend upon estimates of climate change. And I really want to underscore that latter point, that being responsive to practitioners and end users and folks who really rely on this information is really critical, and they have to drive this agenda. They can't be at the end of the line where they receive something we've thrown over the transom and be like, gosh, it'd be really great if you would have talked to us a few years ago, because this isn't really what we need. And so folks like Jupiter Intelligence with Josh Hacker and other folks that are here today to help us really deeply understand what the needs of practitioners are, to make sure that this isn't just a great science experiment, though science is critically important, but it's got to be responsive to the needs of those who actually make decisions on the front lines. And as you know, estimating climate change is a monumental task. And it's really, as the Chancellor said, one of the most important things facing society today. And I think a lot of things have come together over the last several years that really make now the right time to gather this group together and to really look at achieving this goal. So my hope is that when we walk out of here Wednesday, we have a clear sense of how we as a global community can move forward with achieving that goal. Now, I'm going to elaborate on that in my opening presentation, but I want to just right now talk about how this summit has been planned for about a year. And I really want to acknowledge, first of all, the National Science Foundation for funding it. Wrote a proposal last November. It was funded in April, but we started planning this activity, assuming it and keeping our fingers crossed that it would actually be funded. We couldn't wait until we got the word, so we went full steam ahead to try to put it all together. And the support we've received from the University of Illinois here has been absolutely phenomenal. As you heard from Tim Killeen last night, who's a former director of NCAR, and just a moment ago from the Chancellor and the Vice Chancellor for Research, this is an appropriate place to do this kind of convening, right? You know, as a land-grant institution, as a university, the only dog we have in the race here is to see things move forward and be advanced. You know, that is our agenda: education, research, building capabilities and value proposition for society. So it's really an appropriate place. And I'll tell you, NCSA, as one of the 10 institutes here at the university that are major institutes, played an absolutely extraordinary role in putting this thing together. We had planning spreadsheets that went into the hundreds of items, and our planning committee the same way. I mean, we met twice a week. We checked off items. Okay, what about this? What about this? The details were just amazing. And I want to acknowledge those folks here who've worked so incredibly hard to make this happen. I don't know if all of them are here today, but I'm going to go through and list them. Charlotte Payne, are you here, Charlotte? Jason Myrick, who's out at the table out front helping with the registration. KJ Nam, who was here last night. Rachel Park. Sean Quigley, who is managing my NSF award to make sure that we do things in the right way and we're compliant with all the federal laws and regulations. And also Michael Miller. Michael, are you here? I saw you earlier. He's here somewhere. He's outside. And I want to give a real special shout out to my good friend and colleague, Deanne Bates. If you would stand, Deanne, I think, yeah. You've all met and worked with Deanne now, I think, and she joined me just in May, and she is an absolute force of nature. She came here from within the university, and I mean, she grabbed hold of things here and made them happen, working through technical details and all kinds of challenges, and she just made it happen. So Deanne, personally, thank you so much for the great work that you've done. It's a joy to work with you, a privilege to have you as part of the team, and I'm really grateful to you. Also, Obi Essian back there at the table in the back. He is with the iHotel here and Conference Center. We're blessed here at the university with this incredible facility, and he is all things technical. Is running the switching boards, the video, and so Obi, thank you so much for all your good work as well. So I want to introduce the team now, who really was the foundation of putting this whole thing together. They're an extraordinarily talented group of people from across the spectrum of capabilities and activities and topics that you're going to see talked about here. They structured the agenda, they structured the whole program, but they also ran these so-called pre-summit intensives, which we started having earlier this year to gather some of the key thought leaders from around the world to do deep dives into some of the key topics so we could get a really good understanding of what some of the challenges are, what some of the pain points, the requirements. So when we came to the summit, we had sort of pre-organized a lot of the thinking, and so we could maximize the value of your time coming here in person today. We didn't have to start with zillions of presentations to where we all come up to speed, and hopefully you've had a chance to look at the pre-summit intensive summaries that are actually on the website. So these folks have been extraordinarily valuable, and they've helped shape the whole of the project here. So I'm going to introduce them and ask them to stand individually, and we'll acknowledge them when I finish here. My good friend and colleague from the Climas Department, Francina Dominguez, over here to my right. Barb Helen, who is formerly, and Francina is a professor in the department. Stay standing, Francina, if you would. Barb Helen, who's formerly with the Department of Energy. A lot of you know Barb. She is a mover and a shaker and such a joy to work with. Barb, thank you. She's standing over there. Ruby Leung, Pacific Northwest National Laboratory. Talk about a mover and a shaker, a member of the National Academy of Sciences. She is a pioneer, is coming here and spending her time with us. She's part of the planning committee. Maria Molina from the University of Maryland. Met Maria at the UCAR members meeting Everett last October. I was so taken by her intelligence and her spirit and her vision. I said, would you please be a part of this? And she graciously agreed, and really great to have you here. Andy Prine, who is formerly of NCAR, he's now with ETH Zurich. Andy is over here, has been a major force in the program. Dan Reed, I think, who a lot of you know, currently from the University of Utah, back in the day, University of Iowa, back in the day, Microsoft, major leader, Microsoft, back in the day, University of North Carolina, back in the day, here at NCSA, running NCSA. Dan is incredibly old, but boy, is he ever wonderful. So, Dan, it's great to have you here. Former chair of the National Science Board. Dan is an extraordinary talent. Bjorn Stevens, the Max Planck Institute for Meteorology, who is here with us virtually. John Schauf, Lawrence Berkeley National Laboratory. John is here, major force. He led something called the Green Flash Project a long time ago. He really liked action figures, and so I think that what stimulated him to do that, but it was kind of a forerunner of what we're talking about. And finally, our good friend John Towns, who was here last night. John is in the room. So there he is, John Towns. If you would please join me in thanking these folks for all the hard work they've done over the last year. Thank you all very much. And you'll find them listed in a table at the back of the agenda, and also in the handout you have that has a bios of all of those folks. The second group of individuals I want to introduce, I'm going to introduce them en masse because there's over 20 of them, the folks we call the nucleus team. And these are the folks who are really major thought leaders coming here to really help run the breakout sessions, the sessions that we have on these so-called challenge sets, and who are going to be kind of the foundational thinkers and movers and discussants at the summit. But in no way does that exclude everyone else. Okay, so they're kind of the foundational team, and they're the ones that the National Science Foundation grant paid to come here. And so their expertise is broad across the spectrum, and they are the ones who are also listed at the back of the agenda. So I would like to invite the nucleus team members to please stand. We've got about 4 or 5 folks virtually who are joining us by remote control, but if I could have the nucleus folks stand and we could acknowledge them as well, that would be great. So thank you all for the nucleus team being here. Thank you. Now, as you know, attendance at the summit is by invitation only. And I'm very pleased that we invited a very diverse group of folks, over 200 people from around the world, and also a little shy of 40 from our federal agencies. Now, what's interesting, of course, today is September 30th. Tomorrow is October 1st. What happens on October 1st in the United States? Oh, it's the new fiscal year. Oh, do we have a budget going across the boundary? Oh, this word shutdown we hear a lot about. So federal employees were obviously very reluctant to travel because if they get stuck on October 1st or 2nd, you know, there's this thing called the Anti-Deficiency Act where you can't spend money. It gets to be very complicated. So unfortunately, a lot of our federal colleagues couldn't join us. I think we have several joining us virtually, but it's understandable they were reluctant to travel. So finally, just a little bit about logistics. The Commerce Room has been reserved. It's just outside as a nursing room or a quiet room. So that is available to you if you need it. If you have any sort of issues, please see Deanne in the back with the bright orange shirt. If they get solved, it's credit to me. If they don't get solved, you can blame her. It's just how it works. No, Deanne, I mean, she knows who to talk to if she doesn't have the answer. She's absolutely extraordinary. Restrooms just outside and immediately to the left. And as you heard previously, we do have folks joining us by Zoom from all over the world. And the plenary sessions here are being recorded and also streamed live globally on YouTube. So we ask people, if you want to join, please let us know who you are so that we can actually track that and put it in our NSF report. And so these sessions are being recorded, and all the slides, the recordings, and all the other materials, all the slides and stuff will be put on the Summit website at the conclusion of the meeting, but they'll also be permanently archived here at the University of Illinois, because that obviously is a requirement, a data requirement of our grant. And we will, as I say, be submitting a report to NSF that summarizes everything here. And so we will, for the nucleus team and the planning committee, they will look at the drafts of that and so on. Finally, with regard to the agenda, we have a set of very specific goals day by day. And we've structured the summit to maximize the amount of time that we spend talking and looking at issues and talking with each other and so on. So we have opportunities for you on multiple occasions here to submit your ideas electronically, as well as through our discussions, through our breakout groups and so on. And today we're going to hear from a variety of individuals on topics that really set the stage for some of the deep dives. We're going to hear from practitioners. We're going to do a kind of around the world tour of some of the Earth system models, the tremendous exciting things that are happening with them, and also artificial intelligence, the incredible things there as well. And I really want to kind of highlight the point here that we're going to look at the previous day's activities at the beginning of the subsequent days. And one of the things I really want to underscore here is that although the planning committee, we've developed breakout topics ahead of time, we've got those in our pocket. We want this summit to go in the flow of however you feel it needs to go. This is your summit, okay? So even though we've got topics ready just in case, we're going to be listening, taking notes, and so on. So when we go into the breakouts, you might say, well, here's what we really need to be talking about. And we look at our list and we're like, well, that's not on our list. Okay, forget the list. Those topics that you come up with that you feel are important, that's what we're going to talk about. So this is your summit to drive. It's your summit to frame. And that's what we're going to focus on talking about. So we're going to be very, very flexible to allow this summit to move forward and to adjust and adapt in whatever ways you feel are appropriate. We can even tweak the agenda as well as time goes on. So any questions about logistics? Have I covered everything, Deanne? Have I missed anything? Pretty much gone over everything? Okay. Anybody have any questions about anything? Okay, great. Well, I hope your travel was uneventful, and that I know some folks that were, in fact, one of our colleagues who's in Asheville, she was unable to attend simply because of the hurricane. My department head, he just lost his dad about 3 weeks ago, and his mother's house got flooded in Florida and destroyed. So, I mean, folks have been hit really, really hard. And I think the Chancellor and Susan both underscored the importance of what we're doing. This is where the rubber meets the road and the kinds of things that we're going to be talking about. So I'm going to spend just a little bit of time to kind of set the stage for us, and then we'll transition into kind of this around the world tour of some of these extraordinary models. I'm going to start with a quote. Challenges are what make life interesting, but overcoming them is what makes life meaningful. I think that's so important. We as academics, as researchers, as practitioners, as users of information, life is very interesting, but what we get meaning out of, and what I as a professor get meaning out of a lot of time, is helping students with their challenges. Coming to office hours and asking questions about homework assignments, that's important, but I can count really on maybe both hands when students have come to me with really deep challenges and I've been able to help them. And then 20 years later, they say, you know what you said was so important. It really completely changed the direction and helped me out. And I'm like, oh my God, what did I say? You're kind of like, oh my goodness. But that's what makes life meaningful. And we have a track record as humans of doing really audacious things, right? Overcoming huge obstacles that they don't tend to dissuade us, they tend to motivate us. And you think about putting a human on the moon, creating the internet, sequencing the entire human genome, building the Panama Canal. How crazy was that? Modeling the entire human brain, and obviously simulating the Earth system. Going back to President Kennedy, he said something that I thought really touched me deeply. He said, in the context of the Apollo program, he said, we do these things not because they're easy, but because they're hard. And each of these activities I just mentioned have had profoundly important impacts on society, both to us individually, as individual people in our lives, but also globally. Climate change, as we know, is a global challenge, and it's a very complex one. It's not just about understanding the Earth system and trying to replicate it, but trying to understand the future, estimate the future. And as we all know, extraordinary progress has been made in the last several decades and continues to be made, not only through computational work, but theory and experiments, even laboratory experiments and things like atmospheric chemistry, really advance the state of knowledge. But the notions of climate change fundamentally and the research related to it, they're not without critics. And climate change, just like all areas of science, are not devoid of areas worthy of criticism. But I think it's really heartening to me, as a scientist, as a meteorologist, that our limitations and capabilities and understanding the limitations we have, they're increasingly and openly acknowledged, and thoughtful strategies for overcoming them are being proposed. We're not shy to say, you know what, here's what we know and here's what we don't know. And I think that's really, really important. And this community, I think, does that so well. But it's important to recognize that a lot of these limitations that we face are not some fundamental limitations of our understanding or our capabilities. They're limitations that really we have because of the tools that are available to us. And all of you know, of course, that the principal tool for estimating climate, the future climate, is the computer model, now called Earth system models. And they've been around for decades. They continue to grow in sophistication and realism and also in computational complexity and cost. But the limitations of the computational systems available to us and the numerous aspects of the Earth system they have to simulate, and also the duration of the simulations out to a century or so, force these models to be constrained in their realism. It's not really the models, it's really the environments that we have that really force us to constrain them in certain ways. The coarse grid spacings, relatively simple representations of clouds and so on. Our weather forecast models, which is where I've spent my whole career, on the other hand, they operate over much shorter periods of time. They're not required to contain nearly as many degrees of sophistication in physics and things like that. The computational requirements are still large, but they're not what we need for Earth system models. And weather forecast models have transitioned from mesh spacings on the order of tens of kilometers down to a few kilometers. And this is because of advanced high-performance computing that we've seen develop over the last several decades, with other factors like advancements in data assimilation, better model physics parameterizations. And all these things have contributed to what really a lot of people call a revolution in weather forecasting. And I can tell you the jump from grid spacings on the order of tens of kilometers down to a few kilometers in so-called convection permitting models was really important for a lot of reasons, but especially because these small-scale extreme events like we see happen just recently, they cause significant loss of life and damage to property. And George Bryan is here with us today, and George has done a lot of work really looking at what resolutions do we actually need really to do different kinds of things. And that's a very important thing that we're going to talk about. Also, we learned something very interesting in the weather community as we move the models from tens of kilometers down to just a few, and that is that this gray zone, I call it, of 6 to 10 kilometers, so versus 1 or 2, the scale separation arguments that are used really to divide what is explicitly represented in the model and what is implicitly represented, subgrid scale processes, those scalings break down. Those separations of scale arguments kind of break down. And also the non-hydrostatic processes that are very important at fine scales, especially for deep convection and so on, they're not well represented at grid spacings on the order of 10 kilometers or above. And so we found, in fact, through a lot of experiments and published papers, that the evolution of the storms is much slower, the size is wrong, and so a lot of it is just simply not correct. So the importance of higher resolution, or even greater sensitivity, you might call it, it's not unique to our field at all, right? In most areas of science, when you look around at different disciplines, they're all about improving resolution and sensitivity. Whether it's brighter light sources in synchrotrons or larger mirrors and optical telescopes that allow us to see farther back in time and with greater resolution and fidelity, or greater sensitivity in interferometers to detect gravitational waves. And I'll come back to that in a second. Or larger number of atoms in molecular dynamic simulations. Everything you look at goes to finer and finer scales, more fidelity. And so we're in this sort of world group of organizations and disciplines that are all seeking to do that sort of thing. So in my view, because of that, it's not surprising that several groups around the world, many of whom are represented here today, have undertaken extraordinary efforts to take Earth system models down to a few kilometers of grid spacing. And as folks here can tell you, and we'll again do this kind of around the world tour, and you've got Jim Hurl here, you've got Dave Randall here, a lot of folks that have done this. I tell you, that is not an easy task at all. It involves rethinking major parts of the code and retooling it, physics parameterization, subgrid scale processes, mapping the code onto different sorts of architectures, scaling issues. John Schauf can talk your ear off about scaling issues and strong scaling, very, very important. And couplers that link parts of the codes together. Those pesky things, my goodness, they create all kinds of problems. So it's not an easy thing. And so you're going to see after the break here that these efforts in kilometer scale modeling are breathtaking. They're inspirational. They're absolutely extraordinary. But they're also important scientifically, but especially for things like the Chancellor mentioned, of really looking at dealing with these very high impact local kinds of events. And those who have to make decisions, whether it's in the risk arena, the reinsurance arena, whatever it is, very, very important. So the value of these fine scale models to most folks, or I shouldn't say most, but a lot of folks, is pretty obvious, right? Especially to those who've seen the transformation, as I have, in weather prediction, numerical weather prediction, as we went down to kilometer scale models. I think it's generally agreed that these kilometer scale global Earth system models are essential scientifically, and also for addressing a lot of the limitations that we see in models and how they're operated. Again, not fundamental challenges of models, but how we have to operate them on today's computers. And that's what we're going to, of course, talk about here. Whether it's representing the land, atmosphere interactions, tropical cyclones, topographic forcing, clouds, convection, so on and so forth. Those kinds of things are important. But at the end of the day, it's the stakeholders and the users of climate information, as the Chancellor mentioned, transportation, agriculture, all these different areas, they're really depending upon us to be able to address some of those challenges. So I wanted to show you just a few excerpts from some papers here about this issue of fine scales. And I'm going to kind of flip and look at the other side of the coin. So this paper by Roberts et al., talk about global resolutions affordable over the next decade. And you're going to see this as a recurring theme in some of these things. Contribute large uncertainties in our climate simulations and projections, and large uncertainties in sensitivity and so on. And so it really kind of, and this is that honesty factor I talked about, of really saying, here's what we know, but here's what we don't know. I personally believe this isn't due to a lack of sophistication in the models. It's been driven by the constraints that we face with the models that we've had to use in terms of the computers. This really gets to the issue of numerical weather prediction. The 30 plus years of IPCC reports, the Royal Society talked about this quiet revolution in weather prediction, and asked the question, why hasn't climate modeling followed the same path? Well, it's because, as I mentioned, you need extraordinary computing power with these very sophisticated Earth system models that have biogeochemical cycles and aerosol physics and all these other things that weather prediction models really don't need to have. And so really the capabilities, as it says, sort of eclipses what is available. And here it talks about the heart of the problem with the Royal Society, again, being the issue of resolution. And it gets to the issue of extreme events and also two-way interactions, global interactions, things like mesoscale convective systems that drive interactions across the planet, these persistent deep convective systems. And we don't really have a deep understanding of how that works because we don't obviously have the models that can run these things for very long periods of time. And then finally, the paper by Hoffler et al., they talk about, makes it impossible to represent these physical processes that are very locally relevant for the fine scale of weather. And again, talking about the significant uncertainties that we face. So the key points that they make overall, of course, that feel that fine scale resolution can improve the representation of these fine scale phenomena, clouds and convection, reduce uncertainties, and also capture better these global interactions. But it's also important to note and look at the other side of the coin that these views aren't shared by everyone, right? Those who question the use of fine spacing in Earth system models, they have some good reasons for doing that, I think. But among them are the following. First of all, that such models are viewed as, very valuable someday, but they're impractical on current computing systems. In other words, the arguments that are made are that, centers around when such models are going to be valuable and practicable, but not if. And the when part is viewed as not today, not now. And this point was made in a paper by Tapio Schneider, talked about kilometer scale models that stretch the limits of what is computationally feasible. And they can only generate a few simulations. And Tapio's absolutely right. Tapio's here. And it's an extremely important point. In fact, they point out in the paper that one simulation at 1 kilometer grid spacing is the same as 1,000 at 10 kilometer grid spacing. It's a very important thing to think about. Other points that are made in those who kind of question it talk about, understandably, the current trajectory of computing system development. It ultimately will get us there, But especially, it really underscores the importance of artificial intelligence and machine learning. I'll come back to that in a minute. There also, I think, is fear that emphasizing these fine-scale Earth system model development might detract from or marginalize or reduce funding from some of these other efforts that use globally coarse resolution large ensembles or more traditional methods such as statistical and dynamical downscaling. And that need not be the case, as I'll come back to in a minute. There's also the argument of the cost of implementing these models, including specialized computational systems. And again, kind of a diminution of funding for research with these other areas, and maybe even limiting the workforce availability. I had a wonderful discussion with folks at NCAR about this last year, about the workforce availability. When we think about how the climate science community is moving forward, where's the workforce coming from? And there's also concern that the sizable energy requirements and carbon footprints of the computational systems that are needed to run these models, they'll actually exacerbate the very problem that they seek to address. It's a very interesting point. These are all very reasonable points. And with regard to computational resources, and Andy Prine at NCAR really underscored this point in a graphic that I'm not showing you, but he looked at the evolution of computing systems for the IPCC assessments, and it suggests, if you extrapolate forward in time, that the kinds of computational capabilities we'll need to do those sorts of assessments with kilometer scale models, physics-based models now, not AI at all, to inform these assessments wouldn't be available until about 2050 or 2055. So that's kind of daunting. But now enter artificial intelligence and machine learning. We know they've had an absolutely transformative impact on so many things, including the atmospheric sciences. And I've been really astounded at what I've seen with numerical weather prediction. I mean, weather forecast models, you'll see some of this, that are really outperforming these AI-based models that have been trained on ERA 5 analyses and so on, really, being competitive and in some cases are surpassing the capabilities of physics-based models. And also they're calling into question, I think this is fascinating, fundamental limits of predictability, the Lorentzian kind of limits of predictability. What does that mean in an AI world? And machine learning also is now being used, we're going to hear about the neural GCM a little bit later on, in terms of physics parameterizations and the creation of large member ensembles very inexpensively compared to running physics-based models. So, the relationship between physics-based and machine learning-based models, it's very symbiotic because the machine learning models have to be trained on something. And so having those models and the reanalyses are very, very important. But I'm really amazed by some of the work at ECMWF and other places that are looking actually at prediction now with purely data-driven machine learning models that completely bypass physics-based models altogether. So the time by which we're going to see kilometer spacing models in physics-based Earth system models, it's not clear. But we do know, I think, that AI is going to probably bend that curve and accelerate progress dramatically. The impact on numerical weather prediction is pretty much obvious. But there are questions about AI applied to the climate system models and so on. That's a really important research question, and a lot of work needs to be done and is being done. So I think it's clear to you now that the development of these fine-scale models and the work being done in AI, that's one side of the coin, right? The other side of the coin involves the computational systems, and that's what we're here to talk about. And everyone recognizes these systems are not today up to the task. By that, I mean they don't have the ability for physics-based models alone to create appropriately sized ensembles of multi-decadal or century-level simulations at global mesh spacings on the order of a kilometer. In fact, one of the things I find as a scientist very interesting, how do you initialize those models, right? I mean, Jim Hurrell has taught me a lot about how regular climate, of course, the literature too, how regular climate models are initialized. You run them for a long period of time and so on until they kind of settle down, reach from some reference climate state, you start turning things on. When you're talking about a kilometer scale, how do you do that? I mean, you're really talking about, do you do data assimilation? I mean, this is very important research that needs to happen. So I think the point is here that there's a lot that we don't yet know. And Earth system models today are only able to extract a small percentage of capability on even today's most extraordinary computational systems that are designed for massive loads. And, these models are elegant. They're just incredibly sophisticated. And I kind of think about them when we look at how they're run on today's computational systems, like Formula One race cars, saying, okay, you've got a Formula One race car, but guess what? You can only drive it in a school zone. You're like, oh, that's not very exciting to me. How do we unlock the full potential of these incredible models that we have? How do we really help them know how to, explicitly resolve these fine scale events, features that are found in weather models, especially deep convection and shallow clouds that are very important in the radiative balance? and provide the decision-making information that practitioners need and certainly are telling us they don't currently receive. They're not getting it. So you could ask the question like this: will the evolution of computational systems as is presently envisioned be sufficient to support these large ensembles of kilometer scale global simulations to help answer obviously key scientific questions, support local and regional decision-making regarding climate change? That's a really, really important question. And recognizing that the future of HPC, of high performance computing, is largely in AI and machine learning, the question I think is, how do we leverage that known future of AI, that AI-based future, and AI-centric computational environments in ways that address these performance limitations of these Earth system models and create this extraordinary marriage between hardware and software, between AI-based and physics-based models in a co-designed framework? That's really the key question. And that is the other side of the coin, in my view. A computational environment that turns our models, loose on the open road. That really, I think, is the key. And provides the realism, and I think the really important term that Barb Helen mentioned, the value, the realism and the value that are needed and expected and realizable, I think, more than a lot of folks realize today for end users and practitioners. So we've obviously gathered today here at this summit an absolutely extraordinary, very diverse group of international experts, scientists, users, technologists, engineers who understand the climate change issue and those who are impacted by it and who deal with it day to day in terms of decision making. We're going to hear some of those stories at lunch. And we're here to consider what I think is kind of an audacious proposition. And Chancellor Jones, I think, said this very, very well. It's a proposition that really addresses the unmet need of the community and really leverages the incredible pioneering work that's going on in Earth system models and artificial intelligence globally. So the proposition is this: the creation of a specialized computational system for globally fine-scale models, coupled or tethered to AI and machine learning in a completely, interactive, completely coupled matter to better understand the Earth system, obviously produce more accurate projections of the future. This is key. Educate the next generation and meet important stakeholder needs. That's really, I think, what it's all about, what we're here today. And if we were able to do this as a global community, I think it'd be an absolutely radical advancement. And I think, as the Chancellor said very well, to try to do this in traditional ways, it's not going to work, because I think we would have already done it. I think we have to think very, very much out of the box, to where we can't even see the box anymore. I can't think of any global challenge other than a few other ones. There's few other global challenges important as climate change. And we are very well poised as a global community, because look at CMIP. We know how to collaborate with one another. We already collaborate really well. The question is, are we going to do it? And when you see something like this, it's very easy to say, this is really hard. You're right. And it really can't be done. But the benefits to be wrought, I think, are extraordinary. And it takes me to another quote here by Zig Ziglar. It says, difficult roads often lead to beautiful destinations. Kind of feel that way sometimes when I'm flying into Champaign-Urbana. It's kind of difficult to get here. But when you're here, you can enjoy all the corn and soybeans in the university as well. But before talking just a bit about how we could get to our beautiful destination, let me give you a couple of examples of really bold international projects that provided extraordinary benefits to individual researchers, individual investigators, their students, and their institutions, and even the science enterprise more broadly. And in some cases, in fact, I think I would argue that these examples, I'm going to show you these two, it'd be kind of more difficult, far more difficult for them than for us to talk about the practical benefits to society. So the first example I think you're aware of is called LIGO, the Laser Interferometer Gravitational Wave Observatory. I was very familiar with this because on the science board when we approved this thing, and it confirmed the existence for the first time ever of gravitational waves that were postulated by Einstein over 100 years ago. And it was absolutely a groundbreaking achievement. And what it did was, it's a global enterprise now, and it's opened up a new era of gravitational wave physics across the planet. Absolutely a whole new area of scholarly endeavor. So that was really extraordinary. The other one is one I think that you recognize, the so-called Event Horizon Telescope, another global project that involved instruments around the world that created the first image of a black hole shadow. And NSF has this beautiful poster that shows the above the fold newspaper images of this thing globally. There were hundreds of newspapers all around the globe. How many people do you think in society understand what a black hole even is? But it inspired people. It's like, oh my God, there's a black hole. We see it for the first time. And these instruments that were very, very expensive to create, they were planned with the idea of ensuring the robustness of research funding to use them, to support them. And they have led to numerous doctoral degrees, master's degrees, all types of institutions involved, public engagement in science. They inspired so many to get into STEM education. They engaged traditionally underrepresented groups and disadvantaged communities. And both of these things garnered Nobel Prizes. They created enormous benefits and enormous research opportunities and resources for astronomy and physics departments around the planet. Neither of these efforts sucked the life out of individual research projects, but in fact, they provided new capabilities for them. Neither of these things would have been possible had they been done by one or a few institutions, exactly what the Chancellor said. They required international collaboration on a very grand scale and the associated communities to come together. And it's true for other things like the LHC, the Large Hadron Collider. And some of these large projects, they had a lot of funding from philanthropic organizations. And we're going to talk about potentially how we would fund the kind of thing we're going to be talking about here in some of our challenge sets in the breakout groups. But this project that we're talking about here, which is really global, has kind of 5 major questions associated with it, I would say. The first one involves stakeholders and practitioners, and we're going to deep dive into this. What are their needs, and how can they be used to drive this fully integrated system from the very beginning? Not as end users, which puts them at the end of the line, but as being at the front of the line. Very, very important. And something I know my colleague here, Francina Dominguez, keeps reminding me of, and she's so right, making sure that everyone has access to information. No limitations to access to information at all. Very, very important. Second question, can these models make a significant difference in our understanding without diverting resources from existing efforts, which these coarse grained ensembles, the downscaling stuff, really important. We don't want to shortchange that or somehow interfere with the funding for it. We need to grow the enterprise overall. And what research is needed to enable this? These models are going to create incredible research opportunities, but what research is needed to actually actualize and realize their capabilities? What type of computational environments will be needed to enable this capability in a co-design framework in a timely and energy efficient manner? And this is what my colleagues from DOE always remind me of. They think a lot about energy efficiency, and that is something that's critically important. How can the capabilities of AI and machine learning be utilized most effectively? And think about the future workforce. Right now we sort of have degree tracks in climate and weather and so on. How about the economists? How about the folks that are in agriculture that are increasingly needing to understand about these things? Could we think about creating educational programs, not in weather or climate, but at this intersection of weather and climate? You get down to kilometer scale models, you're in this zone between traditional climate and traditional weather. We got to think about how we educate the workforce and bring in a lot of these other disciplines, including policy and economics and risk and so on. Then finally, what organizational administrative frameworks would help facilitate this as a global initiative in an environmentally responsible manner? These are really key questions. So we're going to talk about these things in the challenge sets and in the breakout sessions. So you're going to hear a lot times people will mention, and I say this a lot, these kilometer scale models are really not a silver bullet, a magic answer, a singular solution. They're not a means for replacing or displacing work that's already being done. The value proposition here isn't about kilometer scale models or downscaling or large member coarse grid on site. It's not an either or proposition. It's about these models and everything else in a portfolio approach, a toolkit for us. And that includes the human, behavioral, social, economic sciences dimensions as well. We only need to look to the physics and astronomy communities for inspiration to know that this displacement doesn't have to happen if we do it thoughtfully and carefully. So we have a new opportunity, I think, to create a new generation of individuals who are educated at the boundaries of these traditional disciplines. I think we also realize that the multiplicity of these modeling systems is very valuable for research that informs international assessments like CMIP, quantifying uncertainty. We're going to hear about that from Tim Palmer later this afternoon. Computational grids, developing new parameterizations and things like that as educational tools, people being able to run these various models. But in the context of globally fine-scale Earth system models, they require extraordinary work, extraordinary expense to develop. And so a lot of folks argue that the collective investments that we make in these models might be better done if we sort of utilize kind of a single modeling framework, not a single model, but a single modeling framework and a specialized computational resource that is established for the entire global community, kind of along the lines of the Large Hadron Collider, things at CERN and so on. So the importance of global coordination is important. And Julia Slingo published the paper with co-authors in Nature Climate Change, and they argued the same point. They said, the development and evaluation of a new generation of models, she's talking about kilometer scale, can be accelerated beyond current national efforts. There needs to be a shared research and development program designed around the goal of delivering timely, detailed, consistent, and actionable case-scale global climate projections within 5 years. Bjorn Palmer and Tim Stevens long ago called for a CERN for climate change. And they pointed out that some of these large particle accelerators have gotten so sophisticated, so expensive, they've moved from individual institutions like at Stanford into global enterprises because of that complexity and cost. And they made the point that CERN didn't just transform the physics, in terms of its research, they transformed the community in terms of collaborative efforts. And I wonder if the same could be true for the kinds of things we're talking about here. Bjorn Stevens' Earth Virtualization Engines project, the same kind of thing, another way to think about organizing the global community. Numerous other activities are underway to organize ourselves. DOE has this new thing called Science Security, or AI for Science Security and Technology, or FAST, that has 4 pillars, data, computing, workforce, and partnerships. So there's a lot of things going on out there like this. And, I really believe that we as a research community, I think we generally agree that these globally fine scale models, be they physics-based or machine learning-based or some combination of the two, they're the way forward. They're the obvious way forward. The practitioners and users of information tell us that this detailed and reliable, and again, that's Barb Helen's term, this reliable information is essential to their work. We're going to hear from Renaissance Reinsurance. We're going to hear from other folks at lunch how this kind of information is critical to them. These fine scale models are quickly becoming reality. We're going to see some examples of that. I mean, they're just extraordinary. What is not quickly becoming reality are the computational capabilities needed to realize the full potential of those models. And so in my mind, if we can realize that computational capability much sooner, it's going to be a greater transformation than what I saw in numerical weather prediction. When I co-founded the Center for Analysis and Prediction of Storms almost 40 years ago, Doug Lilly and I had the vision of predicting individual thunderstorms with a computer model initialized with real data. Most people, including Lorenz's theories, said that really is not possible. It's probably theoretically impossible. If you could do it, you might be able to do it for 15 minutes to half an hour. It's being done today, hours on in time for forecast. So that was a huge transformation. Now these things are being run operationally. So I think we're at a seminal moment really in history here, that as a global community, we can come together and truly do something astonishing to usher in a new level of understanding about our planet and greatly, greatly accelerate our ability to address one of the foremost challenges that are facing us. And I really, truly, in my heart of hearts, believe that we can rise to the occasion. And I think the only limitations that we're going to face are those that we tend to put on ourselves. We tie our own hands. So I think we don't want to do that. So I've gone just a little bit over time, but hopefully that helps set the stage. And really, I'm grateful for all of you coming here. It's going to be a very, very exciting 3 days. Again, lots of time for discussion. And in fact, right now, we're going to take a break. We're going to have you think about what I've said here, which I hopefully accurately reflects all of what we've been talking about in the planning committee. And I'm going to put up a QR code here. And you can submit some questions and thoughts in a system here that Francina has created. And in fact, Deanne, I don't know if this is on the Summit website yet. This isn't on the Summit website yet, but this gives you an opportunity to put things together here. We're going to have some stuff when we get in the breakouts tomorrow. It'll be a Google form that you can submit stuff to, but this thing you can actually submit your comments, your questions, anything you want to say to this Google Doc, and then we were going to synthesize this and use this to help drive the breakout session. So Francina, do you want to comment on this at all? Did I get that right?
Yeah. We're going to compile this, and then at 2:15 is when hopefully we can bring everything together.
Gotcha. Okay. So we're going to take a break now, I think until, what is it, 10 o'clock? I don't have the agenda in front of me. Till 10:15. Okay, till 10:15. So you've got some time to talk and to interact with one another, and please submit your questions, and we'll reconvene at 10:15 for a session which will be titled Progress in Fine-Scale Earth System Modeling Around the World. And we're going to see some incredible presentations from folks globally about some of these extraordinary models, both physics-based and AI-based. And we've got NVIDIA, we've got Google. You're really going to love this stuff. And this will set the stage then for our lunch session, where we hear from practitioners and end users and stakeholders. And then we'll have more time for more time for comments and things like that through the end of the day. So thank you for your attention, and we're at break until 10:15. So thank you much. Yeah. Sorry. You want me to go back, you say? Oh, yes, sure. Yeah. Sorry. Okay, great. Thank you all. That's how it was. Yeah. I triple checked. Did you look at your slides here? Okay, yeah, you want to? Okay. I'm pretty sure they're okay, but you never know. Okay. Here, yeah, he's gonna log and see. Yeah, I'll go make sure he does that. Yeah, the student life should be here. I sent an email reminding them to be here, so they should be here at the end. I'm gonna go get the little thing from her. Did I say anything? Are you sure? Okay, good. Okay, I just want to make sense. Because I had some people at Empire saying, we're going to try that last week. We're not really sure. And they said last night, they said, we're all in. I was like, praise God. Right, because previously. Right. Right. All right. Well, we're going to go ahead and continue now with a panel session, kind of around the world tour of some activities in fine scale Earth system modeling development and also artificial intelligence. So this session is being co-chaired by Ruby Leong of the PNNL, and also Bjorn Stevens, and also Maria Molina. I left your name off here, Maria. Sorry about that. And also, I think it was you and Andy, you instead of Andy. Anyway, the agenda is correct, and we're going to be going in the order that you see in the agenda. And each presenter will have 10 minutes for this session, and we have timekeepers up in front here, and there's a big hook somewhere around here. I think some will pull you off the stage. No, just kidding. But I want to thank all the presenters here, and some of these folks are virtual, so we will then switch over to their slides when the appropriate time comes. And so let me go ahead and turn it over to our co-chairs here, and we'll get started. Thank you. Oh, let me just mention real quickly. It was very difficult to run power to the tables, so we do have charging stations. Deanne, she's out of the room. I think they're in the back here. At least they were somewhere. I saw it over there. Where's it? Oh, right back there. If you need to charge your electronics. Sorry about that, but there was no way to actually run the power. We will have it in the breakout rooms tomorrow for the actual tables, but here it was very difficult to do that. Okay. And here, if you want to advance their slides, they can use that or just that. Yeah.
So after Kelvin's wonderful opening remarks, so I think we now kick off for the first panel session. So we have a number of speakers. I think this is a really important panel to give us an overview of the current status of kilometer scale modeling. So let's hold the question until all of the speakers finish presenting, and then we would have time for question and answer as well as discussion. So with that, our first speaker is Andrea Prime. He's going to talk about kilometer scale model survey results.
You're welcome, everybody, from my side.
Yeah.
Okay. So what I'm presenting at the moment, or in a minute, is the results of a survey that we did a couple of months ago. So we sent out a questionnaire to all the major modeling centers that develop kilometer scale Earth system models at the moment globally, and received quite a lot of feedback. This is really to take stake of what the status of these models is at the moment, how the common challenges are, and where these modeling systems are moving towards to. Can I do something from up here to change the slides? Do I have to? Oh yeah, this was easy. Okay, thank you. So just first of all, I really want to thank all the model developers that sent feedback and allowed us to present these results. I think this is extremely valuable to know what the starting point is and where we are at the moment. Again, just to say that, like, this is a momentary analysis. We did this a couple of months ago. These systems are under constant development and continue to develop over time. This is also not to rank the models, so don't get this wrong. We really want to show what the status is, the common challenges, some of the major achievements that were made over the last years, and to see how we can move forward from where we are at the moment. So we, in total, got eight different model development systems or model development centers replied to our survey. Those were GemStack in Japan with the NICAM model, ECMWF with IFS, UK Met Office with the K-Scale project or Momentum, DOE with the SCREAM model, GFDL with X-Shields, CSU with Earthworks, CSME, ENCA with MPAS, and the Max Planck Institute with ICON. And you will hear more about the systems during the later part of this session. So the first thing that we asked is, what language are your models written in? And historically, if you work with climate models, you know most of these models are Fortran. And this is still the case until now for this high-resolution kilometer scale models for most of them. So most of them are majorly written in Fortran. There are some pieces in some of these models which are written in other languages, but majorly they also are Fortran models. One big exception here is the SCREAM model. It was completely rewritten into C++ and Cocos. I also want to mention that there are two activities ongoing at the moment. At ETH, actually, ICON is rewritten into Python, and also Shield has this plan to rewrite the model completely into Python code to more efficiently run on current supercomputers. So this is then also reflected into which hardware these models are running on. So most of these models are still majorly running on CPU machines, and E3SM can really run on almost, or Scream model can almost run on any machine nowadays. So this is like they use, for example, the Frontier machine at the moment a lot. There's some plans, or all of these systems, I think, have plans to move over to use more heterogeneous machines. How they do this is quite different from modeling system to modeling system. Some are rewriting the whole code, as I already said. Others are using, for example, OpenACC or similar platforms to port the code over to GPU machines. What we also asked was, what is the longest integration that you did with your modeling system so far? And I should add some details here because this is really important. The longest integration largely depends on which grid spacing you're running. Like we already heard, if you double the grid spacing, you have 10 times more computational demand. So running at 5 kilometers or 3 kilometers is a major difference in computational needs. So what you see up here, ICANN and the IFS model, and we will hear about those two modeling systems in a minute. They are run within the European Destination Earth framework and NextGen project. So there's a major investment from the European Union into these modeling systems. They have now 30-year integrations, which is quite a major achievement at 5 kilometers and 9 kilometers. I also want to highlight the NICAM simulation here. I think this is probably the one that has the highest computational cost so far, 3.5 kilometers over a decade. So that's a major computation as well. And other modeling systems are on the order from a couple of years to 1 year when we took this survey. And again, like this is all in motion over time. Most of these modeling systems are currently ran in atmosphere only. So there are only a couple of those systems that are really run fully coupled with a coupled ocean. All of the systems have plans to do this in the near future. So there's major development going on. I think there's also opportunities to really join to share expertise here for how to do this best. And I will talk a little bit more about this in my next presentation later on in the session. So then we also asked, how fast can you run? And I only show you 4 of these simulations because they really reported the maximum speed that they can reach if they use a large fraction of a current supercomputing system. And 2 I wanted to highlight here, the NICAM simulation, they used the whole Fugaku machine to get up to 2 years per simulated day, which is really fast. This is incredible if you think about it, how fast this can run. But of course, you need the biggest supercomputers on Earth to do this. And also the Scream model with 1.25, 1.5 years per day, simulated years per day, if you run the whole, like the Scream model on all of the Frontier machine. Then we also asked, where is the compute going to? Like, what is the most expensive part of your compute? And there's a little bit of diversity. Maybe we can learn a little bit more about NICAM. NICAM spends a lot of their resources into the physics, whereas normally if you go to very high resolution to kilometer scale, the dynamics and numerical core takes up the most resources. And this is what you can see from most of these feedbacks that we got. I/O is also sometimes a fraction, like a larger fraction, but this seems to be something you can improve and get control over. Some additional comments here. IFS reported that approximately 21% of their compute goes into the ocean, but this is 9 kilometers, so this might change if you go to higher resolution. Max Planck reported also that they run the ocean on CPUs and the atmosphere on the GPUs, and the ocean can keep up. So this is another interesting mix and match that you can do here. And the Earthworks project reported that especially the coupling between the systems is a major bottleneck. So this is certainly something we have to keep in mind as well. How to couple Earth system components to each other at this grid spacings is not trivial. Looking at the scaling, the weak scaling is great for all of them. I didn't hear, like nobody reported that weak scaling is an issue. Strong scaling can work pretty well for most systems, but communication becomes an issue if you scale up to very big jobs sometimes. And what we heard over and over again, if you run on GPUs, you have to provide each GPU with a lot of compute. So they have to be kept busy to run efficiently. So you really have to have big jobs for GPU machines to run efficiently on GPU machines. The pathway to the largest speed up, I just wanted to highlight 4 of those that were quite common. Moving to GPUs or heterogeneous architecture seems to be the path that everybody is taking at the moment, or most systems are taking. More powerful HPC systems. I guess this is one reason why we are here. So having faster, bigger supercomputers are definitely important. Coupling the model to other components. The coupling is certainly something that can speed up the simulation quite a bit, and reduce precision. So if you run in reduced precision, you can also speed up the code quite a bit. This is an active area of research. So some takeaway messages here. So most centers are really moving to using GPU based HPC system in the future. There's no unified way how to do this. Rewrite the whole code, port your Fortran code. Like, there are many different approaches tested out at the moment. It's not really clear which one is the best, or depends probably on your application. 1 to 2 simulated years per day is already achievable with these systems, which is quite a major achievement, as I already said. So this puts us already very close to, I think, what we want to do in the near future with this activity. The numerical core needs typically the largest amount of resources. So this is it's often not the physics, although the radiation can also take a lot of resources, but the numerical core is normally the major, in the atmosphere is the major part. Improved data exchange, so how you move data around in the system is really important, and reduced precision can lead to big speed ups. And last but not least, efficiency. We didn't really target any feedback about simulation efficiency, for example, watts per simulated year, but it is certainly something that's very important that we should keep in mind, and it should really be a focus area. But how to measure this efficiency is also not very trivial. So thank you very much.
Okay, and next up, we're going to head over to our friends in Europe. The first speaker will speak about Destiny IFS and ICON, Niels Weddy.
Okay, I hope you can hear me. I can't see the slides yet, but let me take the opportunity to thank you for the invitation to this workshop, and I'm happy to give you a quick review of
We
what
cannot
we have.
hear you.
You cannot hear me? Still not?
Folks online can hear. We can't. Folks
Oh.
online can hear. We can't.
So folks online can hear, but we're not getting sound.
Okay.
We have to ask Niels to talk.
Bjorn says online works well.
So what are you going to do? You're gonna switch something in the room, or? Okay.
Are the room lights too bright, or should we try to dim them? You okay now? I think we might want to move on to Misaki and come back, yeah. Okay, while we're troubleshooting that, let's go ahead and Professor Sato, Masaki Sato, I'll go ahead and bring up your slides and we'll move on to you and then we'll come back. We don't want to lose too much time here. So let me go to. That's good. Mouse keep unplugged. Okay.
You want me to say something?
Ah, yay. All right. Thank you. Okay. There we go. Okay. Great. Run the slides. You can do it from there. Okay.
Okay.
Let him know it worked.
Yes,
Yeah, Niels, go ahead, please. We got you.
Okay, great. So thank you very much for inviting me and giving you a brief run through of what Destination Earth has achieved over the past 2 years. I can't see the slides, however, but let me just see if I can get the view somehow differently. Could you bring the slides to the main screen? That would be, yeah, better. Thank you. Okay, so yes, let me give a run through, not necessarily what is different perhaps to existing climate simulations, because this is obviously part of this workshop as well, to sort of distill this a little bit more, and to sort of kind of like work a little bit more on this criticism that, and also kind of the worry about the sort of different fundings. But here, obviously, the reason climate change and increase of extreme events is one driving motivator for Destination Earth. And you see here also the elements of the Copernicus service that ECMWF is running, the climate change service, which gives information about the past and the present, and is extremely useful, of course, also in the context of assessing recent events. But Destination Earth set out to do something more, to go beyond that, to go outside and look at bespoke simulation and bespoke simulation services ultimately. And so this is where we get into kilometer scale modeling. So next slide. So Destination Earth is about the 3 major European institutions, ECMWF, EUMETSAT, and ESA, getting together for the first time in such a scenario to work on such a system, to not only build these kilometer scale simulations on existing EuroHPC supercomputing systems, but also to work on ways to bring this information to the users and to the impact sectors and to the people that actually are impacted by climate change. And we work with a large number of countries and organizations in Destination Earth. Next slide, sort of, yeah, and 300 plus scientists and analysts and HPC experts are enrolled in Destination Earth over the past 2 years in order to make this a reality. This is a system that constitutes the digital twins themselves. We have the first 2 with Earth system modeling involved here for the climate DT, but also for weather extremes. And then we have the data lake, which is a platform area, if you like, of fusing data and information from different disciplines and bringing this to the users through a core service platform that is managed by ESA. And by working through the past 2 years with those impact sectors, we also got a better understanding of what these simulations actually need to deliver, how they need to deliver it, and how we can sort of make them more useful. And that's part of Destination Earth too. Next slide. So in terms of timeline, we started in 2022 building these kilometer scale simulations. We had a launch event on the 10th of June this year, and we're gradually opening the system and the data to users as we speak. And the next sort of phase will see the evolution and ramping up of these operations, consolidating more readily, basically being able to do kilometer scale type future scenario simulations on supercomputing systems, and then transition to a more long-term operation by 2030. Next slide. So I mentioned already bespoke cutting-edge simulation capabilities, Earth system information at scales where it matters and where impacts of climate change are felt, and also the weather-induced extremes, and getting a sort of highlighting focus on some of these. Next slide. So the climate change adaptation digital twin is performed by a number of European organizations and scientists. This is led, in fact, by CSC in Finland and many other sort of institutions, including Björn's, of course, from MPIM in Hamburg. Next slide. So this gives you just a snapshot of some of these simulations. We're looking at, I think, 2032. And it is sort of this detail, of course, that was mentioned already earlier, that we're trying to distill and get out of these simulations, and that allow us to more easily couple to those impact sector applications that we want to focus on. And of course, this is just a flashy video, but we have to think beyond what is in this data, both in terms of time as well as spatial resolution. Next slide. So these are the simulations that was already briefly mentioned by Andreas earlier. In fact, we have a 5-kilometer, 112-degree ocean IFS NEMO simulation now for 20 years or something over 20 years in Destination Earth. We have the 20 years of ICON, and we have the 30 years of the IFS coupled to the FISM ocean model. So these simulations, we have them, as you can see on the timeline, for the future scenario between 2020 and 2040 or 2050. In this one case, and we have the historical runs are currently being performed or ongoing, and the control runs are to come in this sort of simulation protocol that has been performed in Destination Earth. Next slide. So this is about operational capabilities that I mentioned earlier. It is about also common formats of these different coupled simulations. So a lot of work and pain went into data governance in order to bring it also closer to the WMO format that we're used to in NWP, in order to serve, in fact, those NWP centers as well with what they sort of expect. And this has been, certainly an interesting process to bring these three models together. And we have also hit obstacles, so there are certain lessons to be learned. But the interesting is clearly this idea of a general state vector coming out from these climate simulation models coined by Björn, that sort of brings together this information and sort of filters the information and brings it to the impact sector through things like what we call one-pass algorithms, what we call diagnostic packages that bring together also the information from the historical and sort of the scenarios in order to statistically evaluate on the fly the information that's coming out from these kilometer scale simulations. Next slide. So here's one example of streaming this information to applications. In this case, it is about wind farms and directly extracting the relevant information, and also perhaps in the future visually using this information to place a new wind farm and then going forward sort of in this planning process, also creating products that are more directly relevant. So this, by talking through the impact sectors, of course, we can produce, say, 100-meter winds rather than sort of the 30-meter winds and sort of the old paradigm of when, NWP models only produce 850 hectopascal temperature, which wasn't extremely useful outside being an expert. But here we really have an opportunity to more closely produce a whole range of parameters that are directly applicable. Next slide. So all of this is powered by what we call the digital twin engine, which is sort of course, that you have, in order to make these simulations work, you have to adapt to different supercomputing architectures. You have to sort of fuse them with machine learning and AI kind of capabilities in order to also work on uncertainty estimation and other aspects of communicating this information. It is about big data handling, of course, and then tailoring this information to user needs. Next slide. So here's one example where if you click one more, then you can see how sort of if you click on the image, it should move. You would see basically, okay, one back then. You would basically see energy redistribution over the Europe in this case where the weather information or the climate information basically is streaming through, and you see the redistribution of different energies from the different European countries as a function of the renewable energy that is provided from solar and from winds. And you can see basically how this information is then provided to users. This may also be just public information to give people more of an understanding, how, say, their energy provision is influenced by weather and climate. And this is sort of something that, unfortunately doesn't matter. So next slide. So renewable energy management, clearly one of the sort of key target areas. Of course, we have worked on many other things with respect to interoperable semantic data access. Now, I can't really sort of go through all of these different elements that I mentioned here on the slide, but there are just keywords basically that also are signaling to you, if you like, new and different pathways to deliver the data, in this case, in a semantic way, as we also use, of course, to NWP, but also, I mean, for me personally, for the first time, I was able to easily kind of compare the ICON and IFS NEMO ocean states by interactively accessing basically this ocean potential temperature fields through this semantic access and the data governance that we have defined in Destination Earth using these Polytope API interfaces, and there are other sort of keywords that you see here and that are familiar to those that work more on the technical aspects of these things. These are all important aspects and milestones of Destination Earth and kilometer scale modeling in general. Next slide. So, of course, we mentioned supercomputing, we mentioned costs. So these are our costs. So one scenario of 30 years took about 1 to 1.5 million GPU hours, or about 34 million CPU core hours for those that ran on the CPU. This is the price of a scenario. So if you want to think about like bespoke multi-scale scenarios, like things that you want to run basically perhaps in the future on demand, per shot, this is about the price. Okay, next slide. So machine learning finally is, of course, an important aspect to see if we can make this price cheaper, or to enhance, if you like, the information that is coming from these kilometer scale scenarios through machine learning. But training efforts should not be underestimated. Of course, 9 million GPU hours is estimated to train on this sort of data, or at least 1 million GPU hours in order to do a full training cycle per year. And of course, the big sort of plus or advantage of machine learning is inference, is basically the fact that you have this 0.1 GPU hour cost per use to create something that has been trained before. So I think that's sort of like the holy grail, perhaps, that we want to get to. And next slide. But I would finish with this sort of, one more, if you could tap one more. This may, like go one further, but not on the slide, but just add the text. Yeah, thank you. So, so basically, this is showing from the Destination Earth data using the machine learning models like AIFS and other machine learning models as initial conditions, both in the past, in the present, and in the future. And you see this sort of hairy plot, which indicates that when you are in different kind of time regimes, the machine learning models tend to either, going along the path that they have learned, like being in the present climate, even though they're in the past, or being in the future, it still sort of tend to go back to the present climate. That's why you see the hairs going down in the top curve, and then sort of the hairs actually sometimes going up in the bottom curve for some of the models, but not each model behaves the same. And so there are certainly a lot of things and interesting things to be learned, how to combine basically machine learning in the future when we look at the key information that we require, which is information from the past, the present, and the future in these simulations. And with that, I shall stop.
Great. Thank you so much.
So I need to bring up Bjorn's slides because they're in a separate file. Bjorn gets the prize for 8 slides being 1/4 of a gigabyte in size. So Bjorn, welcome. Good morning. I wrote him, I said, it's just 8 slides, right? And he said, yeah, that's what it is. So,
Well, yeah, I only have 10 minutes.
Yes,
Yeah, so I'll just begin. Let me start my timer here so I watch. So first, Kelvin, thanks very much to you and everyone else on the organizing committee, and my apologies that I can't join you in person. I just got back from 2 months in the field. We've been in the Atlantic measuring deep convection with flights every other day, and I had to be back here. Anyway, this slide is for people in the audience who might not be deeply involved in the science, but it just makes the point about the power of technology. So I think a lot of you recognize that. That's 52 years or so ago. That's the blue marble photograph from the Apollo 17 astronauts as they were headed to the moon. And I don't think any other figure shows quite so well how technology can change how humans see their world, how they see themselves in the world, and how they react to that as this figure does. And to celebrate that figure 2 years ago, actually now, and also to celebrate Tim's birthday, we decided to try to simulate it. And that's what's shown here if you click the slide. So we took our coupled model icon and ran it at a kilometer. So it's a kilometer scale grid spacing in the atmosphere and ocean. And that's what comes out when you simulate the blue marble. And it's just a nice illustration of the power of physics to allow you to take very, very, very limited data in 1972, recreate something that looks like what people saw, and to be able to turn around and look where they couldn't see in other places, to put things in motion, to look underneath, to see the height of the evolving ocean, to look at how things like salinity varies due to fresh water from river inflows there in Central Africa, to look at the surface temperatures and the upwelling along the coast and the interaction with the cloud fields, to see the large scale structure of fine scale fronts in the wind field that you see across here, to see how the wind and the atmosphere interact. And all of this is enabled by high performance computing, advanced models, technical capacity, workflows, data. And it really does have the possibility of communicating to people in ways that sometimes I think we underestimate. So if we go to the next slide, at our institute, at least, we've been really focusing on resolution, not because it solves every problem, but because it solves many problems. I would claim that'll probably provoke some people, but it's really the only proven way of making better models. It's the only approach. This sometimes isn't thought about as much, but it's the only approach of the approaches that we're trying to use now that we know how to use hierarchically. So for instance, if we run a 100-member ensemble of a future climate, we struggle to think about how to use that, say, in an aquaplanet and go back and forth. Do we need a 100-member aquaplanet ensemble, and how does that relate to a 100-member, historical climate ensemble? It's not that ensembles aren't useful. It's just that the high resolution kind of fits into our typical way of thinking, and maybe we're lazy and have a hard time getting out of that. It solves the terra incognita or the gray zone problem, because at the scales that we work at, which tend to be below 10 kilometers, we use the same model on all scales. So when we simulated a few tens of meters, which we do sometimes, but not globally, to hundreds of meters over very large areas, to kilometers or tens of kilometers, we can use the same model, and the model just gets better as we go to finer scale, so that it becomes easy to use. The other thing, people show this little graph, which I show there, this ensemble resolution complexity axis. People like to play these off each other and say they're all equally important. And that may be true, but what sometimes is not said is that two of these axes are, increase arithmetically in difficulty, and one increases geometrically resolution. So moving along that resolution axis is really, really hard. And if you can move along that resolution axis, it's really easy to fall back and do the other things very easily. So we run with interactive aerosols, we run with dynamic vegetation, we run with coupled carbon cycles. And those things all become easy once we push on that resolution axis. Again, you just push back and you get a factor of 10 in the number of ensembles that you can run for the same cost. So it makes that easy. And it delivers things that people feel like they can experience, and certainly things that we spend a lot of time trying to observe. So even though it doesn't solve every problem, it does solve many, but it also introduces a few new ones. And those are the main points I want to make in this talk. And if you go forward a slide, the new ones I put 3. I was puzzled a little bit by this idea that Frontier had strong scaling on the whole machine. Maybe that's something that people can talk about. But strong scaling, or this curse of time, the fact we can't parallelize time, even though I think computing systems are large enough to allow kilometer scale coupled modeling now, the throughput is limited, which means that you're using a small part of the machine per simulation, and you're using the folding out the ensemble across the machine. And that makes model improvements difficult because you still have to wait too long for simulations. There's Lewis Carroll's paradox. Sometimes I call that the Borges paradox. This idea, this was another problem, is that you can create immensely fine scales of information, but trying to unfold that map for people becomes hard because of the amount of data that you create. And there's this problem of asymmetric access, in the sense that when we think about climate change and who needs the information, there's this thought that moving to higher resolution actually increases the asymmetries in access, because the few that need it least probably have the most access. So we a year ago, we brought a bunch of people together in Berlin, and we mostly focused on the last 2 problems, Carroll's paradox and asymmetric access. And the first problem is, I think, something this summit is really well positioned to talk about. And so if we go forward a slide, this is, I'd say these are new problems, and they're ones worth solving, but keep going. So this was the Berlin summit. There's about 150 technologists, climate scientists, humanists who came together in Berlin for a week. And we really discussed how can we get around this Carroll's paradox? How can we get around the fact that we're creating, immense amounts of information, but how to make that useful? And how do we deal with this problem of access? And if we go to the next slide, this led to this idea of Earth virtualization engines. And the thought there was not really about just running a big model and delivering data. It was really about how do we use these tools to fill and continually update. And you see this in Destination Earth, a counterfactual landscape with the best possible training data at scale. So you can see really we're seeing this as a way of feeding machine learning. And I think, as we all see from ChatGPT, it's an incredibly efficient way to condense tremendous amounts of information to allow people to interact with it. So machine learning really solved the interaction problem for us. And at the Berlin Summit, we really pivoted in this direction of thinking about how to think of physical models as a way of providing training data, and opening that up to people who wanted to use machine learning to communicate with different stakeholders. We want a counterfactual landscape of futures, but we also want to link this to the past so people can understand and assess whether the futures make sense to them by looking at how well we represent the past and present. That's pretty typical. And doing this in an environment where we give a diversity of users ownership, so they could come to these. If you think about them in the modern lingo, they'd be like AI factories. So having AI factories that allow users to bring their own data, to do their own learning, to deliver the sorts of answers that they're looking for their problems. And the beauty of going upscale is actually it doesn't increase asymmetry, it reduces it. Because if you do something that's bigger than any individual partner, you suddenly create the need for a cooperative environment. And so the question there was, if we do this as a federation of a few to a handful of tiers, centers built around tier 0 computing facilities, it would have to be a cooperative effort. And it would be a natural way to engage other constituencies. So I think here my next slide is probably the last one. Well, that's the sub-last one. This was this idea of Eve as being this sort of neural framework for translating tremendous amounts of information to things which are useful for users. And next slide. So where do things stand now? Eve is happening. We see it in Destination Earth. You saw that nicely in Niels's talk. I'm almost done. I'm at my 10 minutes. But Eve is happening. You see it in Destination Earth. You see elements of it in Earth 2. You see it in these European projects that Niels mentioned. But it's not a coordinated activity and it's not operational. Destination Earth is going the closest in that direction, but doesn't have as natural a link yet to machine learning as we envisioned with the Earth virtualization engines. And it doesn't have this international outside of EU participation, particularly from under-resourced countries. The other thing that's happening, and that's what this summit can address, is that the technology is working against us. If you look at Aurora, I don't know if the conjugate gradient scalings are really true for that machine, but if so, you see the machines are kind of going backwards in terms of the memory bandwidth that is so important for these types of calculations. So how could this summit help? And I think what this summit could really help is dealing with this third point, that the technology is working against us. Next slide. And that the strong scaling is such a challenge. So the second bullet point would be the big one, which would be to develop the technologies that this sort of model needs to run most efficiently and to make their output most salient for users. And I think that's really paired with the ability of machine learning to bring interactivity to the enormous amounts of data or output that these models will create. And maybe the summit could think a little bit about how to do this in a framework that really engages the people who will need the information the most, not just the private industries in the United States, but the meteorological services in places like Senegal or Barbados or Singapore or the hazards community. Perhaps paired with computing facilities in places which can use lots of waste heat. So with that, I'll end. Thanks.
So with that, thank you very much, Niels and beyond. So we now move back to our in-person speaker. So next is move to Asia. So Masaki Sato from Tokyo University.
Okay, I'm Masaki Sato, the University of Tokyo from Japan. So I have some few of the experience of our more than 10 years, kind of 20 years model development with kilometer scale modeling. So yeah, please stop 10 minutes. So I have some materials. I show the recent activity, the 220 meters simulation, and please notice the EarthCare satellite launched in May. So data is soon available from December. So this is our challenge to evaluate our modeling. So we are now proposing a couple of the intercomparison. The 1 year simulation protocol is now open. So I have some ideas. So these are lists. So yeah, our experience, we have started a kind of 2000 model development. Our model development is coordinated with the development of the supercomputer. In Japan, around 2005, simulator is usable. At that time, we ran 3.5 kilometers model, Nikon developed. After that, Riken Kobe, K computer, and Fugaku now is usable. So in Fugaku age, we did a sub-kilometer simulation. Currently in Fugaku, we do 220 meter simulation, and also different type of the simulation for the ensemble and the complexity with a couple model. So and recently international coordinations like Diamond project, and also we are planning the next year Pan Hackathon in May 2025 with coordination with international branches. So the 220 meter simulation, we do more than half of the Fugaku computer resources. So these are computer performance. I'll come back again, the computer performance of Nikama later. But we want to do 200-meter simulation to see how the kilometer scale model is uncertainties kilometer scale model and to use it for the kind of reference. And also there's the experience kind of 100 and 200 meters kind of convergence of the mesoscale updrafts and some properties. So we want to see at least deep convection, some convergence properties in this resolution. So our approach is starting from the 3.5 kilometer simulation. This is Diamond Summer. We started ERA 5 data for 1 week. And starting using this data set, we do a 1.7 and 870 simulation. And using this, we do this kind of resolution dependency. So the high class are not so different from across the model resolution. You may see some finer structure, but the precipitation distribution, kilometer scale model is good to capturing the deep convection, but kind of too strong, we usually say popcorn type convection. But around 2 kilometer and going down scale, we have a more graduation with precipitation process. So yeah, resolution has a better impact on precipitation characteristics. This is 220-meter experiences. And EarthCare, please remember the satellite EarthCare, its successful launch 2024, is first Doppler radar observation from the space. Then this observe the falling speed of clouds, snow. These are parameters used for climate models. So from now on, you cannot use it tuning parameter for snow falling speed. You must refer to the observation. So first image is launched, announced from JAXA and ESA. This is a cross-section of the convection. This is Doppler radar velocity. In rain and snow, we have the observation, this kind of things. So we plan to coordinate the intercomparison of the Earth scale and the kilometer scale model. We had some preliminary simulation. This is the example this June. This is a global precipitation map. And we did two simulations, 3.5 kilometer and 70 meters. So we propose a 2-day simulation. 1 day is spin up, 2 days a comparison. So these are Earth-scale paths. And this two short-term simulation have a capturing the very corresponding synoptic systems and deep convective processes. So we capture this precipitation system in the observation and simulation. So we show the cross-section. So unfortunately, we cannot show the Earth-scale data, but we have very good correspondence to the simulation, 3.5 and 870 meters. This is radar reflectivity, this is Doppler velocity. So kilometer scale model is good for capturing cloud microphysics processes. So we don't think we think kilometer model is good for evaluate using satellite data. This is not so different for 870 meters. And Doppler velocity is the information here. So we have an observation here. So next, we propose this kind of intercomparison. Okay, the last part is we are now proposing Takasuka, Daisuke, 1 year intercomparison. 1 year is an intermediate. Yeah, European group did a 30-year simulation, but it's too much for us. So we propose 1 year simulation. So we have now submit a protocol paper. So please join this intercomparison for this simulation. And also there's a list of intercomparison, like not including a scenario experience for 30 years, but also the CES type warmer climate simulation like this one. So please join the discussion for this kind of intercomparison. Okay, the last part of computational performance. We have a very good weak scaling for this is resolution and this is performance. So for different resolution. from this experience, yeah, Andrea introduced the performance, but this is estimated. In experience, you have this kind of resolution performance. So if we use 1/4 of Fugaku, we can achieve 1 simulation year per day. So it depends on the computer resource we can get. So it's a kind of hypothetical number. So this is the final slide. Thank you very much.
Great, thank you. And now we're going to head back to US efforts, starting with Andreas Prime. A reminder, you can write down your questions and we'll have time for discussion after all the presentations.
Hello again. So we shift a little bit of gears and look at 3 modeling systems in more detail now, which are the MPAS system, developed by NCAR, XShield, GFDL, and then SCREAM, developed by DOE. And jumping right in, just some details on the mesh and the numerics used in this model. So the idea here is really to give you a little bit of an overview, what's similar, what's different, where are the 3 different modeling systems going, and what are the current capabilities. So MPAS uses, and you can see the mesh of MPAS here, an unstructured Baroni mesh, which are basically hexagons mostly. And that's different from XShield and SCREAM, which both use a cube sphere. This cube sphere grid you can best see here. What is common with all 3 models is that they have variable grid capabilities. So you can run high resolution over 1 region. This is, for example, shown here in the SCREAM. So you can go to 800 meters over this region, and then you can relax the grid spacing over the rest of the globe. And this is very often used in this modeling system. So this is something that all of these systems, or many of these newer systems, can do. The numerical, the discretization method, MPAS and XShield use both finite volume approaches, whereas SCREAM uses a spectral element approach similar to CSM, but non-hydrostatic. So this is here the dynamical core is compressible and non-hydrostatic, which means, this is already what Björn said, you can really go down to very high grid spacings. You can resolve updrafts much better, orographic drag, for example, much better with these with these models. Typically, none of these models are running coupled, and I will talk a little bit about this later on. So they all prescribe sea surface temperatures at the moment, but all of them are working towards coupled ocean atmosphere modeling. And the resolution focus is really, like many of those, you can run at coarser scales as well, 25 kilometers, even 100 kilometer grid spacings. But the focus is really on the kilometer scale for all 3 of those. Looking at the model physics, there are also some similarities and differences here. The microphysics, so you can see 3 different approaches used here, but all very similar to what's used in numerical weather forecasting for high resolution models. Very sophisticated microphysics schemes, PBL similarly, so different PBL schemes used here amongst the modeling systems. So again, just seeing how not only the numerics are different, but also the physics are different. So it's sometimes really hard to understand where differences are coming from because you have a large variety of differences here. What's common is the radiation scheme. All of those who use the RRTMG scheme, although I'm almost certain that if you look at the details, those are not identical schemes, but are subversions of this scheme. They all use a shallow convection scheme that's not always used, but the 3 systems are decided to use a shallow convection scheme. The land surface model in XShield and the MPAS is NOAA or NOAA MP. This is coming more from the weather forecasting side of things, whereas SCREAM is using the E3SM land model, which is really more an Earth system land surface model, which has carbon cycle, fire, and other components in it that you really need for long-term integration. MPAS, some additions. MPAS can also be run with other physics, not as many as WRF, if there are any more WRF users in here. WRF has hundreds of options. MPAS has some of these options as well, so you can configure the physics. And XShield is by default run with a mixed layer ocean model. Coming to the ocean modeling, as I already alluded to, all of these 3 modeling centers are working on coupling to the ocean, but none of them are really running with a fully coupled ocean yet. So AMPAS, there's this Earthworks project that was already mentioned, and this is basically using AMPAS within the CSM framework, and it's through this project you will be able to couple AMPAS to the ocean. So this is already working and work in progress, but there's also plans to develop AMPAS standalone ocean coupling, so outside of CSM, of the Community Earth System model. X-Shield already has this coupled, at least slab ocean model, and they use it by default, but work is ongoing to couple X-Shield to the MOM6 model, and they use the FMS coupler. And SCREAM, it's basically a subversion of the E3SM of the Energy Exascale Earth System model, and by default, like this has ocean coupling, so SCREAM basically has the functionality, but it's not really tested well and not really used at the moment, so this is work in progress. They use the CPL7 coupler, so a different coupler again. There's currently work ongoing at 25-kilometer grid spacings to look at the coupling between the atmosphere and ocean and trying to bring this down to kilometer scales in the next step. All three modeling centers really highlighted that it's not simple to do this atmosphere ocean coupling. It's not just connecting the right variables with each other. It's really a lot of fine scale detailed work that has to be going on to do viable ocean atmosphere coupled simulation at this scales. I talked a little bit about this already in my previous talk. These are the systems that the models are typically run on. There are also other systems they run on, but for example, X-Shield, the biggest simulations were done on the Gaia system, NOAA computer. And the AMPAS is at the moment, for example, ran on the Ratio, but on the CPU node. So those are both CPU machines. So they heavily rely on CPUs and they have Fortran code mostly. Whereas SCREAM runs on Frontier, which is the fastest supercomputer that we currently have, a completely GPU machine, and they won the Golden Bell Prize for their simulation, I think 2 years ago now. Just to show you how these different modeling systems look like, Björn had some of these figures already in his talk, but this is coming out from the Diamond phase 2 experiments. So Diamond is a model intercomparison study that intercompares kilometer scale storm resolving models globally. The second phase is a winter case, 40-day long integration with a common framework that the models have to run into. So you can see already from these pictures that the cloud field of these three models are quite different. And it's not, again, not to say one model is better than the other, just to make you aware of these differences. This is already a quite old study by Jude et al. 2021. They looked at the Diamond 1 simulations and looked at tropical cyclones. And he picked out the strongest tropical cyclone of each of these model simulations. And this is the strongest cyclone in AMPAS and X-Shield. There's no observations here, but if you look at those and you're familiar with cyclone wind fields, those look pretty realistic. SCREAM didn't participate in Diamond 1 at this point. But just to highlight, these are other two models that participated in Diamond 1, and you can see quite different wind fields here that are quite unrealistic. The point that I wanted to make here is that increasing the grid spacing alone doesn't solve all problems. You really have to work on the physics and the coupling to the ocean, for example, or at least the pre-described ocean atmosphere interactions to get physical mesoscale structures correctly. Another example is here now going back to the Diamond 2 simulations. I'm involved in a activity where we look at mesoscale convective systems in the tropics. So these are clustered thunderstorms. They're very important for the global energy and water cycle. And here you can see the observations in the top left and SCREAM 1, the version 1, it's a newer version, AMPAS and X-Shield. Again, you can see some differences here. What I wanted to highlight, SCREAM underwent a lot of development to improve the convective organization in the model. So you can see the original simulation here, and here is the SCREAM 1, version 1, and of course it's continuously evolving over time. But you can see, for example, here a lot of patchy convection, which is often referred to popcorn convection, and this simulation looks much better. So again, investing in the physics and understanding of how the mesoscale processes are simulated is really important. Grid spacing alone doesn't solve these things automatically. And this is showing you basically statistics on how the frequency of MCSs are simulated in these simulations in Diamond 2. We use different trackers, so different MCS tracking schemes. You don't have to worry about the details. They're all agreeing on the details. If you look at the multi-model mean, the models are fairly well simulating the frequency of MCSs over land, which is left, and over ocean, which is right. But if you look at single models, for example, the initial scheme that you already saw early on had very little convective organization. So everything was brown. They improved a lot the ocean component here, but there's still biases over land. Now there's too much organization over land, whereas XShield and MPass has the opposite. Land looks really good, but ocean is overestimated, especially in MPass. So just a couple of takeaway messages here. XShield and MPass are working currently towards GPU implementations, whereas XShield can already run on basically any supercomputing system that is out there at the moment. But every modeling center has a different strategy. Like there's no unified strategy how to get to the GPUs or onto GPUs. So you have to really invest in dedicated efforts to look at the physics and to improve the physics in the model. The numerics and the grid spacing is not the only thing we have to worry about. It's really the physics as well. And last but not least, the coupling to the ocean is a major endeavor that all of these modeling systems are currently working on. So this would be, I think, really, and also globally, other modeling centers. So having an exchange and exchanging ideas and experiences there would be really beneficial. Thank you very much.
Thank you very much, Andrea. So now we have two online speakers. Sorry. Oh, yes, sorry. Yeah, we have another speaker here to talk about a neural GCM, Stephen Hoyer from Google. Thank you.
Okay. Hi, everyone. So I'm here to talk about the work that my team at Google has been doing over the past few years on neural GCM. So this is I guess the first of our AI models. So I thought I'd start by giving, I guess, a really quick overview of what's going on in AI for weather forecasting, because it's been very exciting over the past couple of years. So just a few years ago, if you looked at how well we had a few sort of proof of concept AI models for global weather forecasting, and they were quite bad. They're really sort of toy models. And accuracy is sort of a small fraction of sort of the state of the art for physics-based models. This is the ECWS model. And then things really shifted, I guess, towards the end of 2022. There were a few models from Huawei and from Google that sort of hit the accuracy of the best numeric weather prediction models. In terms of like a 3-day forecast here, for example, this is the geopotential height, but kind of across the board, kind of reaching parity. And then over the past couple of years, this has just exploded. And there's now a whole bunch of different AI models that are sort of, by some measures, kind of at parity with numeric weather prediction. And it's been lots of flashy papers. And if you look at talk to like net modeling agencies like ECWF and NOAA, they are really excited about this. This is really clearly going to be a significant part of weather forecasting over the next couple of years. So, well, where does that leave us? Well, I think for the models look sort of skillful in terms of these top line metrics, but it's not entirely there yet. And if you look at most of the forecasts, what you see is that many of the models, for example, they get blurrier in terms of they make forecasts that they're trained to make a deterministic forecast, so they kind of average out, kind of hedge out the weather. None of them are really sort of fully physically consistent yet. Although by many measures they're getting closer. And this, of course, is really important when we get to climate. So the approach that my team has been exploring with neural GCM is a hybrid model. And it's kind of a middle path between the sort of pure AI approaches and more traditional physics-based models. These approaches have different strengths, and kind of at a high level, one thing really appealing about AI models is they're very, in some sense, they're very simple. So they're a lot less code. Like GraphCast is like 5,000 lines of code, and that meant that like it could be built by a pretty small team over a pretty short period of time compared to building traditional models. It's just it's optimized based on these like large data sets like Array 5, which is fantastic. And that means that that the people building these models don't actually have to know that much about the physics, and they can they can miss a lot of that and actually still get really great results. And it's also directly optimized for the forecast accuracy that they care about. So it is possible to optimize these models for like weather forecast accuracy, certainly, and they get really fantastic accuracy for that. On the other hand, for physics-based approaches, these models are much more complex. It's like certainly in terms of lines of code, now we're talking like a million lines of code, as you all know. They are sort of interpretable in principle. If you could actually read the million lines of code, you could understand how every detail works. They're of course based on physical principles, which we expect to generalize. That's, I think, the big challenge for climate, where we don't have data. But my hope and my expectation is that kind of the model's kind of more in like the middle here. It's not really clear what the right modeling approach is, and it may be different for different problems, but we may be able to blend some of the strengths of the physics-based and the machine learning-based approaches. So let me tell you a little bit about what we've done with Neural GCM. So Neural GCM is it's a differentiable hybrid model, and so I'll kind of get into that in a minute what the differentiable part is. But basically, what we did is we decided to rewrite the whole model in the AI modeling framework. So this is a model that it looks at a high level. It looks similar to a traditional general circulation model. We have the physics-based dynamical core, and then we have the parameterizations, the physical parameterizations as well. In our case, we replaced the physical parameterizations with a neural network. But the whole thing we wrote in Python using JAX, which is an AI modeling framework from Google. And so we decided to rewrite that dynamical core as well. And that means is that we were able to optimize through the whole collective system, not just the neural network part in isolation. And that really helped in terms of things like stability and getting good model performance. And so we trained it like these AI weather forecasting models on short weather forecasts, like 3 to 5 day weather forecasts on Array 5. Let me give a really kind of high-level overview of some of the results. So we were able to build models that have very good performance for ensemble weather forecasting. So we were able to slightly better performance than ECWF's ensemble weather forecast, going out to a couple of weeks. And then we also have sort of somewhat like reasonable results for sort of atmosphere-only climate simulation. So this is pretty far from doing everything you can do with a climate model. Of course, we don't model any. We have like it's just the parameterizations are kind of a bit of a black box. There's no carbon dioxide, for example. There's a lot of missing pieces, but in terms of its ability to sort of reproduce the statistics of sort of past observed climate, it tracks with observations much more closely than models than for example, like traditional AMET models. And I wanted to sort of highlight one example of this. So we compared Neural GCM forecasts. This is now sort of going outside of the training period to a 1-year run from the X-Shield model that we were just hearing about. And here, if you look at the sort of the bias for precipitable water over that time period, we had about like 30 to 40% less bias than the X-Shield model. And this is, of course, running much faster. So here we have a model that runs in about, we can do 200 simulated years per day running on like a single TPU chip. That's like something you can rent in the cloud for about $1 an hour, versus like the whole HPC cluster, like 13,000 CPUs. And like a ballpark sort of like cost estimate is like 8 cents a simulated year versus, I may have no idea how much X-Shield costs to run, but like if you rent it in the cloud, that'd be maybe something like $80,000 to do that run. So it's like maybe like 1 million times cheaper potentially. So I think that's potentially pretty exciting. I wanted to also give an example of kind of, this is kind of going beyond the paper, but what we've been looking at sort of more recently, and I think one of the strengths of these sort of differentiable models is that now you can tune your model to handle new types of like sort of new tasks, new observations, for example. So we've been doing this recently for precipitation. We're using, and this is a case where GCMs really struggle to kind of get the right precipitation patterns. So we're, instead of using ERA5, we're using a sort of satellite-derived estimates of precipitation from iMerge. And here we're looking at sort of the patterns of tropical precipitation. So you kind of see on the time scale, sort of like a few month time scale. And the left is, this is the ground truth iMerge. I don't know, maybe you can contemplate, see which of these other models on the right looks closest to the sort of the observed patterns of precipitation. You can make your guess. So I'll show you which is which. So the neural GCM here in the second column, I think is actually looks much closer than most of these. ERA5 looks pretty close, but it gets sort of the intensity wrong, and that's a model that also sort of actually was. That's an analysis. So that's a model that actually saw the state every 12 hours instead of these other sort of atmosphere only simulations. So pretty good ability to get sort of realistic looking like realistic looking weather and climate states when we have that data. So I thought I'd talk a little bit about sort of lessons for climate simulation. Great. And so first, I would say, don't underestimate the power of benchmarks. So what we've seen in AI weather forecasting is we had some benchmarks with Weather Bench. We could measure progress. We could see like how you're approaching this, and that was like a good benchmark really galvanizes the AI community, and they got a lot brought a lot of interest. And I think in most cases, if we can quantify what good means, and that can be very hard sometimes, but if we can do that, then AI can be very competitive, and you'll see a lot of interest from the AI community. And I would love to see that for improving climate models. From my perspective, AI is an accelerator for climate simulation. It's not a replacement. I don't think there's going to be one. There's clearly not going to be like one climate simulation model. It's not like, I don't think we're not going to see AI replacing all of traditional climate simulation. I think in the bull case, we'll see AI is useful as a component of climate simulations. And the places where we have lots of data, we can speed things up. We can get higher accuracy. In the cases where we don't have the data, we can still use physical models. And that's again, like sort of the hybrid approach we showed with neural GCM. And finally, I would say that the other sort of thing we showed here is that it is possible to rewrite a climate model in Python that actually offers a lot of benefits sort of beyond just AI. Things like we have like automatic differentiation support, so you can sort of optimize through the model. That's useful for data simulation, for example. It automatically runs on accelerators. It's easy parallelization, sort of modern code. A lot more people know Python than Fortran. So I think that's also potentially something useful to think about.
Great, thanks, Stefan. Our next speaker is from NVIDIA, Karthik Kashna. And Karthik is online.
Hi, can you hear me okay?
Yes, we can hear you.
Great, thanks. Thanks for the invitation, and glad to be here. Unfortunately, I couldn't join in person, but I'll tell you a little bit about Earth-2 and briefly touch upon some of the aspects of accelerating AI for weather, but pivot to some new technologies that we're developing on generative AI. So I'm Karthik. I'm a principal engineer and scientist at NVIDIA and AI HPC. And let's dive right in. Next slide, please. So I'll just set the stage for what Earth-2 is. Bjorn already mentioned it briefly, and a few others might have already heard about it. Maybe spend a couple of minutes on emulation at 25-kilometer scale. Stefan already described some of the great achievements in the last few years. I just want to mention one of the aspects of what the speed enables, and finally move on to some exciting areas in generative AI for weather and climate at the kilometer scale. Next slide, please. So very briefly, this is sort of a one-slide introduction to Earth-2. It's an NVIDIA initiative to build a climate information system, and not necessarily using it for just climate prediction, but all the components that are required to enable climate science and climate tech. There's three pillars to Earth-2, simulation, of course, physics-based numerical models, AI and visualization. I'll talk more about the AI, and Peter Messmer, who's also at the meeting, tell you a lot more about the simulation and the viz. Next slide, please. So this is probably evident to everyone in the room, but there's this sort of triple bind for realistic climate information systems that we're faced with. One is, of course, resolution that we've talked about a lot. The second is the trade-off between ensemble sizes and resolution, given a fixed compute budget. And the third, which I think hasn't been talked about as much, is that these kilometer scale simulations produce humongous volumes of data. Bjorn had this nice quote at one of our GTC conferences here, where he said, we can compute these kilometer scale trajectories today, but we can't effectively extract the information from it. One of these simulations for a 300-year trajectory produces about an exabyte of data. So we need ways to be able to interact with that data. Otherwise, that information is not very useful. So this is sort of the setting. And the next slide, please. So Jensen Huang, our CEO, is very excited about the opportunities here for the technological breakthroughs and challenges. And he was at the Berlin summit that Bjorn talked about earlier today for Earth virtualization engines. And he gave a keynote where he described these three miracles that the community needs to achieve. And it's sort of our mandate for Earth-2. The first is to enable kilometer scale simulations on large machines, targeting a throughput of about 30,000 simulated years per year within a 30 megawatt budget. And that's to generate high fidelity data energy efficiently. I won't talk much about that. The second miracle is, given all of that data, create AI models or systems that can emulate that full state vector for any region, any time period, past, present, and future. And the goal there is to enable this interactivity with the exabytes of information that's out there to be able to put that information on people's fingertips. And then finally, the third is visualizing that entire state vector from the cloud for anyone, anywhere to enable climate action. So that's sort of our mandate, and I'll focus more on the second miracle. Next slide, please. So I'm sure you've heard about ForecastNet, and there's a dozen other AI models. So I won't spend too much time on this, but there's these models out there that are full atmosphere emulators. They emulate the entire system in a single shot. They're fully data-driven. Our model, ForecastNet, is driven using Fourier neural operators. You can train it on multiple resolutions at different time steps. Without spending too much time, the real highlight here is that these models are at least 1,000 times faster than numerical models and 3,000 times more energy efficient. And they've also been extended to be able to predict at much longer timescales, coupled with the ocean, et cetera, to create climate emulators with folks like AI2 and UW. So there's very exciting opportunities here. They're highly scalable models, and I just want to mention one aspect about that on the next slide. So this is essentially doing spectral transforms and pointwise operations, so not that dissimilar to a classical spectral solver. So properties that are relevant to scaling out spectral physics-based models are also relevant to these types of architectures. And I think that's pretty much all I want to say on this and move on. Next slide, please. So what the speed enables, and Stefan mentioned that AI can be used as an accelerator, is that you can now create these humongous ensembles. And this is some work that we're doing with Lawrence Berkeley Lab, Bill Collins and his team there. And they've generated these 10,000 member ensembles, 7,400 to be precise, to be able to study these low likelihood, high impact extreme events like the 2021 Pacific Northwest heat wave. And Ankur, who's shown there, the grad student working on this, has also developed some very nice calibration techniques to calibrate these massive ensembles. And it turns out that once calibrated, you can actually use it for studying these very extreme tail events and capture things that are just impossible with smaller ensembles. So I think this is an exciting opportunity for these AI accelerated models to be able to study extremes that would be impossible to study using other techniques. Moving on, next slide, please. So let's come back to the second miracle that Jensen laid out about a year ago, which is to synthesize kilometer scale detail. So a lot of the focus of this meeting is around the next generation of simulations, kilometer scale, and maybe even sub-kilometer. So how do we get to that scale using AI models? And the goal again is to enable interactivity with large volumes of data. Next slide, please. So one aspect that we looked at before we got to generative AI is what if we tried to scale ForecastNet out to kilometer scale? And it turns out that that's extremely challenging for a few different reasons. First of all, this is common knowledge in the LLM community, but you need to scale the model size and the data equally, and these are scaling laws that are coming out of studies on transformers, and we don't quite have the data to scale out to kilometer scale. That's one serious challenge. The second is this is also something that we're finding in the last couple of years is that you can increase the spatial resolution of the training data, but it doesn't get you very far if you don't have fine time steps because of this ensemble averaging that Stefan mentioned. Sorry, can we stay on that slide? Thanks. So the error accumulates without a regressive rollout, which means you can't have very fine time steps because then you're not going to have a long range prediction. But at the same time, if you have large time steps, you just blur out the forecast. And then finally, our estimates, our projections for scaling out these models on kilometer scale data like the SFNO, the ForecastNet model, is that we need at least about 12,000 hoppers to do that. So that's quite a hard challenge. So let's see if there are other techniques. Next slide, please. I'm sure you've seen this. It's all over the news. But modern generative AI is highly flexible and also produces extremely high fidelity, including on images and videos. The sort of workhorse behind these models, like the OpenAI Sora model, is diffusion models. And if you play that video, I think you might need to click on the image there. Thank you. You can see that this is completely AI generated, and it's stunning how realistic these AI generated diffusion videos are. And the question we're trying to ask is, can diffusion models learn the high resolution details of Earth's weather and climate too? Next slide, please. So our first step in that direction is this model called Comparative that we've developed over the last year or so. It's a generative diffusion model that leverages ideas from fluid dynamics that are 100 years old, decomposing the flow into a mean and a fluctuation and trying to learn the fluctuations using a stochastic model like diffusion models. I won't get into the details of the architecture, but we've essentially used it for downscaling, so super resolution, on a limited domain over the region of Taiwan with data from the Taiwanese Weather Bureau. And it turns out that we can synthesize new channels as well. So this is a purely generative task, is synthesizing channels that don't exist in the inputs, but also increasing the resolution by a factor of 12.5 in each spatial dimension. So that's quite a large super resolution ratio. Next slide, please. And this is a video, so if you click on that. On the outside of this box is ERA 5, and on the inside is the super resolution model results. And you can see that kilometer scale fidelity and detail that the model produces using the inputs that are coming at 25 kilometer resolution. So this is quite impressive, given that we've only worked on this for about a year, and these are models that are pretty much out there in the visual domain, and we're just adapting it for applications in weather and climate. So I think there's great opportunities here. Next slide, please. So we think that there's a few different ways we can scale this out to global scale. One idea is to couple that with these global emulators at 25 kilometer resolution, like the ones that were just talked about, ForecastNet, GraphCast, Pangu, many others. And then use downscaling on top of that to be able to get to kilometer scale at many different regions. Of course, the key is that we need training data for these different regions, and ideally training data for the entire globe. But the benefits of doing this sort of thing is that you can generate these 1,000-member ensembles in minutes, and you can generate much larger ensembles if you like, because you're just sampling from a distribution. There's about 200x data compression in the spatial dimension, and coupled with the temporal compression that you can get from these global emulators, we're talking upwards of 10 to the 4 compression ratios, which then starts to make an exabyte of data much more feasible to work with. They're thousands of times faster and more energy efficient than numerical simulations, and could be adapted for climate prediction by conditioning on high fidelity regional climate data. And this is something that we'd like to do in the future. So next slide, please. So I want to close with this image that Bjorn already showed. I think the key here is high fidelity, high quality kilometer scale training data sets to be able to then compress them into these generative models that can be used for interactive exploration, science, and also climate action. Thank you.
Great. Thanks, Karthik. Our next speaker is from Google, Matthew Wilson.
Hi there. Can you hear me okay?
Yes, we can hear you.
Brilliant. Okay, well, thanks. That was a really interesting talk. And I'll be also talking about diffusion models, which is a nice connection. So this is just going to be a quick introduction to GenCast, which is our diffusion-based ensemble forecasting model for medium range weather. Next slide, please. I think I'll skip this one, actually. So yeah, I've had to squeeze this into 10 minutes. I may have to skip a few slides. So yeah, this is work with a bunch of great people at Google DeepMind, shown here, and you can find the research on the archive. Next slide, please. So I'm sure diffusion models hopefully won't need too much of an introduction, but yeah, they are, as we've seen, they're driving a lot of the wider advances in generative AI. We saw this cool storm in a teacup, and we've now got, you know, image generation models. So I guess the idea is that diffusion models are great at drawing samples from high dimensional conditional distributions. So we might sample images conditional on a text prompt, or in the case of GenCast, we might sample a next weather state conditional on 2 previous weather states. And the way these diffusion models work is they start from some random noise and they iteratively transform that noise into a sample. Next slide, please. I think I'll skip this one and the next one just in the interest of time. So GenCast, yeah, it's a diffusion model. It operates at 0.25 degree latitude longitude resolution globally. We predict 6 atmospheric variables with 13 vertical levels and 6 surface variables. We produce 15-day forecasts. At least that was our focus. We can actually go for longer, but 15-day was what we mainly verified. With a 12-hour time step, and each time step in this model is stochastic because it's a diffusion model, and it takes about 8 TPU minutes per ensemble member, which is a little more expensive than some of the deterministic machine learning weather prediction models, but still perfectly usable. Next slide, please. Sorry, can I get the next slide? Thanks. Oh, I think we skipped 2 slides. Perhaps we could go back one. So, sorry, yeah. So I give it. Oh, yeah, this one. Thanks. So I'll give a few quick details about the architecture. There's lots more details in the paper, so I'll try not to spend too long on this. But it is based on graph neural networks and sparse transformers. It's a similar architecture to GraphCast, if any of you are familiar with that paper. So yeah, we have data on sort of weather variables on a latitude longitude grid are encoded with a graph neural network onto a latent icosahedral mesh. Then we have a sparse transformer on that mesh, which at each sort of attention layer attends to a k-hop neighborhood on the icosahedral mesh. And after some rounds of this sparse transformer, we then decode back the weather variables back onto the latitude longitude grid. It's trained on error 5. We pre-train at 1 degree and then fine-tune at 1/4 degree. We just train it on a single time step, which works surprisingly well when you then roll it out. Unlike GraphCast, we don't really need multi-step training to get this working. We follow the EDM framework, which is a sort of a nice framework from NVIDIA for diffusion models. With a few little differences, like we sample isotropic white noise on the sphere rather than pixel noise on the grid. And we use this DPM solver plus 2M, which is a slight mouthful, as our solver. And we use 20 steps of that solver, which means 39 function evaluations per time step, as opposed to just 1 function evaluation that you need for like a deterministic ML weather prediction model. Yeah, next slide, please. And so when we look at rollouts from this model, we see a lot more realism than we get from GraphCast. So GraphCast, if you to look at a similar rollout from GraphCast, you'd see it would start to blur, whereas this is specific humidity at 700 hectopascals, and you can see a lot of detail in there. And this is rolled out over 15 days, and that detail is kind of maintained throughout. Next slide, please. But it doesn't just look nice, it also is skillful. And so this is comparing the skill of GenCast relative to ENS, which is the ECMWF's state-of-the-art kind of numerical weather prediction ensemble. And blue here on this scorecard means that GenCast is doing better. Red means ENS is doing better. And yeah, we can see we're better almost everywhere, with the exception of kind of higher in the atmosphere at short lead times. Next slide, please. I think, yeah, in the interest of time, I'll skip this as well, actually. We have some evidence that diffusion is helping over if you take a deterministic model with perturbed initial conditions, you can also do somewhat well, but diffusion does better than this. Yeah, next slide, please. We also looked at the calibration of our predictive uncertainty, and this can be quantitative. So this is sort of, if you say it's going to rain 30% of the time, does it actually rain 30% of the time that you say that? These sort of questions about calibration. For this kind of forecast, one indicator of calibration is the spread skill score, which we aim for a spread skill of 1, but less than 1, it indicates that your predictions are slightly maybe under dispersed or overconfident, and if it's greater than 1, it indicates your predictions may be over dispersed or underconfident. And we can see that GenCast in blue here is pretty close to 1 across lead times up to 15 days. Similar sort of level of calibration to ENS, but if we take a similar model with perturbed initial, like a deterministic model with perturbed initial conditions, we find that it just doesn't do as well in terms of calibration. Yeah, next slide, please. We also see that the diffusion models kind of help with this problem of blurring. And here, this example shows forecasts for the same validity time. The kind of ground truth is shown on the left, and we've got 3 samples from GenCast forecast from 1 day out, and 3 samples from GenCast forecast from 15 days out on the bottom row. And then we also have a sample from GenCast perturbed, which is a kind of an equivalent deterministic model with perturbed initial conditions. And because the deterministic model is trained with a mean squared error loss, it blurs a little bit. And you can see that in the power spectrum. The power sort of drops off at high frequencies. Whereas GenCast, you can see the detail in the forecasts, and the power spectrum matches that of its training data quite well. There's a little kind of uptick in noise. It's a very tiny amount of noise at very high frequencies is the only sort of exception to that, but it replicates the power spectrum quite well. We see similar things across a range of other variables too. Next slide, please. So we also looked at how well GenCast does at modeling extremes. So I don't have time to explain relative economic value too much detail here, but it's essentially a metric of, you know, what's the value to forecasters in actually making decisions based on a forecast about an extreme event. And this depends on the kind of cost-loss trade-off of that decision problem. So here we're looking at decisions around, like, is there going to be a kind of a once-in-7-year heat wave, or like a once-in-7-year extreme wind event? And we find that across a range of cost-loss ratios and across a range of lead times, our forecast has more value than ENS. Next slide, please. So we also applied GenCast to some downstream tasks. So one of these was predicting a kind of a simplified proxy for regional wind power. So the kind of total wind power that could be obtained from kind of wind farms within a given region or pooling region. And this is an interesting task, because to get this right, you really need to model not just a probability distribution for wind at each separate location. You need to get the correlation structure right to some degree between the wind farms at different locations. And we find that, in probabilistic predictions of this regional wind power quantity, we do better than ENS. We also applied GenCast to cyclone tracking, and we find that we do better not only on the error of the ensemble mean track, but also on this kind of probabilistic cyclone forecasting task where you're trying to predict the probability that a cyclone will strike within a given radius of a particular place. Next slide, please. So one last thing that we tried, this is still a bit preliminary, this line of research, but we also tried longer rollouts. So we were interested in, GenCast was mainly designed to roll out up to 15 days for medium range forecasts, but we found that we can roll it out for longer. Next slide, please. Up to about 100 days at least. Beyond 100 days, it maybe starts to drift a bit, but 100 days, it maintains quite good stability. And so here, for example, are 3 different forecasts initialized at 3 different points within 2019, each 100 days. And we're looking at the global average temperature in that forecast. Next slide, please. And if we combine 36 of these rollouts initialized at different times, we can see that we're replicating the global average temperature cycle pretty well over the year. So it seems like, we're stable and we're getting things like this right. Next slide, please. And you can see that this is a good match for observations in that year as well. So there's more work to be done here, but we think there's potential to use these models for kind of seasonal to sub-seasonal forecasting as well. And, potentially for them to be useful in some climate applications in the future, although there's a lot more questions there over generalization and all sorts of issues around this. But yeah. Next slide, please. Yeah, so challenges and further work. So yeah, making this cheaper, like I said, it's more expensive because it's a diffusion model and you have to go through these multiple steps in order to generate a sample. It is more expensive than a deterministic equivalent model. I mean, we'd like to make this cheaper. There are a lot of papers out there doing this with distillation and other techniques. We think that's going to be a solvable problem. It's just not one we've got around to yet. Larger ensembles. So for weather, it seems like 50 to 100 ensemble members may be enough for most kind of decision making around weather. But once you get more into kind of climate and into kind of extreme events and how often they're likely to occur over a long period, larger ensembles are definitely going to be interesting. And this is something, as the previous talk mentioned, that ML models enable because they are cheaper than the traditional models. And kind of also related to that, and related to these questions around climate and around, or at least sort of seasonal to sub-seasonal forecasting are, longer rollouts, really verifying how well these longer rollouts are doing, really tuning the model's behavior to get these longer rollouts right and to tune it for that kind of sub-seasonal forecasting task. One could look at things like coupling with an ocean model, for example, as well. We do have sea surface temperature in this model, so coupling it with an ocean model is something that could be interesting. And then just a kind of a general line of research that I think increasingly people are looking at in ML weather forecasting is using machine learning for the data assimilation part as well as the forecasting part. So this model, it relies on numerical weather prediction to give it the initial conditions, but using ML to infer those initial conditions seems to be where this is going in the longer term. And one interesting thing with diffusion models is sampling from the diffusion model can be constrained using observation operators. So that could be one way to do data assimilation. There's some nice papers out there sort of proving out this approach. And another way could be just directly conditioning on observations. But yeah, this is definitely an interesting line for future work, I think. Thanks.
Great, thanks, Matthew. And we'll go ahead and open it up for discussion now. If the in-person speakers could please come up to the stage. So we've got Andy already on stage, Masaki and Stefan. And we have a few mics on the floor. If you have any questions, please feel free to line up on the mics. And we'll also be fielding any questions from online here at the stage. Great, thank you. And I see we have someone already at a mic. Michael? It's not on? It, yeah. It's size for people my height right now. I wanna.
So my question is for Andy. You showed an interesting picture of the strongest tropical cyclone in a couple of the models. The strongest observed tropical cyclone is Hurricane Patricia with winds of 214 miles an hour. That's one of the 5 hypothetical category 6 storms that we identified. I looked it up, the wind pattern looks a lot like what you just showed. So my question is, do you know what the lifetime maximum wind speed was in those simulations?
Oh, I don't know. Maybe that's in the paper, but this is also only a 40-day long integration. So you have maybe, I don't know, 20 cyclones in those model simulations. So I wouldn't expect that you get really the most extreme cyclones, but to get a quite extreme cyclone out of these models. And like, I think XShield and AMPAS did pretty well because they're used for forecasting cyclones all the time, hurricanes. So they are very well built or tested to do this job very well. You saw really with other modeling systems that were not coming out of the numerical weather forecasting realm that they struggled. Like Arpege, for example, like they never really ran on this scales, I guess. So the SAM model was the one that didn't have a cyclone at all. Like there you really have to invest in basically in the physics to generate these intense cyclones that you see.
Certainly,
So Andy,
pictures you showed were very encouraging.
that was Bjorn. So
yeah.
for the, sorry, but the Arpege model is an interesting story there because the Arpege model wasn't getting good tropical cyclones at their standard resolution. So as a fix, what they did was they increased latent heat fluxes just artificially by multiplying them by 1.2. And they forgot to take that fix out when they ran the diamond simulations. And so they had these wickedly stronger storms as they went to higher resolution, but that was because they inherited a low resolution fix.
Thank you, Bjorn.
I'm really curious. I'm actually on the next panel as a stakeholder, so this is all relatively new data and ideas to me. But what I'm seeing is sort of like you're comparing these models almost competitively, and I'm just kind of curious if I'm getting that correctly, or are you thinking more about how this should be shifted into a collaboration model so that we, can actually move things forward? I'm just kind of curious. Excuse me if I'm reading it right or if I'm seeing it incorrectly. Help me understand how this is collaborative.
The AI modelers, I think we're kind of the worst at this. And the AI community, I think, is the dynamic there is that like people put up benchmarks and everyone sort of competes to do the best in the benchmark, and that's kind of how you show that you did something novel and important. And so we have sometimes kind of gotten that. I guess I'd like to say like I think there are clearly most of these comparisons are not apples to oranges entirely, and like I think most of us actually would very much like to. We're kind of trying to show like the AI can offer something, but we'd like to figure out going forward how to do certainly how to collaborate.
Like maybe just a quick comment. Like model diversity is something that we really value, because different models give you different answers. Like if you look at this CMIP projections, having an ensemble of models is really valuable. If you only have one modeling system, you definitely underestimate the uncertainties. So having models that have different basic designs, different approaches to tackle like the numerics or the physics or AI-based models, like this is really valuable. So I wouldn't say you want to have a physically based model that looks realistic, but having a diversity of models is certainly important.
Question for the ML community here. So it seems like one of the promises of ML-based models is ultimately they're so fast and so easy that they can democratize weather and climate modeling by basically allowing people potentially to run them themselves. Is this a reasonable expectation, and anyone trying to build user interfaces would actually make this possible.
That's a great question. We'll open it up online as well. Feel free to unmute. And Bjorn, I don't know if you have anything to add from Eve.
Oh, that was hard to hear. That the audience, could you just repeat it?
Okay, so the question was just from the point of view of ML-based climate models, the idea is that they're potentially fast and simple enough that they can democratize climate modeling by bringing these models closer to the communities, which ultimately want to see the results. And I guess the question was, is anyone building user interfaces that are going to make this more possible?
Yeah, I would just add that was, I think if there was one point about Eve, I would pick that one, was this idea that we need to create places where people can use these technologies. So laying out the data, filling the space of counterfactual, so people could come and train their own weather models, train their own climate applications, train their own hydrological models, blending their data with the best we could offer from a science framework. And so that's what we talked about, these AI factories. But Destiny comes closest, but they don't really create a space for, some small country to come and develop their own tools or this democratization that you're talking about. So if I understood you correctly, the answer is no.
Yeah, Karthik, did you have anything to add? So I recall a few years ago, David Hall gave a presentation on efforts that were ongoing at NVIDIA, and something was raised regarding anyone being able to run a weather or climate model. And I think there was a mention of a visualization tool or something of sorts. Is that still ongoing or?
It is, yeah, thanks. Yeah, so maybe just echoing what you just said and also what I started to say at the beginning. There's sort of three pillars that we're trying to develop with Earth-2, and one of them is for developing AI models on existing data sets. Peter Messmer, I think, is at the meeting, and his team is developing the data federation engine, which brings together various data sources, and that connects to something called Modulus, which is an open source machine learning platform for developing these machine learning models, including things like ForecastNet and GraphCast. There's a few that are already on there, and users are welcome to develop their own as well. So that's the intention, is to be able to have this playground of various different AI models that people can develop and have this data federation engine pipe in data from many different sources, and eventually also be able to plug that into the visualization engine that, again, Peter's team is developing to visualize that. So bringing all three components together. I'm sure, I think that was Chris that asked that question. So I'd recommend having a chat with Peter Messmer, and he'll tell you more about where that's at.
Great, thank you. I see a hands up from Tim Palmer. Would you like to unmute yourself?
Yeah, thank you. Just like to make a couple of comments about AI and NWP. The first is the kind of comparison. There's always, I think it's a little bit difficult to know whether you should be comparing the AI scores with the kind of raw, if you like, ensemble output, or some, if you like, bias corrected or post-processed output. So there are some quite sophisticated algorithms now for post-processing the output to fit better to observations. And I mean, given that the AI is trained already on these observations, it might be a fairer comparison to do the latter. But the real point I wanted to make was that I hope in the future going forward, we will try to produce kind of hybrid systems which combine both the physics-based models and the AI for numerical weather prediction. And I say that for three reasons. One is that, I mean, if we take it that for sort of longer term climate change, we're going to continue to need physics-based models, I think it's important to recognize that NWP is actually these days quite an important tool in producing climate models. The Met Office, for example, will use NWP to either select or reject parameter values and parameterization schemes that they'll subsequently use in the climate model. So this is under the sort of general theme of seamless prediction. So in the sense that we want a strong linkage between weather forecasting and climate forecasting, I think it's important to keep the physics-based models within the weather prediction service, weather prediction capability. The second reason that I wanted to say was about doing counterfactual experiments. I think, physics-based models, if you want to know what the world would look like or what the atmospheric circulations would look like if Greenland didn't exist, for example, you can very easily do that in a physics-based model, and that gives you understanding of what, of how topography and various things affect the circulation. And of course, that's almost impossible to do in an AI type system. And just finally, the paper by Tobias Seltz and George Craig last year showed that one has to be a little bit careful about statements that you sometimes read that, the AI has somehow learned the equations of motion. And what they did was to ask whether these, in fact, I think it was Pangu, whether can emulate the butterfly effect. And by the butterfly effect, they meant by reducing taking an analysis error and reducing it in amplitude. And they showed that the NWP models correctly captured the growth of those small perturbations, but the AI system wasn't able to, because basically it didn't know about the dynamics of such small perturbations, the fact they were convectively driven rather than, if you like, baroclinically driven. So I just wanted to make this point that I think there are good reasons why going forward, we should try to make the best of both worlds and not just one or the other.
All right, thank you very much. I think with this comment, I don't know whether there are other questions or maybe further thoughts on the comment that Tim made. I think we have maybe like just 1 or 2 minutes left. Okay, maybe just last one.
Yeah, I've just been listening to this. Two things have struck me so far. So I think that last comment about the AI efforts do not learn physics. They learn how to infer physics, which is different. We have to be clear about that and understand that. I think most people do, but it is an important distinction. The future that has this very clear possibility of combining both AI and explicit solutions, physics solutions, in order to provide us with the predictions that we're looking for, does put a strain on the resources used to do the computation. Because I think as we are seeing, at least I am seeing, and I think some of my colleagues, certainly in the computational side, are seeing, there's a bit of a bifurcation going on in the hardware that's being used for the different types of computations, especially in terms of precision. And I get concerned about specialization because it removes flexibility. So finding a path that has the combination of the specialization that's required for good, efficient performance without sacrificing too much of the flexibility seems pretty critical need for what we're talking about here. So,
Go ahead.
Yeah, I just wanted to reply to the comment from Tim. I think the last statement about the butterfly effect, and it's certainly true. And but I do want to point out that also how we formulate the ensembles right from the initial conditions is really important even for AI. So that work by Bill Collins that Karthik featured, they ensured that they created that initial steps in a certain way that was in alignment with operational protocols. And so again, ensuring that we're formulating our AI systems to simulate what we want and want to capture, whether that is a calibrated spread of ensemble members out to some future state is also really important. And just quickly to reply to Chris Brotherton's earlier question about democratization of these tools. I don't know about efforts for other countries, but I'll mention at least from an education standpoint, it has enabled students to be able to run some of these models. So at least from that standpoint, we're seeing some advancement there where students can now take up these tools, download them and create their own experiments.
Mm-hmm. Absolutely. Well, a fantastic session. I think very provocative, which is exactly what we wanted, raised a lot of important questions. We're now going to segue into lunch, which is in box form, and we'll bring it back in here. We do have a working lunch, but we're going to give you a chance to catch your breath a little bit, a half an hour or so, before we get into the next session, which is a stakeholder session. And we're going to hear from stakeholders who are addressing, the use of climate change information. Kind of looking ahead this afternoon, we also have a brainstorming session after that, and then an hour session that will be led by Dan Reed and Maria Molina, where we're going to be talking about some of the questions you submitted electronically and kind of recapping some of the challenges that we've heard, and not at all trying to get to the breakout topics yet, but step by step we will do that. We do have an interesting opportunity right at the end of lunch, which will end at 2:00, to walk outside a very short distance from here and have a drone take a group picture. So we think it's important to capture that. I thought Bjorn did a fabulous job of that at the Berlin Eve Summit. And I think it'd be really good for us to do that here, because I know some folks are going to have to leave tomorrow or on Wednesday. So, with a few minutes left for lunch, maybe about by 11 or 1:50 or so, we'll run out the door just around the corner here and have the drone take our picture. So they'll be ready for that. So any other questions or comments?
Just want to thank all the speakers
Yes.
in our panel.
Yeah,
Thank you.
let's thank them again. So feel free to go outside. I think it's just to the right as you walk out, grab your lunch and bring it back, and restroom break time or whatever, and try to be back here by about 12:30 or so is when we'd like to start the presentations for the practitioner panel. And at that time, I'd like the panelists, 12:30, when you come in, go ahead and come up to the table, if you will. Good job. Fantastic job. Excellent job. Thank you. Yeah, it's gonna be very challenging.
It was a good session.
Also,
the main problem is it's impossible to train. Okay, because basically in order to train these models, basically you've thought about this, you have to run effectively, it's equivalent of we do millions of 3-day weather forecasts. The total amount, it's many thousands of years to get climate simulation. So it's not the model's about the same speed. It's in terms of the runtime, it's basically the problem is to make so many forecasts to figure out a different way. So maybe I'm not sure. It might be maybe a variable resolution scan, maybe you try to transfer parameters from a first model to a minor model. Well, no, okay, so it's different to train. I think you could definitely train all the time. That would be an interesting thing to do. I'm not sure if that would make, if you trained a regional model, typically, the question is if you trained a better regional model, would that, an AI regional model, would that also work with as well? Maybe, I'm not sure. I think that's yeah, maybe. Yeah, I think regionally, I think nobody has done that yet, but I think really very well yet. I think that's a pretty good opportunity. I mean, one challenge there is the regional is that, like, in some sense, because we need the global model, it's better constrained by the data. So we can train a model that's better than this in the US. We'd like to verify. That's not going to be much harder than regionally. There's less. Hybrid. Well, in our model was hybrid. We have a dynamic before. We build dynamic spectral dynamic approach. And then we have the parameterization that is connected to well, we sort of put in our model, we actually put we kind of put the AI and the GCM together. So we had to rewrite the GCM and we wrote the we only have the dynamics. And I was really interested to hear about your model as well. Sure. Let me slow you down. And also it's kind of like an 1980 era, you know, like this. Yeah. Thanks, nice talk.
Complex.
Yeah, good to meet you too, man. Thanks for coming. Of
course.
Yeah, feel free. I think.
Sorry about some of the logistical issues earlier.
No problem at all. No problem at all. So Jean and Edith, if you go ahead and come to the front. Go ahead. Jeff.
Just get started.
Okay, hello, everybody. So now we're going to begin the practitioner stakeholder panel session. And we will begin with Jeff Gao from Renaissance Ray Risk Science.
All right, great. Nice to connect with everyone. So again, trying to give sort of a user, consumer's perspective to all the discussion that's going on over the next few days. So just one gratuitous slide about Renaissance Re Risk Sciences. I know it's a mouthful, but we're a team of scientists that support Renaissance Re, a large global reinsurance company. We're north of 20 people now, and we have expertise in various fields of the geosciences, including things like atmospheric science, which is my background, oceanography, hydrology, engineering, data science. And in a nutshell, our job is to quantify risk, and specifically natural catastrophe risk. And how do we do that? We do that through our internal view of risk. We call the Renaissance Review of Risk. In certain cases, we'll build our own internal models. Other times, there's commercial models available for use that we can license. We don't want to just blindly use those models. We want to make sure we've properly kind of kicked the tires, so to speak. So we do evaluation efforts around those commercially available models. We advise our underwriters. Those are our key customers, if you will, that we support within the company. So view of risk, first and foremost. A few of our other functions include client and investor engagement and things like this as they come up. And then we also have a forecasting service as well. So we've been quite busy with a lot of the activity that's been going on in the tropics the last few weeks. Okay, so why the interest in a global Earth system model? I think from our perspective, the holy grail, if you can call it that, would be a global all-weather peril simulation set. And I have a slide that will go into that in a little bit more detail. But in our view, we would have all of the peril region correlations explicitly set for us by virtue of doing this global all-weather peril simulation. We're modeling the physics. So again, in our view, we'd have scientifically sound stochastic event sets that we could derive from these simulations. And then there's also the opportunity to close the insurance gap. One of the big drivers of insurance gap today is just we don't have a lot of the foundational knowledge that we need in some of these countries where you just don't have great data. So the idea of being able to produce global data to quantify risk is really intriguing to us from an insurance gap perspective. Other potential use cases include tools to help quantify the impact of climate change, inter and intra-seasonal forecasting, and then also real-time event response. All right, so first on peril region correlation, within the reinsurance industry, this is a really important topic. It's an important driver of how we build our portfolio internally. And those assumptions, if different perils are correlated or anti-correlated or independent, right? Knowledge of those relationships are important, and that ultimately feeds into things like capital. And again, I don't want to go into that, but the correlations between peril regions is really important within the industry. And, you know, how the global Earth system model has been represented is that this could be a potential solution to help set those peril region correlations. So for a given year, just to put some more context around that, we could have a Japan typhoon, a South Africa winter storm, a Europe heavy rain event, and a US hail event. All these events would be explicitly simulated and represented within the outputs of the GES model. Just some things to think about. We care a lot about number of years of simulation. 10,000 years, right? You know, that's what we'd be looking for to have a 10,000 year simulation. Maybe could make some sacrifices in terms of resolution, right? But number of simulations is a really important variable. And there's definitely a limit to what we would need in order to make it practical to work with. Yeah, and so even if there's subtle correlations, right, that matters, and you know we think we need that sort of time scale to help resolve and set what those relationships are. So that was peril region correlation. Sort of the next food for thought item is what I call scientifically sound event set. I tried to summarize here what sort of the current approach is within the industry, how with the CAP models that we have available us today from the commercial vendors, you know, what's the approach that they take? I'm not going to go through sort of the approach with each of these perils separately, but maybe if we can just focus in on extratropical cyclone. I think that's representative for the other two perils as well. So the current approach within the industry is to use GCMs to generate the large scale storm environments. And then those GCM outputs are used to initialize and set the boundary conditions for higher resolution mesoscale models, like a WRF model, for example. And how the GES model's been represented to us is, you know, this could remove the need for separate GCM and mesoscale model runs. The resolution of GES is high enough such that we're able to count actual storms, actual events. This concept of being able to directly count events is a critical one, you know, all the way down to severe convective storm. So we could track events, process the event outputs, footprints. When I say footprint, that's sort of the boundary of the event. So if you think about a hurricane, right, it's the extent of damaging winds. For flood, it's the extent of water depth. And maybe there's a possibility to also couple to ocean models for storm surge as an example. And so for extratropical cyclone, the improvement here, what we're doing over the current approach is that, again, these high resolution models, we have the output where we can directly count extratropical storms and capture the extreme events and states that haven't occurred in the last 50 years of observations, but we know are scientifically plausible to occur. And you can go through similar arguments for both severe convective storm and flood as well. But we're really excited about being able to produce these scientifically sound event sets. And just one item of note on tropical cyclone, one of the industry practices, the standard industry practice within a tropical cyclone is to statistically model intensity. That approach works well over the open ocean where you have this nice homogeneous environment. But statistical modeling of intensity gets a little tricky when you represent the tropical cyclone as a point source, and you know a lot of that area is interacting with land. And so that's really where your statistical models break down. And the concept of being able to represent the physics properly of hurricanes is attractive to us. Global weather peril coverage. Again, this kind of gets back to the insurance gap. These are, by definition, we're working with a global model that produces coverage for areas where we don't have great observations today. So we'd have global coverage of all perils: tropical cyclone, convective storm, extratropical storm, precipitation, which drives flood, and drought. And understanding the hazard risk is necessary but not insufficient to pricing risk in those regions. So yes, there's other factors at play, but first and foremost, you want to understand what the hazard risk is in these areas where we have insurance gap problems, and the GES model represents a potential solution there. Just then the few other items here: climate change, seasonal forecasting, and event response. I've rolled all of three of these up into a single slide. I just want to make a few comments on each. So climate change, this is probably the #1 question we get asked from a lot of our internal investors. What is your view on climate change? What do you do about it? How do you think about it, et cetera, et cetera? So the more informed, the more we can do internally around that topic, that's really valuable to us. And the idea of being able to, and we don't want to be beholden to any one potential climate change scenario. You know, we have people who know climate science, but none of us are climate scientists per se. So we want to be able to look at different scenarios and say, okay, for this given scenario, how can natural catastrophe risk be impacted if I make an assumption around this scenario? And the idea of being able to take those various scenarios and do a global simulation on that is very intriguing to us. So again, getting back to some of the concepts that I talked about before, do the correlations change between perils and regions? We don't know. Does the maximum intensity of a hurricane change? You know, could it be, you know, you're going to get more, you know, very strong Category 5 storms? So being able to be more informed on the climate change topic, and specifically when it comes to understanding extreme events, is really useful to us from a reinsurance perspective. Then we get into the seasonal forecasting piece. There's some ways where if we have high confidence in a forecast for, say, the next few months or looking out for the year, you know, there's certain things that we can do to act on that forecast, right? And so can we produce forecasts of explicit simulations of tropical cyclone that is an improvement over seasonal forecasting techniques today, which are largely statistical based? Same thing as severe convective storm. Can we use the outputs from this model to help inform our forecast view for, say, the next month, the next 3 months, the next 6 months? There could be a lot of value in being able to use the model for the inter and intra-seasonal forecasting application. And then finally, when it comes to event response, you know, one of the things that we need to do is be able to say, here's where the event happened, here's the magnitude of the hazard, the wind speed, the depth of the water, the size of the hail, et cetera. And can we run the model in such a way that we can produce realistic measures of that hazard? So can we directly use the output of the model to help better inform the event that took place? And again, once we have that representation of the event footprint, we can plug that into internal models and tools that we have that we use to make things like loss estimates, here are the contracts at risk, et cetera. So there's a lot of value there in being able to have improved event response capabilities, again, especially in areas where we don't have great hazard data coverage today. So with that, I'll stop there. I think I'm right at about 15 minutes. So
Thank you so much. Okay, next is Edith Macra from the Metropolitan Mayor's Caucus.
Good afternoon. Really glad to be here, and I'm just delighted to learn a lot from you. I will admit that I had some doubts about why I was here, but I have to say that I got some great pep talks as far as what the perspective that I can bring and how that might be helpful to you. So again, I'm Edith Macra, and my perspective is working with local governments. The slide a little bit about who we are and what we know about working with climate information. So first of all, my organization, the Metropolitan Mayor's Caucus, represents municipalities in northeastern Illinois. Our region has 7 counties in it, 9 million residents. And if you don't know, the state of Illinois has more units of local government than any other state. We are highly fractured. So we have a lot of organizations where we separate out authorities and powers, and then we have overlapping boundaries. For one example, you all look puzzled. Those of you who aren't from Illinois, take, for example, parks. Parks are a different agency, different elected body. We have different fire protection districts, but not always. So it can be very confusing. However, the authority of the local governments or the municipal government is better known. And the reason that I had that slide earlier, about, the first slide about just the connection that we have, is that people in communities know their mayors, they know their civic leaders, particularly in smaller communities. Because our leaders are present in the grocery store, you're going to see them in the gym, and you can readily go to a village board meeting or a city council meeting. So it's a very easy way to get connected to government and to be involved in decision making and have stakes and outcomes. So the Mayor's Caucus is a not-for-profit regional council of governments, and the council of government unit is something that, again, may bring some familiarity with you. So we have county level council of governments, something like 20 to 40 local governments or municipalities in a council of governments. We're umbrella to 9 of those. So we're a rare regional council of governments. But then at the next levels, you'll recognize some of them, like the Illinois Municipal League, or when I worked in Massachusetts, it was called Mass Municipal Association. The acronym meant More Money Always. So you probably know some groups like that, or U.S. Conference of Mayors or National League of Cities are all councils of governments. So we have municipalities in our region that go very small, from 700 people up to city of Chicago at 2.8 million. The average population, however, is about 20,000 in our municipalities. So it's mostly made up of small governments. And what we've learned is that we do better together. So, in the spirit of collaboration, we do a lot of things together. At the level of the Metropolitan Mayor's Caucus, we have the ability to address things like climate planning, which is what I'll talk about next. We're still a small organization, but in 2021, we partnered to create the first regional climate action plan for the Chicago region. We were one of only 3 regional plans at the time that were advancing. We were selected as a pilot project by a group called the Global Covenant of Mayors for Climate and Energy. So we were actually mentored by the European Union to do the first regional climate plan, again, focusing on that idea of working collaboratively together and empowering these smaller municipalities that were really working together on sustainability, but not yet on climate. I'm sorry, I glossed over this map here. We were working together on sustainability. So if you see the dots on the map, those are communities that all got together behind a program that we have called the Greenest Region Compact, where we set a consensus sustainability goals and put it out for municipalities to connect to through formal resolution. And those simplified sustainability goals that are tailored for municipalities, we now have 161 local governments that are supporting those same set of consensus goals, and our sub-regional councils of governments, which is the largest regional sustainability collaborative for municipalities in the country. So we have the ability to coordinate. And in 2017, when the politics on the national level were changing, we picked up the mantle and the challenge and said, okay, we are going to look at the non-federal leadership on climate, which is why the European Union extended a hand across the pond and said, let's work together on this, we'll show you how. So that first climate action plan was really powerful. And that's when we first got introduced to climate modeling and working with climate scientists Don Wubbles and Ashish Sharma in the room, who really helped us understand where our connection was to climate science. Just to put out there, there was another climate action plan. The US EPA had invested in just recently in regional climate planning and state level climate planning through something called the Climate Pollution Reduction Grant, which put $4.3 billion into both climate planning and climate mitigation investments. So we were also the lead on that project. So 2 climate plans in 3 years. The first climate plan was very data-driven, as was the second one with the US EPA. But going back to this one, because again, we were very close to the climate science on this one, and it was new for us, we brought that information to our local leaders. So we based our plan on a greenhouse gas emissions inventory. This is the updated version already. And that was something that it's very tangible science. So there's emissions. Most of them don't require modeling. Most of them are just gathering the data in analyzing our source of emissions. We use that greenhouse gas inventory then to develop a set of strategies, further model where we would be impactful in terms of emissions reduction. What was very new for us in doing the first plan was looking at climate risk and vulnerability. We had never really before pulled together at the local level to look at climate resilience. So we did, and this is where I think we need a lot more assistance. And this is, again, where we connect, because the work that we did on this was pretty coarse. Everything's on a time frame, of course, but we looked at what our greatest climate risks are in terms of heat, in terms of flooding. And then we had some modeling that was done by our Metropolitan Agency for Planning related to flood susceptibility. So again, lots more work to do, and I know there's more work being done. The plan itself is really tailored for municipal action. So while it's a regional approach, we knew that with an audience of the 275 municipalities is that there's only so much we can do, and that we really need to focus on the levers that we have for climate action. And so those are lead by doing. This has a lot to do with the way local governments operate their own businesses, to encourage others to be responsible for climate action, mitigation, and adaptation, which is surprisingly powerful. And that's, you don't think of it, you think of the one that probably you thought of first, enact. So we're codes and policies people for sure. That's what we do, and we have the ability to have responsive codes. The plan that we put together then, we took those strategies, climate, science-based targets, and then created a plan, put it into municipal speak. So this is where we start to move from theoretical to implementation. And just picking out one of those, I'll follow it through. So there's a strategy to adapt development processes, meaning our zoning codes and policies and permitting, to accelerate investment in EV infrastructure, charging infrastructure, because we know that this is a really important climate solution. And then we, through modeling, sort of looked at how it's a decision support tool. So what municipalities could expect in terms of investment, greenhouse gas emissions reduction, and the degree of effort required. Each of those strategies was also analyzed for equity considerations, for the partnerships needed, and for outcomes and co-benefits that could be gained for the community. And then we moved to action. The Metropolitan Mayor's Caucus, we're not a planning organization. Municipalities do plans, but everybody needs to get some things done. We run on election cycles. We have impatient constituencies. And so the real strength of the Metropolitan Mayor's Caucus and our municipalities is taking this collaborative action. So just two examples. We don't always do things that where we hand out plaques, but both of these happen to be really successful ways to drive that strategy that I showed you on the plan, which is to adopt development processes and codes to accelerate investment in clean energy. The first one on the bottom was a program that was done by Department of Energy. It was a federal program, came up with a checklist of actions that municipalities could take to accelerate solar development. And not only did Illinois take the title as the most number of Soul Smart designated communities for meeting a certain number of these actions, but one of the municipalities, Schaumburg, not a shining star of sustainability. It's not a standout in community in many ways. They have 75,000 people. They adopted the Soul Smart program and then saw a 24,500% increase in the number of rooftop solar installations in less than 2 years. So it's very effective. It's deadly dull. I admit it. Zoning codes and permitting policies are not for everyone, but highly impactful. And our newest program then took that same concepts and models and did it for electric vehicle infrastructure. So that program is very new. We just have 2 cohorts of communities that have become EV ready, first in the country to do that, although there's now a national program that is also operating and looking to do similar things. But I want to now switch to I talk about how well we work together and how we're innovative. And now I want to talk about how maybe we don't always listen to what you're telling us. So this is really important here. And so despite the fact that municipalities have access to knowledge and that we're trying to communicate it, we don't always do the right thing. Let me just say, don't always. So this was a particularly frustrating campaign. This is just a couple of years ago. There was an effort because the Biden administration put a lot of funding, to me, it was very smart. It was very integrated. If you adopt codes and policies and you meet certain standards, you can unlock a lot of funding. And so in something called the Building Resilient Infrastructure Communities BRIC program, there was a requirement that states that would compete for billions of dollars of funding have a statewide building code. And for those of you who are not familiar with codes, we have something called the International Codes Council, where a lot of really smart people spend about 3 years figuring out what's the best approach for building codes, whether it be in plumbing or energy. This is structural building codes. And so those are passed down to states to adopt and then eventually to local governments. So we have the knowledge. This is presumably where they're talking to climate scientists and developing these codes. And Illinois was one of 6 states that chose not to adopt the statewide building code. And not only was that leaving us in harm's way, we had a very well-publicized failure of an Amazon warehouse facility in southwestern Illinois that collapsed. A lot of question about the building code. So on the heels of that, there was a campaign to please adopt a statewide building code. One of 6 states, Illinois likes to think of itself as progressive, one of 6 states in the country that did not have statewide building code. And there was a huge educational effort, and in great embarrassment, my parent council of governments, the Illinois Municipal League, opposed this. And so we were, despite the fact that we had the knowledge, we were experiencing climate change, we were experiencing loss from climate change. We're part of the U.S. Climate Alliance where the governor takes a pledge. We chose to oppose this. And so the bill eventually passed in a watered down form, and municipalities don't like being told what to do. And so they now have to do they have to comply with the code, but they don't have to adopt the code. So this is how we sort of weaseled out of it. And again, I'm not proud of it, but this is also Alton, Illinois, that is, again, very serious floods there. Another lesson in receiving information from scientists that didn't go all that well. In the Illinois State Water Survey, based here at the University of Illinois, very important voice. We in the Chicago region mostly have access to Lake Michigan water, but we have groundwater supplies. The Illinois State Water Survey began sounding the alarm about the deep sandstone aquifer serving Joliet in many parts of the state, but particularly serving Joliet and the southwest portion of the suburban region in the 70s. And the information was ignored by policymakers. It was actually the mayor of the city of Aurora who was a leader in water supply planning, because the city of Aurora, our second largest city, is reliant on groundwater. And pulled the mayor of the city of Joliet aside and said, please listen to the scientists. And so in 2015, a new report came out. In 2018, Joliet was jumped into action with 15 years left on their water supply. And that's not that much time to build a brand new water system and to negotiate. They had to set up new governance structures. So again, with that, I have a concluding slide. And this is just a message that Calvin thought you would get. You would get a good laugh out of. I agree. I saw this. My husband pointed it out in a catalog and he said, don't you have some scientist friends who would love that? So I'm sharing with all of you. And if you're online and you can't read it, I'll just read it out loud for you. And it just says, at the start of every disaster movie, there's a scientist being ignored. So I was going to wear the t-shirt, but in true climate activist fashion, I decided not to spend the money and get the climate of emissions a t-shirt I don't need, but we needed the chuckle. So with that, I'm very happy to close up and turn it over to the next speaker.
Okay, so our next speaker will be remote. He is John England from the U.S. Army Corps of Engineers.
Thank you, Francine. Hopefully everybody can hear me. Give a thumbs up.
We cannot hear.
All right. Can you hear now?
Does
Your microphone is not working.
My microphone's not
Oh, yeah.
working.
Got it. We got you. Yes.
Super. Well, how do I follow the last two speakers? Maybe we can pull up some slides
Okay.
so I can start jumping right in here. So I'm going to integrate some things from Jeff and from Edith on critical infrastructure. So this is really retrospective. It's pretty narrowly tailored. So some initial caveats. I'm a lead civil engineer at the Risk Management Center, and we work really closely with statisticians. Part of my background is hydrology, atmospheric scientists, which I'll cover in a bit, geologists and some other things. But most of what I'm going to cover today is retrospective, right? So it's planning activities, very, very large infrastructure. But we also can use these same tools for reaching out for forecasting, like the Helene, which just happened. As you all know, we had some of our facilities hit record pools in North Carolina. Just for intro, the upper picture is Lake Lanier. So for those who've been to Atlanta, that's a big core reservoir that's critical for water supply and flood control. The design storm, so we use surface ops, is on the upper right. This is from March 1929. The lower center picture is Keystone Dam on outside of Tulsa, Oklahoma, and their design storm is from May 1943, and a core storm catalog. We update these catalogs periodically, but we really could use the input from the models to help with this that I'll get to. Next slide, please. So just to orient yourself for this international audience, this is just a snapshot of the Corps' U.S. presence. Again, I'm going to neglect the Department of Defense. We have this link between the Corps climate community of practice with Department of Defense closely integrated on all those facilities like Guam. Overseas, we get questions, but really where I work is the space of all the red dots on dams and the over 15,000 miles of levees. So let's now zoom out a little bit. Next slide. Besides the core, there's this whole infrastructure that's been historically that provides benefits for the U.S. Water supply, recreation, flood control, power, right? So FERC, these are the green dots, the Federal Energy Regulatory Commission, over 3,700 dams in the, CONUS. Note the top picture is a couple of dam failures I worked on. I'll have one slide on this. May 2020, right when COVID hit, a big rainstorm happened and a couple facilities failed. So we do retrospective planning to make sure that these things don't happen and communities can get their benefits. Like the one on the far left, that's Folsom Dam. So those who've been in Sacramento, that's a Bureau of Reclamation who operates in the 17 Western states. Most know Hoover Dam, around the world. Addicks and Barker, I was involved in a legal trial because during Hurricane Harvey, the two facilities shown on that lower slide in Houston, we flooded a whole bunch of communities for over 30 days. Watts Bar and Watauga, coincidentally, the event that happened last week, Watauga hit its maximum pool by over 3 feet last Friday. It's a 314-foot dam that TVA runs, and TVA also regulates, it uses nuclear facilities that are regulated by the Nuclear Regulatory Commission. So critical infrastructure around the U.S. Now let's zoom in a little closer. Next picture. This is from a report I'll describe in a bit. I was on a panel, fantastic time serving with Ruby, and there's 12 of us on this National Academy of Sciences panel. I'll describe where we can intersect. So this is a picture from that report. On the right is 16,000 change high hazard dams in the US. So notice, I can't point my cursor, but if you zoom into Tennessee and Western North Carolina and South Carolina, not to neglect Florida, but there's major critical infrastructure. And the design standard we use is called this maximum precipitation. And I'll talk about the needs of modeling to meet retrospectively those things. On the left, My wife grew up in Lexington County, South Carolina. This is a dam failure on the lower left, and on the upper left is a picture of rainfall from the Weather Service for that event in 2015. So these are significant hazard dams. I'm not showing this on the map, but there's over 10,000 in the US. 50 dams failed in South Carolina in 2015, and then when Matthew hit North Carolina, another 20 or plus dams failed in North Carolina. And these aren't things that we like to happen as engineers and designers, but they affect people and property, and the risks, as Jeff mentioned, are critically to assess. Next slide. So just some overviews of what the impacts are. My coworker at the time flew down to Puerto Rico. This is a forensics, a study that we did, and an emergency repair. So the Corps of Engineers was called. And so this is in southeastern Puerto Rico, and there's a spillway as you see in front of you. And what happens is if the spillway flows a long time, it can erode all the way back to the dam and fail, and the lake would drain and potentially impact 70,000 people that were evacuated. Next slide. This is the one from Michigan, just to give you perspective. On the left here is Edenville dam. That was hopefully all over the press. People heard about the flooding in this part of Michigan, right near just near Green Bay, and this failure from this dam caused the downstream dam to fail. So neatly, it was the duration of the flood, not necessarily the magnitude, but there's multiple factors we need to have. So the duration of the flood caused this one to fail, and then the second one downstream, shown in this upper right, Sanford Dam, failed to overtopping. You can see the water going across this green grass. That's the embankment, and they couldn't get all the gates open due to debris on the left, that sort of thing. So that's just the impacts we try and prevent retrospectively. So what information do we require for this? Next slide is on risk-informed decision-making. Lots of information here. What I'll point you to really is a Corps of Engineers engineering regulation. So regulations are required by certain federal agencies, and they're used holistically across states and other sectors where the FERC would look at the Corps. What's the Corps doing? Are we all on the same page with these regulations? And so we're using sort of two metrics. One is quantitative risk estimates, very, very small probabilities for these critical infrastructure such as nuclear reactors, 10 to minus 3 to 10 to minus 7. So, really small probabilities. Jeff mentioned, long time horizons. We want to have model runs at 10,000, the length of that time series, to do ensembles and to use those model outputs to get statistics. Shown in the center here, this is a hazard curve. It's reservoir elevation. It was used to assess the dam shown on the upper right. This is a critical flood control dam for Portland. It's called Lookout Point. The lower right is Dallas floodway. So those who have been to Dallas, downtown Dallas, there's a whole floodway where there's a Corps of Engineers and Tarrant Water District dams that protect, and we build levees to protect these major cities. On the far left is a picture of surface rainfall obs. So this is from February 1996. We're still using surface obs mostly. We want to get to the models. We want to use the models. We want to move away from the tools that we've been traditionally using, like MRMS, the radar-based tools and that sort of thing, to do ops for our models. Next slide. This is sort of a zooming in thing. The critical takeaway here is we do watershed-based assessments. So this is a frequency curve on the right of precipitation for 48 hours. It's the basin average over 6,000 square miles for the Dallas floodway and dams upstream of that. What we do is we take averages in space and time to estimate a basin average, but we want to preserve the space-time structure like the storm shown on the left. This is a May 1990 storm. We use surface obs again. We want the models to help with us and to include climate change. But we're doing very specific analyses where the risk is high and we have the resources to do that. Other facilities, screening level processes, for CONUS applications, we don't have that basic information to do screening level analysis for every single site, 90,000 dams in the country. That's what we could use. One more slide on the details of this. This is what the hydraulic and hydrologic models use. So again, the slide on the left, my mistake. The previous picture I showed was actually from September 1921, one of the historical storms in Central Texas that's in a core catalog that's really old, and we have to reconstruct those storms using modern techniques to get gridded information that we can use in our models. We don't have those gridded information at very fine space and time scales around a kilometer, 15-minute resolution, because that's what the models require, these sort of curves. This is a hydrograph on the upper right and a reservoir elevation. Plot over time for an event. This is the May 1990 event. Over here's Grapevine Dam on the lower right. So if you fly in Dallas-Fort Worth, you essentially cross over Grapevine Dam, which protects Fort Worth. So we need this fine scale information. Next slide, please. So how do we get there? One thing that I was able to it was a wonderful opportunity. Ruby's there in the audience. We had a great time. And 10 other people, really, we put this team together through the National Academy for a report produced for NOAA. Major recommendations here for NOAA. And what this is a transformational report to really modernize what's going on for the engineers where I sit, so we get better information today. Just like those events that happened, Hurricane Helene and some of the other previous ones, we want to look retrospectively, but most importantly, we want to look to the future. So the key conclusions of this report was to recommend a model-based approach. So here we are with the modeling audience. We need you guys, and we need this stuff today. We also need some longer term things, which I'll get to. One thing in this report for those in infrastructure, the previous speaker mentioned like the building codes. So there's a long-standing sort of design code for dams and levees. It's called probable maximum precipitation. It's been around for about a century, and the science behind those things is really from the 1940s. I'll skip the details. They're in the report on the history, but we need to do much better today. And critical to that is a phased approach. So next slide, please. Lots of information here. The key takeaways are moving from left to right current practice to model-based estimates. We're recommending 5 to 10 years to achieve a recommended definition, and a critical part of this is a model evaluation project. So the engineers are pretty skeptical, right? It's like, how does the storm scale approaches work in WRF so that we can use those at the global model, at the ESM, to get these estimates for what we need. So what I'm really interested in is what we can do today. So other folks have mentioned, combining, the mesoscale models, which I've been interested in using over the past decade. We're trying to get there with the community. They're not quite comfortable with those mesoscale models, and now we're going to move to Earth system models. Really exciting time, but two things we need to do with these models is under box, this yellow box, bullet number 2, there's current weaknesses, we need to improve it. But more importantly is bullet number 3 in the near term is climate change. We need to include that today for our risk and resilience. Longer term, we want to get to, again, bullet number 3 on the green slide is quantify uncertainty rigorously. I skipped over that. We can do it statistically, one of the previous slides I showed, but we really want the model output to do the statistics on, not strictly surface ops. Next slide, we'll just touch on a couple key things so you see a little bit more. Is this model-based approach? Multi-model, large ensemble kilometer scale models. I think you're all familiar with that. That's what we need. Really, we're at 3 kilometers now, 5 kilometers in some instance at some of our installations. We want to go finer, and we don't have the capability to do that CONUS or for the whole US. Alaska problems, problems around the globe, as you know, South America, and grabbing stuff that's climate change information from the Cortex project. We're trying to grab that information today, and we're sort of behind the 8 ball trying to make sure our facilities don't fail. Next slide. So where I would see the opportunity in the near term and the long term is do both, right? So this model evaluation project, you're building these ESMs, there's a clear global community. We would like you, honestly, to help work on our problem. So we can use the models that you're developing now, improve cores and improve resolution to do some physics, combine that with the AI and get to where we need to be in current practice, which is, again, like 50 years old. I think in terms of time, I'll skip this next slide. If you can skip through this. Oh, sorry, the previous one. So NOAA's on point for doing a lot of this work in collaboration with the core federal and state and academic partners, as well as the private sector. So here's one example. We had funded this work for Cal Davis a couple years ago. We had a mesoscale model run over the Pacific Northwest. The watershed is shown in the black line. So this is the Columbia River Basin. Very, very large scale for the core, using models and doing approaches so that we can get quantitative estimates, but we don't have this everywhere. So I'll leave you with two more quick pictures. One is from the National Academy Report on the next slide. This shows you ideas of products that we need today. The durations are on the upper left and the watershed scales are on the lower left. 1 square kilometer is what we need. So I'll finish up with, just in the interest of time, the vision we have. So that's the very last slide. So there's challenges here and opportunities. So I'm here really to ask you, hey, here's our neat little problem, and it has major impact across the US and across the globe. There's an opportunity to link the climate models, and I've skipped over the forecast things that the core does and the climate change information, but it's getting that information today to make opportunities and decisions, and we think we can do it. So we could use your help on that. Thanks.
Thank you. And our next speaker is Jean Brokish for American Farmland Trust.
Thanks, everybody. serve as the Midwest Deputy Director for American Farmland Trust, and I'm also feeling a little out of my element here. Like Edith, I had to get a couple pep talks to make sure I was in the right room. So I appreciate the opportunity to just kind of share some perspectives that I see are important from the agricultural sector. I work for American Farmland Trust, so just briefly a little bit about the organization and then about myself. We're a national organization that really thinks holistically about making sure there's a base of farmland, long-term preservation of that farmland, how we're managing that farmland, and then what are the policies and practices and procedures that we need in place to make sure there's a vibrant farming population out there. So a bit about me, I'm not a data scientist. I did grow up on a dairy farm in Wisconsin, and I've worked in the kind of that center of conservation and agriculture my entire career. And while some of my time and my career has taken me outside of the Midwest, I currently spend a lot of time here in corn and soybean country. And I'm really, acknowledging that I have a pretty heavy Midwest bias in my presentation. But by no means, is that the entire picture of U.S. agriculture or global agriculture for that matter. So I've organized my thoughts into kind of 3 different, space-time buckets. And so the first, I'm just thinking about this field scale. These are maybe decisions happening on the daily or weekly basis. And so this is where farmers are thinking about, irrigation, timing and rates, and when to plant, prune, spray, fertilize, move livestock, et cetera. They're making decisions on how they're managing their tile water, which I'll explain in a little bit. They're also thinking about, or hopefully thinking about livestock comfort. Is it too hot or too cold for their animals? And then also thinking about farm labor. Is it too hot or too cold for humans to be in the field doing that physical labor? So I want to say, I think most of this data is already available. But it may not be getting in the hands of farmers and may not being used to inform their decisions. So that's one thing I think maybe is a theme through some of my future slides as well. And then, out of this list, I just really want to highlight that risk to humans and the farm labor piece. So to my, there are actually rules and regulations that say how often and how long and with what type of soap farm workers need to wash their hands. But to my knowledge, there's no regulations around when is it too hot or too cold for people to be working. So I think that's maybe my first piece of challenge to you all is, can climate data better identify and prevent those risks to farm workers. I'll dig into tile water management just briefly here. For those that may not be familiar with it, tiles are just basically perforated pipes laid below the soil surface. They are oriented in the upper left. They may be oriented perpendicular to a ditch or a stream or something. And their sole purpose is to really remove water from that soil profile. So it's generally, if you're not familiar with the Midwest or the Corn Belt, it seems a little counterintuitive, but by and large, this is what makes Illinois farmable. This is why we can grow corn here. It does a great job of draining that wet spot and making it suitable for crops, but it has some trade-offs. It's very leaky, both in terms of leaching nutrients that become pollution once they enter the waterways, and it makes crops more susceptible to drought when that weather turns dry. So this slide, options do exist to manage our tile water better. And this is kind of an image showing what a water control structure would look like. So if you're imagining that perforated pipe coming out and discharging into the stream, you can actually insert a control box with some gates, and you can lower and raise those gates depending on how much water you want to put in there. So this image from Purdue University shows how a control structure can be used throughout the year. On the left, this time of year, you're harvesting. It doesn't really matter by and large if those fields stay wet through the winter. So you put your gates in, you close it, and you hold all that water and you hold the nutrients in the field. And then right before planting, when you want it to dry out so you can get your tractors in the field, that's when you remove the gates and it drains. And this B figure here, this is what 99% of the tiles look like year-round all the time. We don't have these control structures in place, and we're just losing that water as soon as it enters the soil profile. But again, with a control structure then, in figure C part here, once the crops are growing, you can put those gates back in so any late spring or summer rains actually stay in the soil profile and are available to the crops, as opposed to just draining it all out and making it more susceptible to drought. So this sounds like a no-brainer, but by and large, farmers aren't using this. There's a couple factors there. Some of it is manual labor to raise and lower those gates. Some of it is just lack of data and not really knowing, is it going to be dry? Is it going to be wet, et cetera? And so, my question here is can climate data help develop these really smart water control structures? Could we combine that climate and weather data? Could we combine it with field data and then automate these, maybe use AI or machine learning or whatever to create these smart structures? The second kind of time space scale I have is just a kind of a farm or county level scale. So this might be looking at a handful of farms or 100,000 acres. And these decisions are generally thinking about like a seasonal or annual timeline. So this is things like field operations, planting and harvesting windows. It also affects crop rotations and how we are moving from one crop to another. Droughts arising way more quickly and becoming more intense. And how will that affect productivity and grain marketing? And, if you're a livestock farmer and your pastures aren't productive, you have to buy feedstock. What's the cost of that? Things like that. Just thinking about those economic decisions that farmers are making. And then the last point here too is dust storms. In 2023, about a year and a half ago, 8 people were killed in the state of Illinois for a dust storm that happened. And it was really affiliated or tied to field operations. And so thinking about when are the conditions right for dust, and how, again, can climate data be used to establish that warning system for dust generation? Maybe we need kind of like days where farmers shouldn't be, or we need to have other safeguards if the wind hits a certain speed, those kinds of things. I mentioned operational windows. This is the equivalent of my funny t-shirt. This is the only humor I have in my slide here, but thinking about field operations, farms generally are getting bigger, tractors are getting bigger, they're getting heavier. The amount of ground they need to cover in a short period of time is increasing. And so what we're doing is pushing the envelope a little bit in terms of when it's suitable. And this is compounded by the fact that there's actually a decreased number of days suitable for those spring operations. So this is some data from a fellow Illinoisan here working with Nutrient Ag Solutions, Eric Snodgrass. Over the 40-year period between April and May, which is really a short period of time, 60 days, we've actually seen the number of dry days decreased by 5. So the days without any precipitation has decreased dramatically, and the number of 2-inch rainfalls has doubled in that 40-year period. So what this means really is that farmers are pushing that envelope and they're having to cover more ground, and it's ultimately, stressing out their equipment, stressing out their soil, et cetera. And oops, it's not letting me advance here. Can climate data think more broadly about what that spring pattern looks like and how can that be used for farmers to adapt, and then think about maybe there's no plow day, maybe the soil's too wet, we've had a history of precipitation and we're expecting more, those kinds of things. That information may be helpful for farmers. Another kind of tool that I'm really interested from a conservation perspective is cover crops. And I'm not sure how many are in this room are familiar with it, so I'll just kind of give a little 101 on them. They're essentially a crop that you plant in between your cash crops. So thinking about a corn soybean rotation, you'd be harvesting your corn this time of year, and you would actually plant something. The sole purpose is to just grow through the winter, protect the soil, capture nutrients, add carbon and organic matter to the soil, and then you terminate it before you plant your other cash crop. So this is the management of, there's so many benefits of this environmentally, and some of farmers are finding a lot of success from nutrient cycling and erosion and water and all that. But the challenge really is, when do you terminate those cover crops? And so the picture on the left here is from Penn State University, and it's just a side-by-side comparison of them doing an early termination or planting green into the live cover crops. And pros and cons here, if you terminate early, you do conserve your spring moisture, but you have that limited biomass for the summer. And then if you terminate late, it could suck up that extra moisture and you have a lot of biomass through the summer. But we have some abrupt swings here. So sometimes it starts wet and gets dry instantly, like it did in 2023. 2024 started dry and then got really wet. So how can we use the climate data to help farmers better anticipate and find success with their cover crops? Next, in my last scale is kind of this regional scale. This may be multi-state, multi-county, multi-state, and multiple years. And so here we're thinking about yield resiliency, variety and breed selection. If we need to be thinking about different crops, do those markets exist now? Is the infrastructure here now? Do we need to build it? Insects and disease are migrating northward, eastward, westward. What does it look like 25 years from now? Irrigation has expanded a lot. How can we mitigate the impacts to the ground and surface water as we're using more water for irrigation purposes? And then climate, transportation, and market access here. Yield resiliency first. This is federal crop insurance is available to farmers to help safeguard their income, basically, against environmental disasters. And many farmers are purchasing crop insurance, and their premiums, by and large, have not really changed over the last 10, 15, 20 years, but the amount of money being paid out in indemnity payments has increased dramatically. And so the chart here shows that increase since 1990. And it attributes it based on which environmental components. So you can see the pinkish or salmon colored bar is drought related. By and large, that is responsible for a very significant increase in crop insurance payouts. Second behind it, and this is maybe a great irony here, second in the running is excess moisture. So again, we have these extremes of drought and we have these extremes of wetness. And one thing I think that climate data can do here is, I mentioned that the premiums farmers are paying haven't really increased very much, But as a homeowner, you know, I'm paying more for my insurance because insurance is more expensive. And so a role, or maybe a question for you all, is what role can climate have in evaluating those premium rates for farmers? And taking it even a step further, then, if farmers are implementing these resilient practices that make them less risky, then can we even dial in a little bit and then adjust the premium rates based on the practices the farmers are using? Thinking also about variety selection. Many of us know if it gets too cold, we don't get peaches, right? If it freezes in Georgia, no peach crop. But do we also know that many crops like peaches have a minimum chilling requirement, which means it needs to be a certain minimum or low temperature in order for them to even set fruit. So this graph shows peach orchards in Southeast US. The red dotted line is the minimum required chilling hours of 850. And the historic average in this place is 1,100 hours. So just generally thinking, you think, wow, this place is a good place to grow this variety of peaches because it meets that minimum chilling requirement. But if you look at this data, you can see 6 out of the last 9 years, they didn't meet that chilling requirement. So is that trend going to continue? And do we need to be thinking about different varieties? Do we need to be thinking about different fruit crops entirely? And so, my last question. Yeah, can climate data guide those decisions for crop and variety selection? This is a headline from just a month ago. The Mississippi River is running low again. The previous presenter from the Army Corps, probably well familiar with this. A lot of our grain moves by barges when the river's low. Farmers can't get their grain to market, affects the prices, et cetera. And, you know, a lot of farmers are marketing their grain 3, 6, 12 months in advance. So it would be really helpful to have those insights now to help inform those marketing and production decisions in the future. And my last slide for you, I think this is just kind of an additional consideration. It's really hard to put farmers in kind of, you know, stereotype them because there's a lot of factors there. And I know I was invited to kind of raise some questions, but there's a few more that I would just like you to kind of think about. And that's just kind of recognizing and thinking about the ag sector. There's generally a lot of small profit margins. There's a lot of multi-generation farms. So not only you as a farmer, you're trying to keep dad or grandpa happy, but you're also thinking about, you know, what your son or daughter or grandchildren might be interested in. There's a lot of farmer independence, but there's also a lot of peer pressure and social status quo happening in rural America. Labor is a challenge, a lot of pressure for sustainability and meeting those corporate sustainability goals that like folks like ADM have set, and then access to the data. We can have all the data in the world. If it's not translated into a language that farmers can understand and use, and if it's not accessible to them, it really doesn't matter. And so thinking about their trusted advisors, who are farmers listening to, and can they be a helpful intermediary for us? And then I just invite you to connect. Yeah, and I do want to give a quick gratitude shout out to my colleague, Dr. Bonnie McGill, who helped me kind of frame some of these things, but then encourage you to catch me at a break or reach out with any questions. Thank you.
Great. Thank you to all of our speakers. They were excellent presentations. So let's open this up for questions from the audience. Trent.
Yeah, thanks for the presentations. Can you hear me okay? I'll bend down here. Or I can take it out. There we go. Save my back. This is for everybody, but Gene, your last point about intermediaries, it reminds me of one of the few productive conversations I ever saw on Twitter, and now X, and it was between some pretty high profile climate scientists, none of which are in the room. Although you all are very high profile, these are different things. So I came out wrong. Anyway, they what they were, yeah. And they said, what's the big solution for like what's one thing that we can just do with climate data? And one of them said, well, we just need to make it available to municipalities. That was the conversation. And then they were basically painting it as like all of our solutions are solved if we just, all our problems are solved if we just make the data available. But Gene's point about an intermediary, I think, is really important. So, I mean, we can put all the new technology in that we want, and the advancements in computations, and we can make the data available, right? I mean, by and large, a lot of the climate data that's already produced is publicly available. But I think the accessibility is really important. So what's needed to say if this summit and the follow-up actions are accomplished, let's say the next 10 years, and we can give data that you would never dream of, 10 years ago, what's needed to make sure that data is actionable?
Is this on? Trent, you offered to pitch me a softball question. I'm not sure that was a softball question. I think one of the recognitions I want to say first about my presentation was I feel like as we were sitting through this morning's talk, I was like, oh, a lot of my talk and questions are more about weather versus climate. And so I think it's helpful though to maybe think like how people are thinking, we're thinking about the weather. I don't know if people are really thinking about climate that much. So that might be part of it, is kind of translating it into ways that, you wake up or you look 3 days out. As a farmer, again, I have to plant, I have to go. So I'm looking more at weather, not climate, but thinking longer term, they're listening to their ag retailers. They're listening to other farmers. They're listening to their grain marketers. Those are the people who really have the farmers' ears. So I think translating it and engaging with that audience to help them see this as a business proposition for themselves. I mean, I mentioned, the weather data that I got from Nutrien. Nutrien's the biggest fertilizer supplier in the US, perhaps globally as well. This is their business. They need to have a viable agriculture sector. And so translating some of this data and figuring out how to package it in a way that makes them see a business proposition for this and how they can then work with their farmers to understand it or their growers to understand it. And fertilizer is kind of a double-edged sword, right? Because the more fertilizer you sell, the more you make as a salesperson. But just thinking about it from that same lens, maybe there's other folks, the grain marketers out there who are engaging with farmers.
And maybe I would just add to that is a system or UI in place to really help the average person kind of visualize the data, right? It's definitely not sufficient to say, oh, the net CDF files are at this FTP site, right? Go here, and you can do whatever you need to do, right? If you think about, I think about a lot of these, websites, even just when we're monitoring lean, right? A lot of people have, some people have built some really sophisticated websites that pull weather data and help visualize it in a way that the average person can just kind of, pull up themselves, right? They're not writing their own code scripts to process the data. There's a UI in place, even a simple one where they can kind of click around and, pull what they need to. So I think that's actually really important and we probably haven't done it, like NCEP reanalysis, right? There's a decent way to kind of visualize a lot of that data, but I think there's a lot more you can even do there. So, tool UI in place to really empower the average person who has maybe some technical acumen, but, isn't going to write their own scripts to process net CDF to visualize the data.
And I'll just quick comment, just to sort of underscore the trusted voices. So Gene and I were talking before the presentation, and the municipalities I work with, very few of them are doing their own climate action planning or making decisions on their own. They are driven bottom up. So we have a lot of climate activists working on their city councils and village boards. But as far as that trusted voice, one thing that's been very powerful is just to be appreciated as for the perspective we bring and being invited to the conversation. So the relationship that we have as scientists really helps. And when you're choosing to partner with a trusted voice, that helps provide the translation. And it's incumbent upon us to get that into information. It does help to have it in a format that we can share it. But we, in many ways, are that link to the constituents we serve.
Yeah, can I chime in here from online?
Yes.
Great. Hopefully you can hear me. So I sent a link to the folks in the chat. This is really critical. So NOAA, we've been working with them. I was at the Bureau of Reclamation before. It's that partnering, right? So it's knowing the stakeholders, knowing what their needs are, and doing the space and time scales. So we have this old cryptic website that we've been hosting the core of the Bureau and NOAA, and partnerships with other folks outside in Canada since the mid 2000s on downscaling climate information to answer really water supply and hydrology questions. And so when I presented earlier, we need to go beyond that. But to your point, the critical stuff is nobody knows what an etcdf file is or what's BCSD, and the science has changed to LOCA, now LOCA 2. Who's the trusted partner? Who's delivering this information and it is accessible and usable? So we struggle with that too. And our successes have been really for the partnering end to end. So if we could use, ideas throughout the sectors like irrigation, particularly, like what their questions are, and they're going to be different, right, on the extremes versus what I'm interested in versus the increases in 2-inch rainfall. We don't have products right now that can answer that from a climate perspective. Thanks.
John, I'm gonna ping pong. So, John.
I'm John Shelf from Berkeley Lab, and I can't remember, somebody said disaster maybe start with somebody ignoring a scientist. Remember, they also tend to end with nuclear weapons being the solution, but anyways. So I wanted to ask about, a lot of folks talked about a 5 to 10 year time frame for climate data to input for decision making, but I also saw a lot of stuff that was seasonal in all of your talks. And, I wanted to get a sense of really how much of this wants to be driven by seasonal, which would be closer to the weather modeling side, where it's an initial value problem, and I want to see how things play out, versus climate, which is out in that year time frame, 5 years or more time frame, where it's a boundary value problem. So it's a different set of criteria that you want to optimize for. And we've been talking about AI versus physics models. But if you move more towards the weather direction, the AI models seem to be in a better position. But when you move more in the climate direction, it's the physics model still, in my opinion. So do you have a sense of where the boundary is between, when we switch over in terms of the forecasting or useful data for your decision making? And maybe for the climate modelers too, where is the boundary?
I guess it's a both and, I mean, people are making decisions on a daily, weekly basis, and they're also making decisions for the long term. So I don't know if there's a really like a fine line. And again, I'm not a data scientist, so I don't know the difference from your perspective on like what it changes, but it does sort of feel like, for me, from an agricultural standpoint, it's a pretty, especially row crop agriculture, it's a 1 year timeline is that seasonality, and anything beyond that, it's hard for farmers to really think about. Sometimes it feels like so, but those longer term trends are still very important. It's kind of a non-answer. I'm sorry.
And for us, for local governments, I guess the riskier one is the longer term, climate horizon, because of infrastructure and policy. That's also the greatest unknown for us. I mean, we too have seasonal decisions that we make, but it's a lot easier to accept, a season that was erratic and we didn't get enough road salt, or, we planned for events in the summertime and it was really stressful to people because we couldn't participate outside. So I mean, we're a little bit more used to that, but it's the longer term investments that we just really need the guidance on.
Say long term, what is that?
Yeah, and you don't want to get too long-term with local. So the question is, what do we mean by longer term? It's an investment horizon, and the time frame on a lot of our larger infrastructure projects are less than a decade. I think much longer than that, we tend to tune out, and that's going to be somebody else's problem on down the road. So it's, a lot of our strategic plans are in the 5 to 10 year horizon, which is about what it takes to plan a major capital project as well.
Yeah, I mean, and just further to that, I mean, sort of the answer for us is both from a reinsurance perspective. The typical reinsurance contract renews on an annual basis, right? So from that perspective, what's going to happen the next year, over the next year is important, and anything over that year. But then also, we're starting to think about, what does our view look like in, say, 2050, right? And having a view of what the risk looks like in 2050 is also a very important view to establish as well. So both are concerned for us.
And I know, John, did you want to?
Yeah, I'll echo that. It's the both and. What I talked about today was the really big infrastructure. So our planning horizons are 10 years to begin on a major capital project. So we're talking like some of the core projects are $1 billion. They're obviously more than the states, but that longer time, what I didn't cover is critical for, I think, the nation and the Corps and others that have been impacts. So we have the very, very short term. We have a program called the Forecast Informed Reservoir Operations. So we try to use weather mod. So the forecasters can do a better job at manipulating the water to save it in Southern California in times of deficit when a flood comes in. That's the benefit, is we can capture that flood water. And so we have a program we're rolling out on that. And that's a really short-term thing. But the flash droughts that you mentioned earlier, we've already had major impacts on the Mississippi on barges not being able to travel because it's, within the year. And seasonal water supply, broadly speaking, for the Bureau of Reclamation and water agencies around at least the US, they really want to know, because water is, as you know, is a big critical thing. So having that both scales is important. Thanks.
Thank you, John.
It was interesting to see that all four of you converge on what we really need, which is kilometer scale or better climate information, and nice API to build apps on top of it with a graphical user interface to traverse it easily. I think that's clear. I think we can all agree we want something like that, right? But the question is, how do we get there? And I think that's in part the theme of the summit. And it was striking how in the morning it was all about AI solving all problems, and you barely mentioned it. So John, for example, in your presentation, it was do kilometer scale simulations globally, and we use them directly, so direct from simulations to that API. I think in the probable maximum precipitation report, which was great because it's really forward-looking, reforming an archaic practice, but that was implicit in there too. AI was mentioned briefly in passing, but it wasn't an integral part for how to get there. I was part of a PCAS committee out of Kelvin's former office, OSTP, last year. We proposed a bit of a different approach, which I think would accommodate what you want. John, you want 10,000 years of simulation with a lot of ocean variability to broadly explore risks. You can't do it with kilometer scale models, but you can do it with 10 kilometer scale models. And so what was the gist, I think, of the PCAS report last year on extreme weather risk and climate risk was, well, do ensembles of 10 kilometers or tens of kilometers resolution, and then use downscaling tools, generative AI, for example, to get to the kilometer and build an API that feeds that. It was striking that in the National Academy's report on maximum precipitation, I think there was this latent conservatism I read in there that people didn't want AI. And I'm just curious about your views. I think in some of the other presentations that came through too, things need to be trustworthy, interpretable, that people do something about it. What is your view of how AI can play a role here while satisfying what your stakeholders need?
Yeah, I mean, I can start off. I mean, my view is if AI can help us better quantify the risk, we're all for it. I'm also cognizant that it's not going to be, the holy grail to solve all problems. Just as an example, this is maybe an aside, right? But one of the problems a few years ago, before I joined Renaissance Re, my former company, we were looking at the flood problem and trying to use machine learning AI techniques to identify areas that could be very susceptible to flood risk. Went through the algorithm, worked with some external consultants to help us come up with, a view there. And when it turns out, all these different variables that they said they would look at, it ended up just being a really clever and overcomplicated way to determine which areas had received a lot of rain and which ones haven't, right? So if you just overlay okay, yeah, of course, because these areas got heavy rain, right? So like if you take, in my mind, we never want to lose sight of the physics and the physical relationships. They kind of help us keep the guardrails on, so to speak. But at the same time, right, if we can leverage AI to help us come up with synthetic event sets, right? Tens of thousands of years of hurricane simulation right? We're all for it. Like we just hope that, the numbers of Cat 5 hurricanes, for example, is reasonable, and that type of, that we're not violating some of these, guiding physical principles.
I think for a couple of thoughts that come to my mind on using AI and kind of the ability to trust AI is sort of some perception of control. So maybe there's a little bit of like user input that's still needed, or people can do that so that they feel they have a little bit of control or trust in the data and the output. And then I think also, this was maybe more my question before. It's like there's so many models, and I get it's nice to have a lot of models, but some of that just creates noise. And so I just kind of wonder if AI is creating noise, and I'm sure it is initially. A lot of things create noise, but like how do we wade through that to get to something that makes sense and feels comfortable and true and accurate for people?
John? Are you gonna?
Yep. So on the National Academy report on modernizing problem maximum precipitation, I can speak a little bit to the committee, but more really as my personal view. The committee did our best job to really, the slides that I showed was really focusing on the long term. And so it was not, broadly speaking, AI was not a focus just due to oversight, right? So we're focusing on models, growing the modeling capability, and then what's really there, I think if you look at the key recommendations to NOAA, it really wasn't about dismissing AI or that sort of thing. It's more about, well, we were focusing on the modeling architecture. That said, what I can say is we were using AI a decade ago to track moisture using self-organizing maps into the Intermountain West. So there's technologies that's really great. We can use it today, and it's really helpful. So I see Tim's hands up, Palmer. Like we see it I'm looking for a near-term solution that we bring in everything. Historical data, which I sit on in the core in our extreme storm catalog, that isn't readily available to people. So there's a barrier there, but like bring it all on and sort of shake it out. So I think we're open because in the near term, what I'm pushed on the core, we have weather models, right? So we're going to latch onto those and improve those that we have. And I mentioned the model evaluation project. There's going to be things that they don't work right for convection for the fine scale details that some people may need on the really extreme rainfall, but they could do for other things. Thanks.
Thank you. Dan?
Yeah, so many good thoughts here. And what I was trying to think about was vetting. So, we're talking about stuff that's irreducibly uncertain. Right? We're talking about like the odd, in many cases, we're talking about odds of extreme events. And, we don't have 10,000 real years of history. We can make models that look really good and, do a great job in recreating the statistics, maybe, eventually for the last century, and then we can run them for 10,000 years. But it's still going to be an active faith to believe that. So I think Jean kind of answered my question earlier but what I'm to try and repeat it back, like it seems like what we're looking for is a lot about process. We're looking for maybe some kind of national effort that says, here is, that says every once in a while, here is the state of the art for generating probabilistic, information about extreme events, so that we can all say, okay, well, those people have settled this, and we're going to use their information, and it's going to be convenient and accessible, while we acknowledge that, we don't really know what the answer is to some of these questions. It can't. Does that sound right? And what are the things that like what is going to be convincing to users about characteristics of the data that you're looking at, that we've done a good job?
I think that's the $1 million question, actually, right? Because there is a lot of uncertainty and noise, and there's still, like in my sector in agriculture, there's still a lot of climate skeptics, and things like that. So it's hard. That's the hard thing. I do think though that this is part of the first step, is like getting out of our own echo chambers and start asking questions and listening to other people to see
what kinds of gaps in knowledge exist with them.
I mean, and I think too, if there's some way you can show that if you ran these, the model, whatever the GS model we're talking about, sort of to capture, some of the broad statistics or, kind of key observations over the last 20, 30 years. So like, maybe number of hurricanes, or number of tropical cyclones, maximum intensity of tropical cyclone, some rainfall, some of these statistics, and show that, while we're not intending to, forecast, these extreme events years in advance, right? You're kind of you're representing the events that we're modeling, are consistent with what was observed over the last, 20, 30 years. So I think that's a useful exercise to show that, yeah, we can recreate some of these extreme events with the, with the tool that we're building or have built. So.
Okay, we're gonna go Christy. Maria? Maria, Tim Palmer, Christy. Okay. Go ahead. Yeah, because you've been standing for a while, Christy.
I was hoping to get out of this. So my question was kind of answered, but I was too embarrassed to go back to my table, so I'm going to ask it again in a slightly and reframe it. There's two time scales that we usually think about, and they involve two separate modeling paradigms. One is the deterministic weather forecasting, which is 2 weeks out, and then maybe seasonal to intraseasonal, and that's a deterministic projection. And this is where AI does really well, because as somebody mentioned yesterday, it's more of an interpolatory problem. Then there's the long-term time scale, the 50-year time scale, where we use RCP 8.5 for maximum signal-to-noise ratio, and that's where physics-based models tend to do better, because you're worried about energy conservation and error growth over 50 years, and I think we're all familiar with those two paradigms. But what has struck me about all four of your presentations is sort of this third time scale, which is the near-term 5-year time scale, where you're sort of asking a slightly different question. You can go off the historical observations to a large degree, and that's a lot of what's being done. So, and Jeff, this is a framing that comes from one of your competitors. But one of the questions that strikes me on those timescales is more like, how different is the risk profile next year compared to the historical data that we're using to train our models, right? We know climate has changed. We know it's non-stationary. So that's a different question than either of those two. And I wonder whether it needs a different paradigm, because once you're asking that question, is how different is the risk profile compared to the historical data, then you're really worried about bias correction. You're really worried about not overfitting your model, so actually model complexity can work against you. So I guess what to phrase as a question for you is, how much do you care about each of those three time scales? And specifically that third one, I think I mostly know the answer is yes, you care a lot about it, but yeah, I don't know if that makes sense.
Yeah. Anyone else want to comment? I can jump in, I guess. I mean, first off, if that, I'd like to think that's part of the job that I serve, right? Is sort of representing what the risk profile looks like for the next year. And yeah, we have observations that helps inform that, right? But what other techniques can we leverage to inform that view? And the more tools that we have available to us to help inform that view, we'll do that, right? So, when there's evidence, overwhelming evidence, where the most likely outcome, not necessarily the statistically significant one, but maybe the most likely outcome suggests a shift, right? We're not afraid to act on that. So I think like the ability to sort of represent
even just, distributions and what the most likely outcome is, that's really important for the work that we do. So kind of thinking about it in that context is very helpful.
Okay, so in the interest of time, we're gonna do,
Christy.
and I apologize, we're gonna go with Tim Palmer, who's raised his hand for a very long time, and then we'll close the discussion. Okay. Tim.
Okay, thank you very much. I wanted to, I have to apologize. I haven't been following this discussion very carefully because I've been having supper, but I came back just as Tapio was speaking, and he made a point that I feel is kind of gets to the heart of this issue, which I just want to raise in case it's helpful. He sort of said, well, why don't we just have a 10-kilometer model and we'll do very long integrations and, more than we could do with a 1-kilometer model, and we'll just downscale to 1 kilometer with AI or something like that. And I want to make the point that for me, at least, the point about, or the principal point actually about kilometer scale models is actually not the kilometer scale information per se. It's not, clearly getting more extreme hurricanes and extreme events and all things like that is useful and so on. But for me, that's not actually the primary purpose of the exercise. The exercise is actually to reduce the biases we see in climate models on large scales, on scales of thousands of kilometers or more. These biases are something we've lived with ever since climate models existed. And I think it's very hard to make any regional statements about climate change in the light of these biases. A good example is El Nino. An order one question anyone wants to know about climate change is, how is climate change affecting El Nino? Because effects of El Nino propagate, around the globe. So if you have biases in your water circulation or whatever, it's going to affect how the model gives an impact of climate change on El Nino. So in a sense, it's not about having a better downscaled forecast. It's actually about how better resolving the kilometer scale will upscale to these synoptic and larger planetary scales. That for me is the key issue about kilometer scale. So we still, in a way, have to prove that actually is the case, that we can reduce these large biases with much higher resolution models. But that's, of course, the catch-22. You need the compute resources to show that. If we could do it all with 10-kilometer models, then yes, I think Tapio is right. But I think the problem is at 10 kilometers, you still do have to parameterize convection and gravity wave drag and ocean mixing. With 1 kilometer, you can't necessarily not parameterize it, but you can go some way towards resolving it. And that's the hope, that it'll have an impact on improving these larger scale biases. So I just want to make that point because it's an important conceptual point in my mind. It's not about the 1 kilometer information per se, but it's about the ability for that kilometer scale information to reduce the biases we have in larger scales. That for me is the key driver for this high resolution activity. Sorry if that's a bit off message for this session, but I just felt I had to say that in the light of
you're Tim, thank you. No, this is Kelvin. Thank you so much for that. And I was going to make the point that when Tapio made that comment, that in fact, what we heard among all the presenters was there's a multiplicity of time and space scales and needs. And so the tools that we have available, can we deploy them as effectively as possible to meet those individual needs? If we could do 100-year simulations and 100 ensembles at kilometer scale, maybe we'd be home free, and you'd get everything with that, right? You get the very large, droughts and so on and so forth. But, we can't do that right now. Our hope is that we'll be able to, create that capability much sooner than what we thought we could. But we have all these tools. How do we maximize the utility of them to meet stakeholder needs now? And I think the point is, we heard from them, their needs aren't getting met. And part of it's communication, part of it is other things. A couple of really quick points. I hope that in the future, folks like Jean and Edith, when they come here, it's not like I feel out of place. It's like I'm exactly where I'm supposed to be, right? That really needs to happen, right? Because they're the people that are on the front lines of this kind of thing. And if we don't reach out and help them understand and they become part of our community, then we've really missed the boat, I think. So I'm really glad you felt out of place, but I hope that a year from now you wouldn't, right? And so thank you for being willing and having the courage to come in and say, I'm not sure why I'm here. I hope now you do see, you could set up a t-shirt stand and sell t-shirts, I think. But another thing I just want to mention was we talk about risk and risk profiles and the hazard risk. You know, we think about risk like in the severe weather arena, there's a moderate risk of severe storms or there's an enhanced risk. That isn't right, folks. Risk is about where you live, how you live, what your vulnerability is. Risk is that. It's not about a uniform thing of, well, there's an X% of chance of this. And I think, you know, the community that Jeff lives in understands that. And we really don't think along those lines nearly enough. That we need to think about risk as being a very local thing. Do I live in a mobile home? Do I live in a well-built structure? You could be at high risk for severe storms, but your risk is very different, right? Very, very different. So I think that's really important. And finally, Jean, you know, the farmers, you talked about what Eric Snodgrass did in that survey. I'm really curious to know if you could do that on a really fine scale, what that would look like, because everything is what now? It's precision farming, right? And so when you think precision, you're thinking about, well, there's this broad increase of precipitation and the number of wet days is greater. But if you're talking about maybe half of Illinois, I imagine there's a lot of variance across that, you know, and that's the kind of scale that we hear from Renaissance Re and all these other folks. We need much more local information. So again, kilometer scale, it's not a silver bullet, but I think we're on the right track to doing that with AI and physics-based model. This has been a phenomenal session. I really am so grateful for you all to do this. We have a break now. We were going to use for brainstorming and submitting your questions and stuff that Maria is frantically synthesizing in GPS. No, she's not Chat GPT, I should say. But we are going to take a little bit of a break. If you would, go outside, turn to your left, go out the door. And it's not an attack drone, it's a photo drone, okay? So don't be afraid of it. And they're gonna take a cool picture of us as a group out there. So as quickly as you can do that. And then equally quickly, try to come back in by about what is the next session?
I think
Oh, sorry, go ahead.
the QR.
Oh, put the QR code back up. It's way back there. We'll stick it up. Okay, great. Yeah. And our next session is a whole hour of Q&A. So if you didn't get a chance to ask your question, believe me, time is coming now for you to have that opportunity. And Dan Reed and Maria Molina will chair that session.
Okay. I can do this. I don't even remember.
It's here.
Okay. Got it. We have.
is balancing that with software development and also our science questions. So there seems to be a bit of a tension there in that realm. There's also a bullet point that rose to the surface regarding challenges and opportunities at kilometer scale for non-atmospheric processes. So some folks in the notes submitted that ocean, land, and ecosystems are also critically important and also introduce challenges as well as some opportunities for us. Another key point is how do we evaluate our high resolution climate models? What are the evaluation standards and metrics, and what makes a kilometer scale model good and make sure that it meets the needs that are stated? We also need to go ahead and come up with some sort of concrete roadmap for actually achieving this big goal of kilometer scale sub-hourly predictions. And I'll also refer to an email that Bjorn sent following his talk where he said, you know, let's also think about not getting stuck in a sort of circle where we're kind of talking about what is a resolution that we need, what is a compute that we need, and try to move forward and identify how we could actually do this, meaning resources and also some sort of infrastructure. ChatGPT also identified issues regarding limitations of AI, machine learning for climate prediction, as well as climate model resolution issues. Folks also identified the need for a computational system designed for climate modeling, along with things like deployment timeline, memory access patterns, computational needs, flexibility, and also funding. And then the last couple of points here really just focus on that continuing tension between climate and weather timescales in regards to our modeling at this sort of kilometer scale setting. I know that was a lot, and we don't have these 10 summary points for you on a slide that you can refer to, but we'd happily go ahead and open the mic up and just let folks kind of speak on what some of these comments and that they submitted. And I guess I'll also raise that in our last session, we don't have any comments regarding stakeholder needs, but I'll point out that many of the panelists mentioned the importance of us engaging with stakeholders, and that oftentimes perhaps not going directly to a stakeholder is a viable path, but finding those trustworthy advisors or those folks that people have trust in to be those intermediary folks that can guide the conversation on what the needs of stakeholders are and what climate scientists can do to meet those needs.
Is there any way you could email that list out to all of us so we can ruminate on them? I couldn't keep all 10 of them in my mind.
I know.
Yeah, we'll work on that. John, are you telling that your memory stack is less than 10 deep? Okay, all right, that's what I just want to make sure. All right, Torsten is going to start us off.
So my memory stack is just barely one, you know, I can remember one. But I want to echo this one, which was basically asking for good metrics, for evaluation metrics. And there was a talk earlier that called that said do not underestimate the power of benchmarks in AI. And I think that is a statement that requires repetition and rubbing in. So I think we as a community, we should really try to understand how we come up with good benchmarks for the climate scale. I want to make this one of our major efforts because after all, these benchmarks have been driving AI. I mean, benchmarks like that have been driving AI to where we are today. So that's something I just wanted to bring up in the discussion where we should really think about how to do this. And I've personally been on that route to try to extract even a loss function, like not even a benchmark, but a loss function. How good is something from my fellow climate science? I'm a computer scientist. I have only dangerous half knowledge about climate science. But my climate friends are not really able to give me a loss function. And that is very concerning, actually. And usually it comes down to we run analyses and we see how well these analyses run. And other people say RMSE is a good loss function, but then you tell them like, no, it's not. And CRPS and things like this. So somehow this, and I'm trying to provoke here, and I see some people are getting aggravated, which is good. So somehow we should really discuss that. I think that's a discussion session, right? Oh no.
Okay, well, the risk of having unpopular and irrelevant opinions. First, we should not diss the efforts of CMIP in providing metrics for climate. I think they've done a great service there. And I think one of the metrics from CMIP and also from my own experience in a conventional climate modeling organization is I also tried to come up at that point with if you want a loss function for CESM or for the atmospheric component of CSM. And so I proposed, okay, we should use RMSE of time mean seasonal 500 millibar height, and then T850 and blah, blah, and came up with a set of 10 metrics. You average those together, you get an RMSE, you get a climate score, and you use that for selecting your physically based model. Yeah, it was a hopeless game. Even among the atmospheric modelers, it was a hopeless game because, well, what about El Nino? What about the Pacific Decadal Oscillation? What about the land surface? Et cetera. Anyhow, so I think the main moral is that climate modeling will always be evaluated along multi-dimensions. And so scorecards are more effective than loss functions. And I know we can't deal with that in ML, but we'll have to live with that. I guess the one other comment I wanted to make before we get into this, I'm a huge fan of GSRMs. I'm also a huge fan of machine learning. But the thing I felt like I most learned today was what we really, really need is a national climate information service more than anything else that can actually sort of formalize and improve the connection with the stakeholder community. And if we're going to do something tech savvy, we should also be thinking along those lines at the same time.
I want to take moderator's prerogative and pick up on that for a second, because something that Calvin and I found ourselves doing post-pandemic was participating in a conversation with folks about how multiple disjoint stakeholders involving government and NGOs and the private sector respond to crises and share information across cultural boundaries. And I heard a lot of that in the previous panel discussion, understanding how to translate the impact and implications of technological insights into ways that stakeholders can actually act on them. Because information without any, what do I do with this, is really not helpful. Because it doesn't empower people to actually do anything. I think that also speaks to how we communicate the technical urgency that we see from insights to government folks who would act. So I do hope as we talk tomorrow, one of the things I suggested in our breakout conversation, this topic is how do we actually communicate something that will cause action? Not just here are things we need to invest in to improve technical capabilities, but how do we motivate the people who in the end control the purse strings to actually do something? All right. With that pontification, someone else come up to the mic and offer an opinion. Otherwise, it's going to be a long hour.
I did want to follow up on the metrics point that was made, and in the back of the room, Professor Sonnewald was at our AI pre-summit intensive online and actually made some great points about the need to create an evaluation methodology that perhaps we may need to rethink that. And I am doing a terrible job at trying to synthesize your thoughts that you gave way more eloquently at the AI pre-summit intensive. If you want to come to a mic. Sorry. Thank you.
Sure. Thank you, Maria. Yeah, to some extent, I guess I'm also echoing, or we are echoing some of the thoughts that have been presented before, and that the things that we need the models to do, the AI models, aren't necessarily obvious to us as a community. Like Chris pointed out nicely just now, having a scorecard is very hard, but also defining the loss function is equally, what do we actually care about? And determining okay, how can we actually tell that we're doing well? How can we actually measure or present, hey, if you're a farmer, or if you, in my opinion, talking to the people that actually make those insurance policies is a great way of actually making the farmers do something, because at the end of the day, the amount of money that you have to pay is a real motivator. But redefining or thinking about community what the community cares about in terms of saying, okay, yes, this is how well my model is doing. I think it's really worth having a community-wide conversation about it. And I'm from the oceanographic community. I know there's a lot of representation from the atmospheric community, and the needs across these, are different in a lot of ways that may or may not be meaningful in terms of our development of AI models or determination of how useful these AI models actually are for a lot of the use cases that we envision for them. And I'm not sure if that's a question or a comment, but I would love to have more discussion about this.
Either way, it's fine. Thank you. So those are the summary that Maria read off, and will help John refresh his stack. So please.
I want to follow on what Chris and Micah were saying on this loss function benchmark question. It's actually incredibly easy to write on a loss function for a climate model. I think we want the climate model to predict precipitation and the impacts accurately. The trick is for the future, 10, 20 years from now, in a climate for which we do not have data, and that's the crux of the matter. We could write down a loss function, but future data are extremely sparse. That makes it difficult, right? And that is the issue with benchmarks and metrics. We can use surrogates, seasonal cycle and various variables, as we do for ILM land model intercomparisons, ECM eval tools for CMAP and the like. And they're all useful surrogates for the trust we may place into a model, but they themselves are insufficient. Models, in addition, need to have a closed energy balance, for example. Closed water balance is desirable as well. And so you need more than just a few metrics. You, in addition, need to be able to trace physical processes through these models to have trust in the outcome. And that makes the machine learning part harder. And I think that's why, say the AI models we've heard about, none of them was a climate model, right? None of them can predict the response to changes in CO2 concentrations. It is not something you can easily learn from present-day data. And I think that's why the climate problem is so much more complex, and we shouldn't shortcut this by saying, all we need is a right benchmark. I think benchmarks can be incredibly useful in response to Thorsten, more on a process level. Benchmarks for clouds, turbulence, for upper ocean turbulence, for the carbon cycle and the like. We can generate them in a more granular level, but holistically, the problem is that we don't have data for the future.
And we all know metrics both reward and punish, so you choose them wisely. Yes, go ahead.
Yeah, I just want to add, and in the spirit of discussion, thank you, Tapio. In my opinion, and I stress opinion, the focus on benchmarks as well could be, not just, okay, how am I training my model, but how am I verifying it afterwards? So for example, if you're starting to modify your loss function and thinking about physics-informed neural networks and whatnot, like Tapio was saying, we fundamentally don't have data from the future. So how do we know that, yes, the Navier-Stokes equations are going to, hold in the future, but the approach we have for putting them into our neural networks in terms of a loss function, maybe that's not appropriate. So what I think is very interesting is how can we, if we know some relationships would hold, verify potentially afterwards, okay, has this model actually learned physics? And this came up earlier as well, which I thought was nice. But thinking about what that might mean or not for, understanding why these neural network models are doing so well. There's obviously some information in there that we maybe as a community could do with figuring out how to access to answer some of the really important questions we have. And with that, thank you for letting me speak.
Good.
I was going to speak on on behalf of benchmarks, which I love. And I think that benchmarks are not a complete solution, right? Like we're never like the Tapio's example of like sort of extrapolation to future climate. There's no data there, but certainly I'm sure that we in this room can think of many examples of cases in which, say, current AI models currently fail even to reproduce current climate, for example, like the sort of the variability that you expect over like you know, in like the observed past. And like, so I think that the extent that we build those, we may still be able to, that will be very helpful in terms of guiding these models towards something that may eventually be helpful for a variety of different use cases, including seasonal forecasting, possibly also in climate projection.
Yeah, and acknowledging that sometimes some of these benchmark metrics may be at odds with each other. And so how do we try to find a happy space in between where we can try to meet multiple needs with the fewest metrics / benchmarks possible? Go ahead, sorry.
So do we need to distinguish between emulators of climate models that might be used to condense a large amount of data and give people interactive experiences around that data, and AI models of climate that are trying to be their own model rather than be an emulator for a model whose data you use to train it, like a single model? Are those different things?
Excellent question. I guess I will open the floor. I know definitions can vary depending on who thinks what is an emulator and what your training data is. And in fact, I'm on a paper right now where we're sort of stuck on a table of defining the difference between an emulator and all these other words. But I would say, I guess, an AI model that's trained on a data set that's derived from a physics-based model is inheriting those biases and some of those characteristics. So I don't know if you can fully decouple the two, but again, I welcome thoughts from anyone else.
I'd like to follow up on that, actually. I mean, this is, we make a conscious decision where we believe things extend into the future, where we believe that observed states of the past present the future, right? So it's pretty clear that the future for the future is very sparse, but it's also pretty clear that near-term weather forecasting works pretty well. So climate may be out of distribution, but climate is also out of distribution for your climate model that you run today, unless you make a hypothesis of what's going to change. You increase the CO2, and then you have your hypothesis that you put into the game. I mean, that is something that we need to decide. What are our hypotheses, how the future may be changing and whatnot? And then we need to limit the AI models to the places where we believe they generalize into the future. And we need to put in physical models or AI extrapolation models that allow us to model these pieces where we believe they change into the future. So it seems, and I don't understand the community well enough, but I understand from an AI perspective, other communities well enough, that they have a clear distinction between those. So is the CO2 concentration the only thing that we believe changes? Or is it second order effects as well, like CO2 causes more forest fires, and then our land model would need to change in a simulation. I'm not sure if that is taken into account today, for example. So it's the same for AI, and there's really no big difference. So we just have predictive models that either extend into the future or don't. And if they don't, we have models that explain how they extend into the future. Both of them can be handled by physical equations or by AI models. I mean, there's no magic in this way.
Wait, let's get a mic over there. I see Christy and Tapio replying. I'll add some to the fire. I think physics-based models are black boxes.
Well, I'll just remind people of something the statistician George Box once said about models. All models are wrong. Some models are useful. That's what he said, because all models are approximations. He could have said that about
Go ahead. Sorry.
Yeah, so this is a little bit different.
I was mainly teasing.
Yeah. So this is a little bit different topic, and then we'll get back to the other one. But one thing that I think is extremely important for us to be thinking about is the time frame on which we want to be deploying the computational systems and the modeling for it. And I would argue that we should do it as soon as possible, because I think by deploying it quickly, there'll be so much learning that happens. And along with that, I think it's very important to think about what would be the upgradability path, because the technologies in terms of the hardware and the software are changing very quickly. So we want to make sure that we're not deploying a system that we're stuck with for the next 2 decades or something like that, but we really have a good plan for upgrading the overall system. And then finally, I just encourage us as we think about the computational system that we deploy, making sure that we have very, very broad training, both on how to use the system, but then also making sure that the system is very easily accessible to a very wide range of users.
Yeah, great point. I'll add here, someone submitted something on how we even think about potential climate mitigation strategies and how would we validate that, which again, also valid points for extrapolation. Chrissy?
So first of all, I didn't say anything. Maybe my face is expressive, but it's on Tapio. I have a cheeky question for the audience, for everybody here. So on this topic of metrics, right, there's been a number of emergent constraints proposed for what metrics best constrain future climate change, like climate sensitivity. How well can we reproduce the current climate? How well can we reproduce historical global warming? Who knows what is the primary constraint on climate sensitivity now, according to the WCRP Sherwood et al. Report and to Chapter 7 of AR6. Who knows where the tightest constraint on the upper bound of climate sensitivity comes from? Chris knows it's paleoclimate. So interestingly enough, and that comes back to Tapio's, it's the one place where we have some data for what an out of distribution climate looks for. To me, as somebody that was in paleo, that's very scary because I know how finicky paleoclimate data is. But what we've been discovering is that a lot of these metrics that we can use to constrain models actually have too many degrees of freedom. Yes, you can constrain models based on how well they reproduce the historical record, until you find out that actually the entire CMIP ensemble is biased in their low clouds and in their Southern Ocean SST patterns. So you might be running into compensating biases and you're constrained to global temperature, and actually that's going to give you a biased estimate. So it's a really hard problem to find a metric that actually is predictive of an out of distribution climate. And right now, paleo is our best bet.
Thanks, Chrissy. Go ahead.
Yeah, it's interesting, perhaps because we are from the same department too. Like I'm also thinking about the value of the paleoclimate data. So my angle is slightly different. So my inspiration came from the animation or video from Bill John Stevens this morning. He was showing the satellite image like a simulation from the 1970s. Basically, using the simulation, you can get the data, the state of the atmosphere, like that was not visible to the astronauts. I'm thinking about, well, perhaps we can use the same idea to do the same thing for climate states. So say we train the machine learning models using a data from a certain historical period, but if we go back further, we can potentially validate the performance of machine learning model in different climates. So it may not be as good as validating the data in the future climate, but it is helpful. Then if you are willing to go back further to the paleoclimate, hundreds of years, 1,000 years, or millions of years, then perhaps we have a good, useful way to identify the model strengths and weakness using evidence.
Okay.
Thank you.
Hey, so I'm going to go back to another topic. God, this is tall. It's disgusting. So, yeah, so, you know, my wife and I, we argue all the time about stuff because she's a statistician by training. I'm more in the physics deterministic computing side. And when she worked at NCSA too many years ago, that I wanted, when they called it big data, working for Welge, right? And there's a lot of stuff we disagree on, you know, how far you can push, you know, a statistical model. But one thing that we both agree on is that in statistics, you find correlations, and the data scientists get excited when they find a correlation that they hadn't seen before, but they still have to work out what the causality is and what's the direction of the causality. And the reason why statisticians like her are really excited about AI is because it finds all sorts of correlations you didn't even know existed. And some of them aren't even real correlations. And even if you do find one that's real and you get confidence that it's real, it doesn't tell you the direction. So all of our applied mathematics and the physics and the mathematical models is about nailing down causalities that we've learned over the past however many centuries. So it's great that I think it's getting a lot of skill in other models because there's so much data that you can reduce that confidence interval. So it's very tight about what, it doesn't matter what the causality is. We believe that these things are correlated and that correlation stands. But when we have sparser data, when we go out into the climate region, I worry about depending on causality alone. On correlation alone, and that causality has to play a role because the correlations are so uncertain.
I have a slide that I sometimes use in talks, and it turns out that there's a very strong correlation between frequency of suicide by hanging and research funding.
And there's an entire website about false correlations, which is a lot of fun, by the way. Axe murders and Kool-Aid use.
So, John, I'm going to take real issue with this. You need to read the book by Judea Pearl on causal inference, and this will fix your notions of what's called Granger causal inference. And I have 2 papers on it.
There's also a correlation between people dying by falling out of wheelchairs and sale of potato chips in the US. All perfectly correlated.
Kelvin, why do you know this? Why do you know this? Oh.
Tell people stop eating potato chips.
I was a meteorologist, but right now I'm a business person in something called weather derivative. I think it is a business sector and we should not ignore. As a business sector, financial sector that has been grown pretty noticeably, and then right now being utilized quite a lot. What weather derivative actually needs is something you can measure the economic impact with pure weather variables. Yeah, so that's what actually weather derivative means. Now, weather derivative right now so far all focused on temperature, that kind of thing, in which we have weather station to measure. But going forward, there's a great need to actually cover something called a protection gap. I think Jeff mentioned about that, about insurance. And there has been, I think everybody probably have read, there has been a lot of loss. The loss increased a lot recent years, either due to climate change or due to climate change and then leading to certain events happen more or intensity or frequency, whatever, it doesn't really matter, but the loss actually increased. Now, when the loss increases, the insurance protection gap gets bigger, right? Now, insurance protection gap gets bigger, that can be a problem. It's a huge problem, yeah? Now, how are we going to strategically, and then even from societal perspective, right? And then solve that problem? It is very important, very important. And they're very important in the sense that how are we make those things insurable? Yeah. Without enough data, it's very difficult. First of all, you need the data to make it insurable. And secondly, it is because a business person and money is kind of all in the thought process. And they need the capital. Now, the entire global insurance capital is just only 5 trillion. Yeah. But the stock market combined is 100 trillion, and then bond market is another 130 trillion. So there's no that capital cannot access the risk. Why? Because we do not know how to represent the kind of impact with the pure weather variable, because the capital market cannot deal with somebody's car gets hit and we get hit, that kind of thing, that kind of thing. The capital market doesn't deal with it. That's an insurance company deal with it. But insurance companies only have this little capital. If a bunch of capital would be a lot of money, it cannot access the risk. So how we turn this kind of risk into investment vehicle and push the capital market is strategically important, not only for this country, but globally. Now, Now, actually, it's really important. Actually, a couple of weeks ago in Monte Carlo, we were talking about actually insurance capital and special gap. In Monte Carlo, in fact, that was actually a big event for the insurance and insurance industry. Think about it. I think this is where the derivative business and who have already offered parameterization, parameterize the solution based on temperature. That's where the station manufacturer. I'm thinking here, something called severe convective storm. Can be for the severe convective storm.
Can you get closer to the mic? Sorry, because online.
Represented well enough by the data which this project is going to offer. Yeah, that's going to solve huge problem, financially, economically. But it's also a big challenge so far, and I'm not even sure even kilometer scale is going to solve the problem. Is that kilometer scale really good enough? Now, today I saw a presentation by Dr. Sato, which is pretty kind of intriguing. And he showed that 1 point something kilometer versus 200 meter, and it's vastly different details, right? So what is actually needed? We do not know. And then what have we learned from the so-called massive scale modeling, numerical weather prediction model, that kind of thing? And then what's actually needed? What kind of modeling is needed in order to represent what kind of granularity? That kind of knowledge, I think, is probably good to have at the very beginning so that we know actually where we're heading and what we can expect. Yeah, so maybe, I do not know. I'm not quite sure whether a global scale, kilometer scale, kind of resolution global model is going to solve the problem. There may still have a room for a nesting. Yeah, right? Okay. And there may be, does AI solve the problem? I don't know. Honestly, I'm very skeptical. Yeah, so now if those results cannot be accomplished, a lot of the purpose get defeated, right? In the end. Yeah, because we just as a stakeholder for in this area, and somehow we need to get to the point in order we can commercialize the results. Yeah.
Okay, I think we got it. We got the.
Yeah, I guess
Great.
yeah, overall, we need to engage with stakeholders to find out what they need. Tapio?
I want to address the division between climate and weather models, and I think that will lead to an answer regarding the loss function question. So, of course, Lorenz had a distinction between climate and weather prediction, first kind, second kind prediction, and that was brought up already. But I think pragmatically, a more useful distinction for us here is weather models of the type you've heard about are verifiable on a useful time scale, and climate models are not in the same way. They will eventually be verifiable, but it's too late by then. And so that, I think, dictates how we use AI, among other tools, right? It's perfectly fine to have a black box AI model if you can probe it, verify it on a useful time scale, a few days or so. If it works well enough, many times we trust it, you'll be happy to base our weather decisions on that. We don't have that luxury in a climate setting. And I think that now affects how you deal with metrics, loss functions, benchmarks, and the like. There is a role for AI in climate models, a strong role. I just don't think it's the holistic learn everything about the climate system from data role. You have to focus on the pieces of the climate system that you can verify on reasonable timescales. And this is either that there are natural variations and the like that are large enough, or a verifiability in principle that you can go to a laboratory and measure that function that you have in your model and test if it's actually accurate. Every climate model has these functions right now, right? I mean, most prominently, I would say surface layer turbulence is represented by Money-Novikov similarity theory in every model I know. That is a physically reductive theory, but in the end, some people went out over wheat stubble in Kansas in the summer of 1968, measured these functions, and we used them in the Arctic. We used them when we model Mars or Titan, and they work. They're truly universal function. The reason is that, well, they were reduced to learning non-dimensional functions of non-dimensional groups. You had plausible belief that they're universal, But now you can probe the universality by going, not just measuring in Kansas, measuring in many other places. And that has been done for the last 50 some years. And we have developed great trust in those functions because they were verifiable in principle and have been verified in many contexts. There are limitations to that theory in some contexts, but it's by and large quite broadly applicable. The lesson to me is that you can use metrics and learn some functions where the climate system does you the favor naturally of sampling this space in which these functions live right now quite well. So this will tend to be fairly small scale functions, turbulent exchange between cloud and the environment, all sorts of things like that are probably well sampled in the present climate, won't look functionally different in a different climate, but that won't be true, say, for the height of clouds right now will be different from what it will be in a warmer climate. They'll get taller, right? So for that part, it doesn't work. And I think it becomes necessary to combine this domain knowledge, the physical knowledge with the AI in a judicious way that you use the physical theory, A, to allow generalization, but well, B, interpretability, but maybe most importantly, in the end, we have fairly little data for the climate system relative to the number of degrees of freedom we have. What it does for us is reduce the demands we play on data, that you don't have to learn all of physics we already know from data. And I think that's sort of both addressing climate versus weather on a pragmatic level, but also the metrics loss function question. It's a question of scale ultimately and what's sampled in the present climate.
Yeah, makes sense. Thank you, Tapio. Brian, I assume you might be bringing in some computational points of view. And after Brian, I want to bring in our stakeholders into the conversation. But go ahead.
Yeah, I'll be pretty quick because most of this goes over my head, and I, like John, my stack size is 1. I think I've been trying to think about this a little bit. I love the really cool stuff we're seeing on the AI models, but at least to my tiny stack size, they are predicated on needing to train them on the computational models first, right? Like we can't get an AI model at 1 kilometer until we have data at 1 kilometer to train them, which means that the first milestone is how do we get the system to do these 1 kilometer runs, after which we can use the AI models and get huge benefits in cost. So I think that that's what I'm taking from this is this stuff is really cool, but my God, this is a big problem. I want to consolidate to something I can understand and you know what we can focus on, because I think there's just too many degrees of freedom in this room of cool things to study. So for me, I'm going to try to say maybe we try to bring it back to where is the architecture that can do this and how do we get the resources for that and what's the strategy. But I welcome other opinions from the AI experts.
Like I said, it is true that most of almost all of the examples we've seen of current AI models are like trained on simulations, but not in every case. So particularly for models, say doing like nowcasting, for example, they've been trained more directly on observations at a kilometer scale. And I think my perspective is that in the AI weather modeling community is there's a lot of interest in training models directly on observations as well. So I think we'll see more of that in the future.
Great. Thank you so much for that. And I did want to bring in our stakeholders. I know some mentioned that maybe they felt a little out of place and we don't want that. And I want to mention that a lot of the comments were received before your session. And so just note that. But my question to you all is, you made the great comment, which was about how we need to engage with sort of the people in the middle that can communicate between the climate scientists and the farmers, let's say, and they are the stakeholder. And so they need this trusted advisor, or, you know, there are these people that they trust and they have established relationships with. And I've heard this from different communities as well. For example, if we're thinking about engaging with Indigenous groups and how do we, you know, engage with them on and understand their science and their Indigenous knowledge. And I'll mention as well with Francina Dominguez this past summer, we were at the Amazon rainforest and I was like, great, we can engage with Indigenous communities. And they were like, you can't just go into the Amazon and like go up to groups. So I'm just like, okay, how can I as a scientist make sure that my science is reaching the people that I'm trying to create a relationship with, and acknowledging that there's limitations on both sides in terms of time,
I mean, on my end, we are all very busy, and even my mom says I don't call her enough. So I don't have time to build relationships with all these groups, but I really want to have a relationship. So how can we do that? Is there a database of trusted advisors? Who are these people? And, how do we move beyond that statement, which is valuable, but how can we actually engage with these people and identify them? I don't know.
So while you're thinking about that, please come up to the mic. I want to challenge the other side, the flip side of that. Most of us in this room are scientists, and we're glad those of you who are representing the real world are here with us because it's important. But for those of us who are scientists, I would ask you to think about the following question. I'm going to pose it in a very provocative form intentionally because the whole goal is to have some robust conversation. And I'll say it this way. If we had to freeze research and focus our energy on communicating, would we achieve more outcome?
So I actually have been thinking about that time scale question that came up at the end of our session and just thinking about what is the right kind of timeline horizon to be thinking about. And it feels to me sort of like that 3 to 5, maybe 10-year horizon is the right space from a communication standpoint. It feels very real to me as a human being still to think about 5 years or 10 years down the road. 50 years, not so much. And I think, again, like it's been really interesting hearing all these discussions and just understanding that you're all wrestling with some of the uncertainties as it goes out there. And I think when you communicate that uncertainty, it all just becomes noise again, and you just like reduce any credibility in what you're working on. So I think that's sort of part of it. And I think engaging the intermediaries also in that right horizon timeline is important too. And then I guess, there's just a lot of like words you're all using. And I know if you were sitting, we do it too from the ag sector. What has been really interesting for me sitting in this room is like, wow, we just talk to ourselves and we assume everybody understands what we're saying, right?
Exactly.
And I think that my sector is guilty of it as well. And so I don't know, maybe it's just kind of listening to yourself too and just checking in and understanding, are we using the right terms? Are we using the terms that matter to the people that we're trying to read? Those kinds of things have been just kind of bubbling around in my head.
So I'm the state climatologist for Illinois, which means that about, well, any given day, depends on what happens. 30%, 40% of my job is being a climate scientist. The other part is it's an outreach, being the intermediary for a lot of people. So being in both worlds, trust is built by repeat engagement and genuine repeat engagement, which means that you're not coming from a need of, I want your data, thanks for that, but that it's constant, we're serving each other. Unfortunately, the academic model and most of the research scientist model runs counter to that. You work project to project, so the timelines don't match up. So what we need is to make sure that as scientists who aren't able to devote that time, because most folks in this room just simply aren't going to be able to devote that time needed. And so any kind of real engagement is going to be superficial. That's just, I think that's the reality of it. What we need to do is to make sure that we're collaborating with scientists who are in a position to be able to engage deeply. We can't do it all ourselves. And so what I like to do in my position is engage with the people who are in the science, like Christy, for example, who I'm just pointing to Christy because, my phone easier, who can think deeply about these issues and in ways that maybe transcend the individual problems of the stakeholders in Illinois, but then I can talk to Christy and get all of his brilliant ideas and figure out how that works for the people in Illinois. And I think that collaboration works really well. So investment in the fundamental science of the modeling, investment in the outreach and the applied part of stakeholder engagement is equally important. And I think that's how we get there. Also, last point is to Jean's point about talking to each other. It's great that they've come here. We need to go to people. So if all we're going to are AGU and AMS each year, we're not doing the community service. What's that? Yeah, well, SRI is happening in Chicago. We can put that, but no, the floodplain managers, the association, the green industry, municipal managers. These are communities that we can engage with, and just not even need to present, but just sitting in the audience, listening to how that world operates.
Yeah.
It's really a great way to figure out how our science can intersect. So that's just some thoughts.
Thank you. That's a good starting point. Reach out to state climatologists.
Peter Meismer, NVIDIA. You presented as if we need this intermediary to translate between, the source of truth and the commoners. Why? I mean, why can't we just make people, everybody, the farmers, the sailors, whoever is affected, why can't we make everybody just work with this data, right? How do you build trust? Well, how do you build trust in that gravity actually works? Well, I let things drop. I experience it myself. I do it over and over again myself. Sure, I can read a book and it says things fall down, but it's much more powerful to me if I observe it myself. So why not give people the ability to actually play with the world, with the climate, with everything themselves? And sure, there's lots of things that need to be fixed to make that happen, right? There's a huge amount of potential and danger that all the results are being misinterpreted, misunderstood, and whatnot. But that's a different problem. That's then one of the places where a lot of words can come into play, or a lot of AI can come into play. How do you translate the data that's being generated into something that's intelligible and understandable by everybody?
So I'm compelled to just respond to that. First off, just to, the relationship. So listening, and to Trent's point, being present, and it's okay to ask dumb questions. You don't have to understand, we don't have to understand everything that's being said today, and you don't have to understand everything about our world, but at least we can be in the same room and learn from one another. So I just wanted to endorse that. But kind of to your point about why can't we all be climate scientists, we actually love touching the lab coat is the way I've sort of put it, of scientists. So I've worked in the public sector for decades now, and every time a scientist had come with like an impossible question, we need more from you than you can give, we need you to do it on this time frame, my people have stepped up with great enthusiasm. So when we're like, one example was, it was the internet, the Array of Things project. It was a smart cities project, and we were asked to be a part of a NSF proposal. Could we get 16 communities? Again, impossible time frame where you're committing to something, but we need a letter of support. I had 16 communities in 3 days turn around and get a letter of support. So even if it's just a question, but if it's sincere that says we need your information, we need to work with you, we need to learn from you, it can go a long way. So that, again, that's why it's important for me to be here today.
Great. And just to follow up quickly, would you say that having a user interface to be able to access the data yourself and interact with it in a friendly way would be helpful to, let's say, your office or any other person can comment?
Yes, but that's limited by those. Even in my world, working with local governments, we have a planning agency. They lead on the scientific inquiries for us. So they're the ones managing the data. It's not that much. We don't do that much at the leadership level in local governments. We don't have the capacity for it. It feels like more work. So that's one caution there, is that here's a tool. It's really easy to use. It's unlikely, unless there's something at the other end of it that immediately solves a problem, or there's grant funding, again, everything on deadline here, it's not likely to just say, give us a really useful interface. Coming and talking about tools that we can use, coming to a conference that a gathering of our people would be helpful. Or if, again, sort of setting up a project that says, can we use your city as a test case for, a model for, that's a good way to engage, and then you have a story to tell.
Yeah, because a crisis is the absolute worst time to try to build relationships.
Oh,
What?
Someone has her hand up.
Oh,
Go ahead.
Just responding on some of this interface opportunities. I think, I don't know if you all remember, many years ago on Facebook, there was this game called Farmville, and we could all pretend we were farmers. I feel like, creating a way for people to turn some dials and simulate different things creates a little bit of control or agency, and it reinforces that message. So I think if it was just something like a game from a farmer or agricultural perspective, if they say, okay, well, here's the climate, projection next year, business as usual, what happens to your yield, doing some different things, what happens to your yield. And obviously it's not going to be 100% accurate, but if we can show them kind of that relative impacts, and engage with them in a way that allows them to play with some of those parameters and things you're all modeling and show how it impacts what's important to them, I think that there may be some value in that.
Yeah, great. I one thing that I wanted to point out in this room and also in the context of a lot of the things that were just raised is that we as scientists, are very much so tied to the funding. So in terms of the cycles that we have to respond to, I'm, NOAA maybe has a 50-year cycle that, maybe. But certainly what I operate on is much, much smaller. But the really nice thing, I think, in this room as well is that we have engagement from these big companies and we have engagement from, philanthropic. There's a lot of attention, I think, and that, I think, opens up the possibility for what we can do and how fast we can move as a society in terms of both saying, wow, if I were able to collaborate with a game developer on this new stuff that I have, wouldn't that be awesome? And you are kind of seeing that at the NSF, for example. They had a recent new collaborative AI geoscience call, for example. That was new. I thought that was great. But those types of engagements and those types of opportunities for, collaboration that are new are really exciting and also worth, I think, thinking about and reflecting on in terms of, okay, if I want to engage with Native communities in the Amazon, who do I need to talk to? And is there actually, is there a landscape for me to do that? And how would I connect those dots if I have the energy? And of course, everyone has limited time, but, maybe developing a game is worthwhile.
Before we give the floor to Kelvin, there's a comment online that we want to share.
Yeah, there were just a few folks replying to my question that was very poorly framed, as was noted. But I think, someone mentioned that there's no comprehensive list or database of the right people to reach, but of course, considering our networks is important. And I do want to acknowledge this is KJ now, so if you want to unmute yourself. But also mentioned that reaching out to the network and asking how people like them can help. And John, did you have your hand up earlier?
Yeah, I had my hand up earlier just to echo that point from KJ. So we've had various groups in the federal sector for decades. One being the Advisory Committee on Water Information that was under FACA. So for those who are not familiar with the federal government, it's a federal agency advisory committee where all meetings are open. So that group was spectacular because it was academics, federal agencies, stakeholders, private folks, consultants. It was this whole mixed bag, giving advice directly to the federal government. So that's one path if it's a federal perspective, which is in contrast with the guy from NVIDIA. I apologize, but when we're dealing with large infrastructure, we have challenges with regulatory processes, frankly. FERC relies on federal sector guidance and regulations. And we're frankly in conflict right now because, First Street Foundation came out with precipitation frequency estimates for, buildings and infrastructure in the Northeast in direct conflict with what's published by NOAA. So, who's your trusted partner is a very active question right now. To KJ's point, I would say, let's bring everybody to the table. So we have these notes in the Academy report we just released on modernizing maximum precipitation. And that's basically a big tent and everybody's invited to hear your voices and we'll shake something out with that. But I somewhat, frankly, disagree with give everything to everybody. That just doesn't work in large infrastructure.
And I will just jump in. Thank you for sharing this, and thank you, John, for elaborating on that so well. I am the marketing and communications person on the call, so of course I'm thinking about how you talk and reach different people who have many different priorities. Before I joined NCSA, I was at Columbia University working at the NSF-funded Northeast Big Data Innovation Hub there, and a lot of our work was trying to bring together really disparate people working on data science, whether they were in academia, industry, government sectors. It's very hard work, and it's generally not people's first priority. As you mentioned, you have to do the research, you have to do all of these other things. I think acknowledging those limitations, as John suggests, is correct, and being very strategic about what your goals are. If it's, giving tools to, farmers, that's great. But as Jean points out, some of them, that might not be something they're willing to engage with, or something that they only want to engage with at the level of the game. So as a communications professional, it always just really comes back down to knowing your audience and knowing, what your goals are at the end of the day. So thanks.
Thank you. Yeah, very quickly, I was just going to say half the battle is just showing up. And so Jean and Edith and other folks here showed up. They were willing to take the risk. I think we as a community here, a fairly small community, but a very important part of the community, can take as an action item building communication and linkages between the weather and the climate communities. I think that's very, very important, but also the stakeholder communities. And we could do that. We could take that as an action item. It could be very grassroots. And in fact, I think it's a lot better to be grassroots, to start going to each other's conferences and being welcomed. I think you all have done a fantastic job of welcoming Edith and Jean and other folks here who represent the stakeholder community. I think they feel probably a part of this group now, right? We got to be welcoming. But the thing is, we could create all kinds of formal structures. I'd say let's just start doing it. And it will grow. It'll grow organically. We should really take that as an action item, as an outcome from this thing. And you'd think that IPCC and all these other groups, they do that. They do engagements. But if you talk to the folks who are getting the data, they're saying, we're not getting what we need. We're not getting listened to. Well, let's fix that. We have it within our ability to fix that. So anyway, I know we're getting close to time. So.
Thank you very much. Okay, so I'm Yi Zhou. I'm at San Francisco State University. I come from the financial economics world, and my feeling is that right now there's very limited study in weather finance. And in terms of climate finance, the most popular way of extracting the climate finance information is to use earning call transcript and to use text analysis to extract keywords about the climate risk from those newspapers and earnings transcripts. So it will be very useful for economists to try to look at how this interesting weather and climate forecasting data, how this can be used in predicting the asset market returns and other corporate finance related issues. And so that's my feeling. There's a lot of directions can go on. We can talk about different time horizons, daily, weekly, monthly, and also seasonal and annual and more than 50 years and things like that. And also there's also sectors, different industries, and there's also geographic difference, right? There are some developing countries, developing regions, and my own research have found out that using the storm event database, you can actually predict the future change in stock price and credit risk, and fundamentals. And also this effect is very, very strong, even stronger for firms that are in trouble. So firms that are speculative firms. So this shows that there's quite a lot of heterogeneity in this kind of result, which might be interesting to us. So thank you very much.
We are at 3:18 p.m. Kelvin, should we take our last questions here? Go ahead, Brian.
So I'll be really quick. I just want to reiterate the points that were made here. For most scientists, NC View or a Jupyter notebook plot is pretty sophisticated. But if you want interactive visual engagement, the video game industry is really good at this. They make 3D things all the time that you can zoom around. We just got to think outside of the box, and that would really help engagement a lot. So.
All right, we're gonna take a break. I'll remind you, in terms of bridging cultures, remember there's a big difference between a spherical cow that radiates milk isotropically and dairy farms. That's the culture gap we're talking about here. Okay, we're gonna take a break till the bottom of the hour. And so get caffeinated, do what you need to do, and we'll be back here to talk about the pre-summit intensives. But thank you.
And feel free to continue submitting your comments. Thanks.
is the presentation of the pre-summit intensive summaries. So we'll go ahead and get started here. It's kind of like the 2-minute warning in football. It goes by so quickly.
Speakers, we only have one of the four.
Who's up first? Francina. Okay. Francina. So if all the speakers for the session would go ahead and come up to the front. So Maria, Andy, and Francina, there they come. All right. All right, great. Well, it's wonderful to see all the great interaction and exchange of ideas and so on here. So really glad to see that. So let's see, where's Andy Prine? Is Andy around? He may be in the washroom. So we got John, we're good to start. Okay. So co-chairing this session are Barb Helen, formerly with the Department of Energy, and also John Towns with NCSA. So we're going to go ahead and turn it over to them, and they'll monitor the incoming questions. And so we'll go ahead and get started. So Barb, over to you and John.
Thanks.
Is your mic on?
Thanks so much. As he mentioned.
It's not on. Her mic's not on, Obi.
Here you go. Try this one.
Okay, there we go.
Two.
You're important enough.
Yeah, that's right. As Kelvin said, this session, we're going to start out by sharing the information that we gathered prior to the summit at our pre-summit intensives. We had 4, one focused on, as you can expect, practitioners and stakeholders. Then we followed it with Earth system models, computational systems, and AI and ML. So we have the organizers for each of those pre-summit intensives here to give us a summary of what was discussed at the summit and what came out of it. So with that, we'll start with Francina.
Okay, so yes, we organized the pre-summer intensive for the practitioners, and this is with Frank Nutter, Trent Ford, and Kelvin Drogemeyer. And the goal here was to bring together practitioners from different sectors. As we just saw in the session, we tried to be as broad as possible, bringing agriculture, urban, water resources, insurance, reinsurance, and energy. And we met, this was May 13th, when we had the pre-summer intensive, and then we also had Google Forms. So this presentation is based on both the virtual and the Google Forms that we compiled. And you know, one of the things that we started with was which communities are most at risk. And of course, we know that the communities that lack the financial means or resources to adapt and protect themselves are those most at risk. And we heard about kind of outdoor workers in rural areas. There was discussion about the elderly. There was also a big discussion about the middle class, like the muddle in the middle that we cannot forget. And also a long discussion about not only communities, but systems such as the healthcare system or the ag system. So these are also vulnerable. And as we've seen today, the data that we provide to the practitioners, they don't use it raw. They have to pass it through, in general, additional models to get the variables, the output derived quantities that they need. So whether that be hydrology and hydraulics, like what we saw with John England, or techno-economic models, where's Dan for the energy systems, or CAP models. So that data goes through additional models, and they can use either kind of historical data, observations, reanalysis, or future projections, which is what we're here to work on today. So, and as we've seen a lot today, of course, particularly for the future climate projections, these are too coarse for them to take any action. So currently they do downscaling, so statistical or dynamical downscaling of the CMIP archive, of the CMIP data that they get. They also, like in the insurance and reinsurance industry, they use proxies. So SST for hail, we talked about that. And a topic that came in over and over again was uncertainty quantification. So this is vital across many domains, and we must address it. So, and I'll talk a little bit about that in a second. So uncertainty quantification and the need to downscale the data to the resolution where decisions are actually being made. In terms of what is the data that they require. So of course it varies by sector, and it also varies by like the ability of our models to actually represent it. So we can go from kind of the easiest data, I guess, or the one that has the least uncertainty, temperature, min, max, mean, wind speed, direction, heat waves, precipitation. We talked a lot today about duration, frequency, intensity, drought, but then there's all these really kind of difficult variables, I would say, when we go down to cloud cover, severe storms, ice accumulation, hail, which is super important. There was a ton of discussion about hail. So that's a very difficult variable for our current models to represent. And I put an asterisk as to derived quantities like floods and wildfires, which would not directly be output by our models. Okay, so broad consensus about kilometer scale. That's what the practitioners need. So kilometer scale and hourly. So even though we run our models and we could output, like just say like the CMIP archive could potentially be output at the hourly timescale. It's generally not, but we practitioners really do need hourly data. I think this was emphasized a lot for the energy sector, and I know for hydrology and hydraulics, they even want shorter timescales, but I think hourly is really important. So the output to be made available at the hourly timescale. Yeah, and then I think as Jeff said today, ideally, the next modeling system will resolve these critical types of meteorological phenomena, tornadoes, hail, ice storms, extreme winds, with the appropriate level of detail. So that's their goal, right, the idea. Okay. We've talked quite a bit about timescales today. And so this was another question that we asked, what is the timescale that you're interested in? So it ranged, as we saw today in the discussion, it was kind of mimicked in the intensive. So real-time hourly, let's say for like emergency type of response, daily, monthly for planning, and then kind of the furthest that I kind of input this 5 to 10 year horizon based on the discussion today. There was also discussion about the 20 to 30 year time scale, and really beyond this, from the people that we surveyed, they were not interested beyond that. Just the uncertainties are too large. However, there was talk about the regulatory framework that will likely require stress tests that may request for stress tests for like the 70-year horizon. So that was like a caveat there that it might, if regulatory framework could affect these timescales that they're interested in. Okay. The next idea that again came up again and again is uncertainty. So ensembles, and here we're used to thinking about like scenario uncertainty in terms of SSPs, climate response uncertainty in terms of like individual individual models, or like internal variability where we have
to address this, we use like ensemble members, but you have to think like a practitioner and know that beyond this, there's another level of uncertainty because this has to pass through a hydrology model, a hydraulics model, an energy model. So those models have their own associated uncertainties that just kind of blows this thing up in terms of the variables that they need, their derived quantities. So practitioners must deal with this added uncertainty. And we talked a lot about how to communicate this uncertainty in a transparent and usable way. So that this is a really important part of what we're building here. I think Kelvin at the end said a nice question, like what keeps you up at night? And I think a really interesting discussion followed. One of this was, okay, there's a lot of data that is not publicly available, either from the federal government or proprietary data, wind, solar, hail. So to try to make that available for the community. A lot of talk came from for-profit organizations entering this space and providing data without the transparency or proper quantification of uncertainty. So we need to be careful as to what are the kind of different players in this space whose motives might be more driven by profit. And related to this, democratization of the climate information. So to get it to the people who actually need it, and not only those with the financial means to be able to pay for it. So this was a really nice part of the discussion. And I think kind of to the point that Trent made a little bit earlier, and that Edith and Jane Brokish are alluded to ensure more seamless communication and collaboration between climate scientists and practitioners through repeat engagement. So not just now, but throughout the process. And again, we did talk about this quite a bit. We need to better communicate the facts, uncertainties, and potential implications of our results to ensure that this information is being acted upon. So yeah, I think that was most of the takeaways, and that was it. Thank you.
Andy's told you here what the Earth system modelers thought in their summoning.
Hello again, 3 times a charm. This is the last time you will see me today. So this is summarizing the Earth system modeling pre-intensive summits. We had 2 of those actually, and Francina, Ruby, and Maria Molina helped with those. So thank you all for your support there. And I really wanted to also thank all the people that were engaged in the summits. Like we had really fantastic discussions. So this is summarizing the summary that you can find on the webpage. So it's a summary of the summary. I will point to the summary at the end, so if you haven't seen this before. So we structured this in 3 different parts. The first one was what we know and agree on, like there's quotation marks, because of course, this is still up for debate. This is really to prime you the discussion here and to continue the discussion, to give you the summary. Then we talk about opportunities and open research questions and potential issues. So let's tackle one at a time, starting with the easy one, what we agree on, and you might already disagree on some of these points. But our community would benefit from more collaboration. Like what you see here is a figure from the Diamond 2 experiments that I already talked about earlier. There are more than 10 modeling systems now that contribute to this Diamond 2 experiment. So there's already a large amount of modeling systems. Many of these model developers are struggling with the same challenges. And there's, I think, a limited amount of collaboration here. And I think there could be really benefits to have more coordinated or better coordination between, or at least information exchange between the communities. The second one is there's benefits of going down to kilometer scale grid spacings. And of course, there are also drawbacks because they're expensive, but here it's really like we see that they're like the mesoscale processes. This is a nice example here. This is Hurricane Bill. as simulated by the GEOS-5 model, which is in the middle here. So you can see a 25-kilometer grid spacing, 3.5-kilometer grid spacing, and this is the observed field, the cloud field. You can clearly see there are benefits. This is also what Kelvin alluded to, like the numerical weather forecasting community made this step 10 years ago or longer and benefited a lot from these higher resolution models. So I think this is something we definitely can agree on as well, hopefully. Model requirements. So this is, I think, still something that we can debate about. So what are really the things that we want to do with these models? We had long debates about that. We wanted to come up with some more specific numbers here, especially for the next intensive that will focus on the hardware that John will talk about after me. And we basically surveyed the group that we gathered during the pre-intensive and asked what is the target grid spacing we should focus on. And you can see here in this distribution, I think this was a clear answer. 1 to 2 kilometers was what we were shooting for. And I think I heard this coming up quite a couple of times here. There's nothing magic about this, but this is a really good grid spacing where things start to get resolved quite robustly. Secondly, we asked what should be the throughput, so in simulated years per day. And you can see there's more bimodal distribution here. Some people were happy with 1 simulated year per day. So this is actually already what we could do in current climate supercomputing systems. But there was actually more consensus on something between 5 to 10 simulated years per day. And then the third pillar, and of course, all of these things are connected, was what should be the ensemble size. And there are 10 to 50 members was a good size that we should shoot for. And again, like we could have a discussion on that, but this is basically what we passed on to the next intensive. And then third one, the code structure. So you have to have a co-development effort here between the software and the hardware. And really having this from the very get-go is really important. Collaboration with the numerical weather forecasting community is really key. I think we heard this in the previous session already. We can learn a lot from NWP community, but also team up with them because they face very similar challenges than we do. And the public-private partnership, I think also Francina mentioned this in her talk, to co-develop protocols and these models is really important. How to do this efficiently is I think, more challenging, but I think we can agree on that there's definitely benefits in these partnerships. So those are the 4 themes that we came up with where we can agree on. Now moving on to the opportunities and research, open research questions. The opportunities, AI, we heard a lot about AI today. So AI is a big opportunity, I think, for us to speed up the modeling systems, but to also increase the accuracy, uncertainty quantification, but also working a lot with model outputs. So I think there's a lot of opportunity in this field. Enhanced model resolution. So again, like there are large benefits that we could harvest if we would have these modeling systems running at the speed that we need those and the ensemble sizes. Again, private-public partnerships, large opportunities there as well, but also unsure how to collaborate really efficiently in this space. I think this is something we have to figure out. Community building, like again, like working closer together, not only in the US, but really internationally, would be really beneficial. And the last one is the public and stakeholder integration. And this was the whole last session was focused on that. So basically really trying to, from the very beginning, think about user needs and trying to engage with users and make those systems as useful as possible. Research questions, like this balance between grid spacing and model complexity came up. And I think it's still not really clear where we should be in this space. So there's definitely research needs there. Validation, we talked a lot about this in the last session, which was nice to hear. So how do you validate those systems? How do you build stakeholder trust in your projections? Do we have the right metrics or not? So we had a nice discussion on that already. Coupling to other Earth system components, like the coupling is not trivial, and how to do this efficiently at the grid spacings that we want to run on is really difficult. Do we need new parameterizations? Do we have to, we probably want to improve the parameterizations that we have. especially, for example, shallow cumulus parameterizations. How do you simulate shallow cloud decks over the oceans? Like, this is big challenges that we're still facing at kilometer scales, unresolved processes that we don't resolve. The ensemble size and how we best sample uncertainties, and how we quantify uncertainties. So here AI can play a role again, but how to do that is not very clear at the moment. And then, of course, the computational efficiency and energy consumption. So we already heard from a couple of talks today, like 20 megawatts, 40 megawatts, we're heading towards a 100 megawatt machine. Like, those are mid-sized cities that we're talking about. So being aware of the energy consumption and the footprint of these calculations is really important as well. Last but not least, potential issues. And you see, I use this Venn diagram because you can see there are already some overlaps here. The energy consumption comes back in here again. So in Europe, for example, it's already quite clear where these exascale machines will be, probably in Scandinavia, where you have a lot of hydropower, renewable energy. So moving the systems into locations, or Iceland, where you have geothermal energy, where you can produce renewable or use renewable energies to power the systems. Still, like, they will have an environmental impact even in those regions. So we have to be really aware of that. How to best develop these models of the future. Like, we had a long discussions, like, do you want to rewrite the whole system? Do you want to rewrite parts of it? Do you use things like OpenACC? Do you compile systems onto these new machines? How you make sure that you don't have to do this every 5 years when you have a new machine coming up? Do you have to rewrite the whole code? So being aware of that and this is definitely a challenge that we will face. Balancing model complexity, grid spacing, on ensemble size, like how complex do we want to make these models? Like, if you go into, for example, simulating chemistry in the models, you can easily increase the computational demand by a factor of 10 or 100. So where do we want to be especially at the beginning of this project? What are we aiming for? Model validation, again, like we talked about this a lot. Here also, the availability of ground observations is a key issue. Like, for example, over ocean regions, but especially also in the global south, the observational data sets are really sparse. How do you validate, for example, your climate models over Africa? That's a big challenge. And those are the communities that are heaviest impacted already by climate change. And last but not least, what we are in here, the community that we want to build, how do we develop a framework that is supportive and broad and inclusive, but don't compromise efficiency? I think this is something we probably want to discuss also in the remaining time of this workshop. So these are the three themes. I will be done in a minute. That we talked about. I would be really eager to hear your thoughts, if you agree, disagree on what was presented here. The main aim was really to provide information across the different pre-intensives. So those topics are really, these intensives are connected, and the information has to, basically, there's an iterative process that you have to run through to be efficient here. This is the QR code for the summary. If you haven't looked at that, I think it's only 3 pages. It's a short read. It's a really, I think, condensed version of this pre-summit intensives that I wanted to present to you here in a couple of minutes. And of course, the next step is to start to have further conversations here. Thank you very much.
All right, thank you. All right, so next we're going to talk about translating. By the way, I'm John Schaub. Can you dig it? Right. Okay. And I'm not going to be as good with the iconography or animation as my colleagues here, but I did use DALL-E to make some pretty pictures. And so let's go here. This is the outline, very similar to the Venn diagram that Andy showed. And we'll start with stuff that we agree upon. And so what we know that we agree upon, or at least after a lot of discussion where we disagreed some, that we are, this part is just focused on translating the ESM model requirements that Andy went through in the previous presentation into a set of hardware requirements for a system that could satisfy those requirements. We're gathering the engineering requirements for the system. We are not saying whether it's a CPU or a GPU or custom or COTS. We're going to translate those requirements into hardware speeds and feeds, and then we're going to see where the difficulties lie. We're also not going to weigh in on AI versus physics-based climate model. It's not versus, it's and. And we have a discussion that's best left for the AI intensive plus the climate ESM experts. This is really back to the engineering requirements for a kilometer scale physics-based climate model. And there's a separate discussion into the requirements that are derived from the AI type models, which is a different machine. The atmospheric component is the dominant consumer of computational resources. We all agree that this is a coupled model. It's got atmosphere, land, ocean, ice, maybe trees, I don't know. But the simplicity, in order to get ourselves off the ground here, we need to simplify. We're taking the dominant consumer of resources and using it as a proxy, or at least set the upper bars for what the requirements are, and we'll bring the other stuff in later. So we have a straw man spreadsheet for the model requirements. I'm happy to share it with anybody who's interested. It's in Excel, and we keep on building it and making it more and more detailed as we gather information from the codes. All right, so let's go to the ESM model requirements. So this is the various things we have to collect from the ESM people. They talk about layers in the model, domain decomposition, step size as a function of resolution, things like that. So we talked to the code practitioners, so the people who actually do the screen code, and looked at the icon paper, and also talked to people who have been analyzing these codes for vendors that supply us. And we came down to, for simplicity, 10 variables, right order of magnitude. I was corrected that Scream has 16. It's okay, 10's close enough. In terms of levels, there was kind of a bifurcation. 100 levels seems to be typical across a lot of the codes, but there are reasons why if you go to cloud resolving, you might want to go to a lower mesosphere model. So, but that only doubles it. So what's a factor or two among friends, you know? So, then we got the horizontal resolution. So we're targeting that 1.25 kilometer model. And by the way, the step size scales as to the square of the resolution as opposed to the cube, which would be normal in CFD. And that's because the atmosphere is super thin. So in terms of ensemble size, Andy's survey said 10. But thanks to somebody told me no, but it really needs to be 100. But I can't tell you who they were because Chatham House rules. So, and then the production rate, we saw something on the order of 10 to 30 simulated years per day. When you see the spreadsheet, you'll see somebody else who can't be named came up with a calculator for if you have a certain ensemble size, this is how many your production rate needs to be. All right, so let's start with memory requirements. So step size, Scream does 20 seconds per simulated time step. When we looked at the red code back for Green Flash, it was 7 seconds per time step, 10 seconds. We're gonna round it right in the middle there. Step rate, so we're talking about at that 10 simulated time seconds. So this is the world that is being simulated. And in order to get to 10 simulated years per day, that's about 2.7 milliseconds per step. So that requires about 40 petabytes per second of global system bandwidth. And so if you want to just count up for like a typical GPU that's got 6 HBM stacks, you're going to need about 10,000 MPI ranks in order to hit that step rate. And that's just to aggregate enough global memory bandwidth. And that's assuming you're nearly 100% efficient in your use. But GPUs are pretty good at that, so we'll give it to them. And that's a 7 megawatt about machine for one ensemble. If you want to go to 100 simulated years per day, now we're starting to talk real business in terms of megawattage, but that's where we're at. So in terms of memory capacity assumptions, so we say we're going for this 10 simulated years per day, 125 levels. So, and you look at the global surface area of the planet, that means you're doing about 3 terabytes, so 4 to 8 kilobytes per column. So that's 3 terabytes total memory required. But with a 10,000 way domain decomposition, you're only consuming about 270 megabytes per MPI rank, which is ridiculously low if you think of the capacity of having 6 HBM stacks on your system. So we're severely, we need this many nodes only to get the memory bandwidth, and not for anything else. We don't need it for the flops, and we'll talk about communication. We only need it for the memory bandwidth, and we're greatly, severely underutilizing HBM stacks. And it's very similar to what the transition we went from DRAM sticks to HBM stacks. We ended up in this phase where we had too little memory capacity, but we got the memory bandwidth. Now you got to take a step beyond this somehow. This also, we can look at this. This corroborates our observations from the previous thing. This is a roofline plot for the screen code. Unsurprisingly, it is memory movement dominated. And, you know, you could do something like aggressive loop fusion to push up to the right for this roofline model, but it requires a ton of on-chip memory in order to do that kind of aggressive loop fusion or kernel fusion. We have 3D integrated caches in the market that are actually very close to that 250 megabytes that we need per chip in order to run this entirely out of the L3 cache. And the L3 cache has way more bandwidth than 6 HBM stacks does. So it's doable. Second thing is that you can run, we're assuming we can run chemistry concurrently with the die core, and we know we can do that, use spectral deferred correction. People have demonstrated that that's feasible. So communication, model assumption, we assumed based on the number of variables we had that it would be 20 halo exchanges by 10 variables per step. That would be 200 halo exchanges. Corroborated, the screen code does 255 per time step, so we're right in the right ballpark. We're going to 1 millisecond per time step at 10 simulated years per day. That means if you spend 20% of your time on unoverlapped communication, so we're not even the sophisticated, and you have a separate halo for each variable rather than aggregating the halos, which is another optimization that a lot of people do. You still only need about 50 gigabytes per second of injection bandwidth, and that's very achievable using off-the-shelf technologies. There's nothing, and because it's 18 megabytes per message, we started doing a log P model to see if the latency would mess us up, and you don't even need to worry about latency. So that means you could use Ethernet here if you wanted, and this is making the worst case assumptions in terms of inefficient communication. You know, every message not aggregated, and yeah, so on and so forth. And this is consistent again with, you know, the scaling the screen code, really good scalability because you're sending these huge, pretty big messages to your nearest neighbors. So lastly, I/O requirements. So this is hourly in terms of the simulation, the simulated Earth, not in terms of we're not going to dump it hourly on Frontier. This is the simulated Earth. It's hourly in that time zone, and we're doing 10 simulated years per day. So that's, you know, hourly for the surface temperature and such, 15 minutes for precipitation and wind events, and then your usual CMIC 6 deck protocols. So that means you have to have a usable ingest rate for your I/O of about 160 terabytes per second. So that is a little daunting, given that's like 5 times more than all of Frontier. But if you think of it from the standpoint of, well, how many SSDs or NVRAMs would I need for that? Yeah, from a hardware standpoint, it's very doable. The likely challenges are probably in the I/O software, the system software to manage the I/O, and that's consistently been the case with most of our supercomputers. So I don't see, you know, if we have more than one major challenge with building this machine, then we're kind of sunk. But it's starting to look like it's not a very interesting machine in some ways. You know, it really doesn't matter if I have a CPU or a GPU. It's the memory thing is the engineering challenge. I also can attribute, but very sharp profiler points out also that it can look like you're spending a lot of time in communications, but if you screw up that multiphysics coupler, it's going to look like you're spending 70% of the time in your communications just because of the sync between these components. The climate modelers talked about this. They said they're worried about it, but it doesn't keep them up at night. They've had enough experience wrangling this over the past 30 years that they say it's going to be hard, but it's not the thing that they're most concerned about. But it is noted, and we need to worry about it, and we need to collect information. So next, open steps and research questions. So in terms of hardware metrics, we've got the simulated years per day, IO requirements, communication model. We need to go back into the code though, and we need to create in the spreadsheet model, which I'm happy to share with you, we need to get more granular in attributing where the power is going. I just did a calculation for the HBM stacks, and so even though it's a 7 megawatt machine, it's 0.4 megawatts actually in the HBM stack, so it's not the loss leader. So we'll have to think cleverly about what the different design scenarios are to deal with this. We want to go back into the code and corroborate all these assumptions that went into the spreadsheet model. So we've got, the number of messages and the size. We got corroboration on that. We need to get corroboration, the total amount of memory movement necessary to support the model. We need to look at the load imbalance at SIG points. Need to talk with the rest of you, and I've gotten a lot of help. I haven't done this spreadsheet alone. I've gotten a lot of help from everybody in the topic 2 to refine this spreadsheet. We need to keep on talking and refining that. And then the last is there are potential code optimizations that get us out of this pickle here that could enable us to more fully utilize the capacity of these HBMs and reduce the amount of data movement back and forth. That includes aggressive loop fusion, which we've seen can reduce the bandwidth requirements by 10x, but it requires a massive on-chip cache. Or doing concurrent physics with the atmospheric chemistry, which is pairing something that's very memory intensive with something that's very compute intensive. So those are examples of things, but I'm sure the ESM people have lots of war stories to tell us other things, and we can go back and figure out what that impact is on the hardware requirements in order to support that optimization. Some optimizations fail because the hardware can't support it, and you end up being the same. So, all right, that's it for me. Thanks.
Lastly, we have Maria, who's going to talk about the artificial intelligence and machine learning pre-summit intensive.
Like Andy, this is the last time you'll be hearing from me today. So thanks for dealing with me. And I thought it was too predictable to use Dolly to make a figure for my slide, given that we're the AI pre-summit intensive. So I went to Paint and I made a nice old school figure. Huge thanks to the participants to this AI pre-summit intensive. I really learned a lot from you all, and I hope I did an okay job at capturing some of your comments. And huge thanks to Kelvin for trusting me to summarize this. And Kelvin said that if you have any issues with this presentation, take them to him. So I went ahead and summarized our thoughts into 4 different categories. First being what we know and generally agree on. Second being kilometer scale and AI community views, which at times are in somewhat of a bit of tension, at least depending on who you ask and some of the conversations that were had during our AI pre-summit intensive. There are also a number of opportunities and research questions that are outstanding regarding this kilometer scale modeling system and where AI would fit in it, and also some potential issues were identified that could be coming up on the horizon. So there were quite a few things that we agreed on in terms of and identified. And one of those key things was that community organization is needed. Amongst the participants of this AI pre-summit intensive, there were efforts that were raised and noted, like Destiny or Destination Earth, and also a number of operational modeling centers that were already either running data-driven models or very high resolution simulations. We heard earlier from Neural GCM, Stefan Hoyer, who presented a different approach that would be more hybrid, whereas other centers, again, taking a fully data-driven or fully physics-based approach. So we just felt that really we need to coordinate amongst each other and cooperate. We also found that and agreed that identifying stakeholder needs and placing those front and center is really important. Earlier, I had a discussion with someone who raised perhaps that we would need to take kilometer scale model output and then give that to stakeholders and have that go through an additional layer of modeling. And you heard Francina earlier in the presentation also identify that. So that's just another thought that I'm noting as we continue having discussions throughout this summit. And it was also noted that researchers are practitioners. in that we should think about how easy is this kilometer scale modeling system going to be, right? How usable can we make this so that people can actually pick it up and use it for their applications? And of course, who exactly are those people going to be is another thing we need to think about. Regarding what we generally agree on, there were points made that the efficiency of parameterization schemes is perhaps not a priority and that there's more potential for improving their accuracy. And it was also noted that replacing the dynamical core perhaps is not a place where we'd get the most benefit currently. Also noted was the need for observations at a similar scale. And we noted that we don't really have in situ observations in all places. And so when we're thinking about ethics and equity in terms of not only training data for AI systems, but even for validating a pure physics-based model and how it's performing in certain locations, ensuring that we're keeping that front and center and who's represented and who's not represented is important. And of course, AI can also help with determining where we need more sensors and perhaps where some can offer most value. Where we had a little bit of tension, that included whether we actually need to model at kilometer scale or whether AI could be used to downscale at kilometer scale. And there were raised questions regarding whether AI could actually generate convection at sub 25 kilometer or so grid spacing. There were also points made that an advantage of kilometer scale is that it can capture extremes, but it was also noted that currently several data-driven models that are pure data-driven can predict extremes rather skillfully, and these are currently being run operationally. And then lastly, there were also points made about that we keep raising that physics-informed frameworks or physics-informed neural networks are important, and incorporating physics in our systems are critically important. But of course, again, our data-driven NWP efforts are showing quite a lot of skill. Some of the opportunities and open research questions that came to the surface as we were all discussing during this pre-summit intensive included how well can AI-based models extrapolate to extremes, thinking about do physics-based scale dependencies also apply in fully data-driven models, also asking questions about whether predictability is different when we're thinking about AI models and how they can capture fastest growing modes and ensembles, and even what are the optimal number of ensemble members, which is of course an open question depending as well on even a physics-based model and the phenomena of interest. Some open research questions included, or these are also opportunities, whether, how can we efficiently calibrate existing parameterization schemes? The question about explicit generation of thunderstorms, if we're downscaling using AI, is that actually occurring skillfully? Thinking about pairing our AI-based ensembles with established data assimilation systems as well. And also the need for more empirical evidence regarding the need for physics-informed AI rather than simply stating that we need to incorporate physics into our machine learning models, also important. And of course, after our summit, we did have participants continue sending us some thoughts, and someone did note that AI can also be very useful for creating some sort of user interface where there could be interaction with data that's produced by a kilometer scale physics-based model. There could also be exploration and interpolation of these kilometer scale simulations. So potentially thinking about this in a framework where we'd run a physics-based kilometer scale model and then use AI to interpolate in between projections and so on. Some issues that were identified that we noted, these are just going to be 4. Perhaps there were more. You'd have to look at the summary, but the first one being that it's really difficult to make concrete decisions about AI and machine learning and where it fits in this kilometer scale model, right? Because any decisions we make today may be superseded because the speed that AI is moving at is just so fast. Also thinking about the timescales of relevance. So we've heard a number of different timescales, 5 to 10 years, longer than that or shorter than that. When can people make decisions with that information? And this is really important to nail down for our modeling efforts and for when we're thinking about how we're going to evaluate whether those model simulations are actually producing skillful results. Thinking about model validation and whether we need to completely reimagine how we would be validating such a system, and when is this kilometer scale model modeling effort successful? When has it succeeded? So another example of even thinking about the effort overall and evaluation of it. And then lastly, this has been mentioned already today, but thinking about how we store that data and then how we access it is really critical, not only for people in this room, but also for folks outside this room. And just really, how do we even access, right? Like downloading all of these kilometer scale simulations is perhaps not really reasonable for many people. And with that, I'll go ahead and end here. This is a QR code for the summary of our notes that provides more detail. And thanks again to the participants.
Yeah. Could we have our pre-summit intensive leaders coming back? So over the course of the day, you've heard a lot of information. Calvin set the stage early this morning. You've heard from the practitioners and stakeholders, and you've heard from the various Earth system modelers and models that are out there, and then you've heard the pre-summit intensive, and of course during that, John gave you a deep dive into the computational needs of the systems. And now it's time, you've heard from us, it's time for us to turn the tables, because this is your summit, as Calvin said, to have you give us some ideas of what questions we should be discussing during the breakout sessions tomorrow. And there you have two options. We have 45 minutes, I think, for discussion here, but there's also another Google Sheet, and the link is on the. Yeah, it's on there, so that you can submit, this afternoon, tonight, as you're thinking about it, early tomorrow morning, submit your thoughts of what we should be discussing in the breakout sessions, because the first session tomorrow will continue this discussion. So with that, I'll open it up for questions.
So, yeah, we'll open it up. I don't have anything in on the chat, so questions from the floor.
Yeah.
I got one for John.
Yeah.
So back in the green flash day, we were looking at one model with one run.
Yeah.
Not 100 runs.
Right.
And we came up with a limitation of about 20 million way parallelism.
Yeah.
Which, as I recall, was like a couple tens of thousands of chips at 14 nanometers.
Yep.
What are you talking about today? I mean, how many parts is this thing going to take? And how does that compare to, say, Frontier or Perlmutter or the machines we have today?
Yeah, so there's some things that are similar, some things that aren't. So some of the design choices that we made was because it was so far in the bandwidth bound zone, we said not even do SIMD, just do single issue, simplest core possible. And even though it was 20 million way parallel, we could pack a whole bunch of cores, even in that older process technology, onto a single chip, and a modest sized one at that. And we sacrificed a lot of on-chip floppage to get more on-chip memory, which at the time, we didn't have these 3D caches like they have today. And so we were able to get enough data reuse from that we could do aggressive loop fusion. That was what Schwabe did, was the aggressive loop fusion. And so we fast forward to today, it's actually a very similar number of chips. Part of that is because of the complexity of the cores we're dealing with if we do COTS. But if we went to like a ARM type solution, we could probably do this with a lot fewer parts. The only limiting factor now, though, is how much SRAM can you fit in each package? And that will actually be the determining factor of how much silicon surface area we got to field in order to deliver a machine that could do this.
So we thought that green flash would be $75 billion.
Yeah.
And draw 5 megawatts.
Yeah.
You said 7 megawatts.
Yeah.
How much does it cost to buy this thing?
No idea. Cost.
Come
There's
on,
cost.
come on, come on.
No, come on. There's power.
You know this. We weren't allowed to say $75 million.
So something else that's different today is that the leading edge nodes are crazy expensive, whereas what we were looking at, it was affordable to do, not a leading edge node. We were doing 45 actually for the one that we first.
Cell phone processor.
It was a cell phone processor. Yeah.
So do we need anything more than that now?
No, if you wanted to spin it yourself, I would say go with commercially supplied IP like ARM or Tensilica. We were using Tensilica, but Tensilica is gone, so ARM. So I'd say if you want to do it yourself, you'd use commercially supplied IP, but the companies like AMD and Intel and ARM are also offering a different solution, which is these chiplets, which you can even just buy these chips and they'll do assembly service for you.
So just like that was 2011 when we
Yeah.
wrote that paper.
Yeah.
And it was not technology that was limiting us.
No.
It was money.
It was money.
And you're just
Oh,
telling
an
me
assumption.
it's the same damn thing.
Well, okay, back then we still had Moore's Law. You know, people thought that we had Moore's Law in operation. We actually didn't, but we thought we did. And
They also thought we
people,
were nuts, but
well, that's something we should manage on the side.
Okay, well, this question's also for John, but with considerably less jargon, I hope. In any case, it has to do with the fact that my perception of the biggest roadblock to a really state-of-the-art system is actually none of what you talked about, but in fact, disk storage. Like, how do you store all the data that you're going to spew out of even a single 10-year run, let alone a 10-member ensemble? And this comes out of discussions with Peter Caldwell about how are we going to do a 10-year run of Scream on Frontier and not run out of space. And so it's like, I know that this is a problem. So tell me what your strategy is.
Yeah. Well, and it's actually worse than that. So we talked about using a physics-based model to train the 1 kilometer AI-based model, and the data output rates I was talking about are 100 times lower than what they need according to Karthik's presentation. So that training a model off of the data that's stored offline is completely out of the question. You'd have to train it while the code is running, never let it leave the system. But if you do decide to output it at those 160 terabytes per second rates, I will go and calculate how much storage capacity it would be. But that kind of a problem I consider to be a problem of money and not of technology.
Yeah, it's a problem of a lot of money.
Yeah, it's probably, we'll see. Yeah.
I think there's another dimension to that problem, which is important, which is if I were to say, what was the biggest single achievement of Diamond, which I think was a great achievement, and it was that Bjorn was able to get all of the models to put all of their a substantial set of outputs on the DKRZ server and have people work on the server on data analysis. And that was transformative, I know, for my students who worked with that data. And that's a model that I would think you would want to have here too. But it does mean you have to have all of that data, not only in storage, but you also have to have it able to be served to a community.
Yeah, talk about jargon. But anyways, there are things that we should discuss. I'll try to put that into the spreadsheet because actually, the storage is a commodity, and so we can calculate that out. But Barb always used to say during the exascale program is that you can buy more of X, but you can't buy back time, and so we have to hit these simulated years per day targets.
Okay.
Shall I go next? Okay. I think what we've heard a lot today about observations from various groups. And I really wanted to stress the importance of observations. I mean, one of the things we have heard variously, ERA 5 called observations and data, right? I would argue it's neither, right? It's a model. And actually, what I look at, which is precipitation, is quite poor from ERA 5, right? So if we're training AI models on ERA 5, we need to be worried because they're not going to give us good predictions for either weather or climate, right? So that's the first thing. I think the second thing, I mean, Andy knows about this, but, I've been involved in collecting a huge data set of hourly precipitation data, which we're updating at the moment across the world. And we've got like over 25,000 gauges. Of course, we don't have extensive coverage everywhere, right? But we do have like 30 years of data at least for most gauges now. Well, we will do when we update it by the last 10 years. There's a lot of other data out there as well, right? iMerge, there's other remote sensing data, and there's good
daily data sets as well that we can also use. So, maybe one of the things we should be thinking about as part of this collective effort is actually improving observational data sets that we need for evaluation. I think particularly, I don't know, I know a lot about precipitation, right? And I really do think that it's something that we don't understand well enough. And we don't predict well enough. So I think it would be very useful to have better precipitation data sets. The other thing we should be thinking about is what are the other observations that we might need to try and constrain our models when we get to these much higher resolutions. I don't know what those might be, but I think it's something as a community we should be thinking about. And there's low-cost sensors. There's all sorts of other things that we could be getting out there within the next year or so to actually help us evaluate some of these processes, right? So sorry, I've got a few points. Second point is land surface processes. Now, we haven't heard very much about that at all. I know Andy talked a little bit about what's used in the current global kilometer scale models, right? But a lot of these land surface models and hydrology in particular, which is something dear to my heart, they don't actually allow a lateral flow. They don't have routing. There's not enough feedback from soil moisture. We really need to think very carefully about the land surface processes and how they interact when we get to these very high resolutions. And it's not something we're doing well at the moment, right? So it's something we've kind of ignored in this meeting so far, but I think it's something really, really vital to get right. And it's really important. I mean, Sonia Sunavaratne has shown this years ago now, in terms of producing these big heat events and all sorts of other things, blocking events. It's really important, those land surface feedbacks. So we're not going to get those things right unless we actually get those land surface feedbacks right. And I think my final point is something that, just to reiterate something that Tim Palmer said earlier, right? So we can't just downscale with AI. Of course, we can downscale with AI, and they're doing that with climate models now as well at the UK Met Office, and it works really well. It's able to sort of be trained to reproduce patterns for data, right? But what's really important is that we actually reproduce some of these. It's that feedback from these convective processes to the large scale that actually matters for getting the future projections right. And I think Andy gave a really good demonstration of this in a figure that he showed in his talk earlier with a paper that's, I think, in review at the moment, Andy, where they've improved the tropical convection over particularly the Indonesian region, it seemed, where the MJO starts. And I think there's some really, really key connections in this area to the mid-latitudes that actually we're not capturing well in weather forecast models actually at the moment, really. We're not capturing them well in climate models. And it was interesting in that figure that you could see that there was more structure in the mid-latitude clouds as well, perhaps from that improvement in the tropical convection. So I think there's a whole raft of things that we really need to be thinking about within this space.
Does anyone want to speak?
I can add, yeah. Do you want to add anything?
No.
Yeah, thank you so much for those comments. I mean, they're excellent points. I'll add really quickly that you mentioned ERA5 being used quite often as if it were observations, and we know that it's indeed been post-processed or assimilated, et cetera. But I'll mention it, the motivation for using ERA5 is because it's already so neatly packaged on a grid. You have it, extended back to 1940 now, and so it works. Go ahead. Did you?
No. I was just going to say, I mean, don't get me wrong. I think the AI advances is absolutely amazing, right? It's so exciting. And I think there's a hell of a lot we can do with it, but it's just a case of really thinking about what data sets we use. I agree. Everybody uses ERA5, right?
Yeah.
And everybody uses MSWEP and other gridded data sets, but it doesn't mean they're real. And I think we just need to be cognizant of that.
Of course, yeah, no, most certainly. And I'll add, and so we could think about how we process our observational data sets to make them easier for people to use. But I'll add, observational data sets themselves also have limitations, right? We can't always treat observations as, we need to be careful about the uncertainties associated with them as well, and any potential issues. Even for remote sensing, oftentimes it gets raised to me that, oh, we have a lack of in situ observations in a certain region, but we can just use remote sensing for that. But oftentimes the calibration, there's issues with that, and then sometimes even geolocation over certain terrain, or depending on the or parallax issues. So it's just there's no perfect answer. And I think for this effort, in my opinion, we would want to be very targeted with our goals because we also can't do everything. And so what is it that we should focus our efforts on? Should we be improving observations to improve AI, or should we be focused on the kilometer scale modeling system? And I don't, yeah, I'm just thinking out loud here, but great points, and thank you.
Any other comments?
I'm going to comment on the earlier guy. So it's $13.5 million per day.
It's expensive.
Yeah.
Go ahead.
Okay, less of a comment and more of a question. So even if you go to kilometer scale resolution, you're still not resolving everything like microphysics, aerosols. So you still have to make choices about parameterizations. And if we're building a big climate computer, we've heard about how many ensembles, how many years, how many versions of the model. Is the idea that everything is going to go into one version of the model for which the hardware is purpose built, or is the idea still that we're going to have a number of different models that also sample structural uncertainty? So I don't know what's the idea here. I've only sort of heard about the ideal model, the one ideal model we're going to build.
I think this is a discussion we should
Yeah.
have to have in this room. That's a great topic for the breakout.
Right, yeah. Write that down on your.
So I think you heard me. Like, this is a discussion we have to have. This is a good topic for the breakouts. Yeah.
Yeah, I like to think Everett just left because he knows I'm going to be a little pessimistic. I think for the hardware, I'm skeptical that we can achieve this. You mentioned 2.7 microseconds per step. While you were talking, I ran a ping pong benchmark for an 18 megabyte message, and it's 750 milliseconds. So problem is, you don't just have one communication neighbor, you've got multiple on these grids. So that's already going to be a lot of time in communication. Now, you said what's a factor of 2 or 3 between friends, so maybe we're still in the game, but I just think we have to have a little bit of a counterbalance to the optimistic projections and look at a realistic one as well. So.
Yeah, I agree. That's why we need to go back and analyze the code and see how much time is actually spent. But I will stand by a log P model. It was fairly pessimistic as far as log P models are concerned. That 18 megs per message didn't involve any aggregation of the messages across the time step. We're assuming no collectives. I asked about collectives and they said only at the end. So.
Okay, thank you. So this is also a hardware related question. I'm from the hardware community, so I'm curious to know the real computational needs or requirements. Is there a upper bound for the requirement for computing? For example, at the end of the day, that's the only resolution we need. That's the only length of simulation we need. That's the only assemble we need. If there is an upper bound, how much are we still far from that? And if there is no upper bound, we don't have a target then. Does it make sense if we just revolutionize the entire computing stack? I guess my biggest question is there an upper bound for the computational need, and how far are we still from that?
I'm not sure. We're going to instrument a real code to see if our model assumptions play out when we actually have the codes instrumented. So,
for example, the growth of the computational challenge comes from the finer resolution, the longer simulation.
So are you asking how far beyond 1 kilometer will we ultimately need to go?
Yes. And then based on
so that's back to
there
him.
is an upper bound for the computation, right? It's not like the AI model, they're growing infinitely, but for this, is the need growing infinitely?
Yeah, like there is no upper bound. I think this is like, you can go down the rabbit hole. Like NICAM ran 250 meters globally. And of course, like you want to go down to 20 meters, then you have tornadoes in your simulation. Like, and you can go to DNS, direct numerical simulations, to do microphysics. Like this will continue into the future. Like what we're setting here as a target, I think this is really important that we decide, like, this is what we want to do now in the near future. And this is a system where we can do science on, which is meaningful and answers important questions. Like otherwise we get into this rabbit hole, like let's wait until we have a computer with 200 meters and 100 meters.
Yeah. If it was just getting linearly better as you increase the resolution, then it'd be like, yeah, well, we'll just go as far as we can and we'll stop there until the next machine comes along. But in this case, they're making the case that at a kilometer scale, something transformational occurs. So it's worth it to make it at least that far. And it may be that you go beyond that, but the transformation that happens when you're resolving individual clouds makes it more than just getting a linearly better resolution.
And I think the urgency of the problem that we're trying to address we can't go into a rabbit hole. We need to answer questions that are concrete for people in the coming years. So.
Okay, got it.
And I think that's an important point. I mean, we're trying to accomplish a certain amount of things with it. You could go to the microphysics if you want, right? But that's not required to accomplish the goals that we've laid out.
So in
The goals are important.
reality, more practically, there is something that, okay, this is good enough so far.
It's a transition point
Okay.
when you're able to resolve the clouds.
Okay, and then we just, so far, we want to analyze that point and see how far we're from there.
Yeah.
Okay, got it.
Okay. So I'm Estela Suarez, I'm HPC system architect, and I've tried to listen all the discussions this morning and now in the afternoon. And I've seen, maybe it's my perception, but a little bit of a contradiction. So very early in the morning, it was said that the codes are there, but the machine to run these codes properly is missing. Now, when I hear the talk from Jon before, it seems like the machine that is needed is not really something too exotic. So it seems to be, okay, more memory bandwidth, right? But otherwise not something out of this planet. So my first question, is this perception correct, or did I maybe misunderstand the discussion? And the other question is to regards to the model that you presented, Jon. How much is this variable depending on the different models that have been discussed? And in particular, when you compare from the physics-based models and the AI models, I would expect that the requirements towards the machine are very different. So
we're going to have to do a lot more work to figure out what the requirements for the AI models, but I mean, we're talking about different precision. The training is got a completely different communication pattern. We hadn't even cracked that yet. So, but I'd probably start with talking to the people who are already doing the AI weather models at Google and stuff to sort through the details of that. When it comes, I'm not sure if it's too much of a contradiction. They have machines that are capable of doing one simulated year per day. I mean, not machines, codes, plus machines that can do one simulated year per day. If we want to push it by a factor of 10, the limiting step is how many HBM stacks you have access to. And we looked at the other features that you need to hit that number, and they don't look completely out of place from the kinds of technologies that we have available. Now, integrating them together, everybody knows fielding a system is a whole nother ball of wax. But if you talk about it from strictly the speeds and feeds, it's that we have too much HBM capacity for the amount of occupancy that this code requires. And that's the general challenge, is that we need more bandwidth, and in order to, we need more bandwidth. And we might need latency hiding, which is, by the way, another thing that we have not examined yet. But when you get a very tiny piece of problem, like a GPU chomping on a 256 megabyte problem, might not be enough work to keep it busy, but talk to my GPU friends, they say, oh, we got some tricks up our sleeve. And so I want to see what those tricks are, and let's see how it goes.
Okay, thank you.
Maybe just a quick comment on the soft. Like, I think the models are not ready either. Like all of the US models, for example, none of them are coupled to the ocean at the moment. So there's like the land. I fully agree with Haley. The land, like there's rope in the ice. Like you have to put a lot of effort in the modeling systems as well to get to this point where we say this is a good modeling system to do climate projection.
Yeah, I agree with that. So again, we're talking about straw men here. But the straw men say it's not completely ridiculous. You know, it's not like sending a human to Venus or something, but at the same time, so we could see a path, but it's not there yet by any means. Yeah.
Okay, thank you.
Hi, my name is Udit, and similar to Callie earlier, I'm from more of a computer architecture and systems and hardware background. And I think one of the things that I noticed earlier in the day was a discussion on how there's a lot of heterogeneity and diversity and kind of ongoing flux of what these models look like, whether it's on the physics side or on the ML side or some sort of hybrid in between. And from a systems and hardware perspective, that makes me really weary in terms of the balance between general purpose and specialized architectures. And I'm curious if one way to think about this is to do a rough comparison of what makes this domain similar or different to other domains or other physical simulations, or how ML is being used in other application domains. And then kind of focus our attention on the vectors that are the most dissimilar, so that we're not trying to re-engineer or engineer in parallel similar optimizations than what's already being done in the broader community. And it sounds like the memory bandwidth and capacity aspects are one important vector there, but I'm curious, are there other aspects that you can start to foresee that kind of come up in that area, or?
Well, definitely, we're seeing a lot more 3D integration because everybody wants more memory capacity on chip. There's a crisis in DRAM now that's not just affecting us, it's affecting the AI marketplace. And so there's going to be a lot of force behind having a faster cycle time cell that has DRAM densities, and that would be a game changer for us too. They have direct inter-SM messaging now, so to lower the overhead, so you don't have to MPI everything if that became an issue. But at the same time, talking about a specialized system here, it isn't, the compute elements aren't the issue, aren't implicated yet as an issue. So it isn't really that specialized a system. We're still having fairly general purposed elements, but different ratios of them to achieve this target. Now the storage is storage is a lot more expensive than I was expecting, but I haven't done that calculation yet.
So I have multiple points and multiple comments and questions. So first of all, I think we should stop looking at exclusively looking at performance. So the simulated years per day, great metric, but it's a constraint. So we shouldn't be slower than one simulated year per day. And I guess that's probably even sufficient. So I don't see the reason to go to 10, because if I have one SYPD, I can run an single ensemble member in about a month on the computer for a 30-year study. So that, to my friends, seems sufficient. Then the question is really, should we optimize for cost under that constraint of the SYPD? Because there's always a trade-off between the two. And I've not heard in cost, I mean, in terms of energy, on capital costs. So there are various cost metrics that we can employ. So I'm missing this a little bit in the discussion. Then an extension of this is John, you kept saying we're going to benchmark this, but we've already benchmarked it just for the non-Berkeley code, so for the ICANN code. And so
we want to get more than one sample point.
Yeah, exactly. Yeah. So it would be good to work this in somehow, because we have a lot of data about this. We have absolutely accurate counts. So then the second point is the data. Well, the data is very expensive, I agree. But if we would not compress image and video data, our data centers would be dead. So we just need to learn how to compress this data. Today, the compression methods in climate and weather are a total joke. Sorry. But they are, but they're a complete joke. So we know already how to compress this stuff better. We just need to figure out a cost function again, right? So that's our unfortunate problem. We need to understand whether it's good or bad. Well, for JPEG images and videos, we have a pretty good cost function. We look at it and we think, we see if it looks good, and that's our cost function. Right now, that's as far as it gets with meteorologists as well. They look at the fields and they say it's good, but that doesn't satisfy me. So that again gets us back to the cost function. So then actually a question in Maria, in your talk, you mentioned physics driven or physics.
Go ahead.
Yes, some physics constrained AI models.
Physics, yeah, physics informed.
Physics informed AI models, yes, PINs, yes. So this got me to an internal conflict where I'm not fully sure if we should. It sounds like you want to put the AI in the driver's seat.
And here I'm not sure about this. So we should have a discussion who's in the driver's seat, because it's pretty clear that we need to combine AI and simulation to some extent, or physics to some extent. And now should the AI be the driver, or should the physics be the driver? Right? So that was a little bit, it's a discussion we need to have at some point.
Yeah, that's a great point. And I'll note that our AI pre-summit intensive was not originally planned. So we felt that AI actually touched so many different aspects of our system modeling that perhaps it was better left to have it just come up organically in some of the different breakouts for our system modeling, for HPC, and for even stakeholder engagement. But given how much it came up in these discussions and people wanted to talk about it more, and so we decided to have an AI pre-summit intensive. And so during that time, folks raised different things. And so we really do need to clarify what exactly would be the role that AI would play, or but acknowledging that that's a really tough conversation to have because of how quickly AI evolves and moves, and things can look very different in a year. So I don't know. I think it's a really tough question, and I'm looking forward to more discussions tomorrow with our breakout group where we're going to have our system modeling and AI together. Go ahead.
So we have an overarching breakout group.
Yeah.
So the AI group is also ESM.
Yeah. So I do want to address a few things. Cost, we haven't brought into it yet because it's among one of the most difficult things to calculate because there's price and there's cost. GPU on the street is $20,000. I doubt cost that much to produce it. In fact, we know that it doesn't cost that much to produce it. So, so in terms of value engineering this machine, I'll give you a couple of data points to think about. One is, yes, definitely agree. The compression is a thing. MPEG, though, creates artifacts that are systematic, which will really pollute your results. So we need to
use MPEG.
Yeah, sure. But somebody in this room who I cannot attribute because of Chatham House rules pointed out that you could go with half precision, you would be fine. So that's a right off the bat, order of magnitude. Yeah, it's 2x. Yeah. So
not an order of magnitude.
No. Divide by 8. So you go, you put out some of these quantities as okay, so it's like 4x, but still, there's a lot that could be done there. Didn't want to engineer a solution.
That's what we were doing today. That's the grid format that usually stores it in 16-bit.
No, so we didn't want to engineer today. We wanted to find out what's the tough problem so that we concentrate on the tough problems first. I will point out if we go back, if we dial it back to 1 simulated year per day, we're still underutilizing memory by a large factor. The memory capacity is sitting there. We're underutilizing the flop horsepower of these things by a large factor. It's just sitting there consuming power. And worse yet, no supercomputing center that I'm aware of allows a job to run for more than 24 hours. Because there will be 100% chance of failure and your maintenance windows will stink. So 10 simulated years per day, they want 10 simulated years as the target. If we can't get it to run in a day, then it's impractical from an operation standpoint for a supercomputing center. So 10 is the right number, I believe.
Wait, fundamentally disagree, because most of those are run in multiple pieces because you checkpoint restart, you can restart from any field that you have output. Exactly. I mean, come on. No. You don't need to run a single job before the whole simulation campaign. You almost never do this because your machine is not up for that long, especially for these very large runs. The Blue Marble was run in probably 50 steps.
I think a 10-day run is kind of tough. Anyways, lots of underutilized if we want to tackle this problem of cost engineering, then it's still a problem of this imbalance, even with 1 simulated year per day. It's really not solving the problem.
I don't buy the underutilization, but I'll yield.
Yeah.
All right, so now I realize I've made a mistake. First mistake was being in line after Torsten asked his questions and made his points. There's no way to compete with that. The second is I think I need to give John a tutorial on how proper run computing centers can do sustained performance over more than 24 hours. So we'll do that offline. My question is, and maybe I'm not understanding the structure of the workshop, is I'm missing what the use scenarios are that we want to define. So I got the idea, yes, we're going to have a computer. It's going to do fantastic climate simulation, maybe more than one, but most things right now are looking at one single climate simulation. And it's not clear to me how those are going to be used. So a use case that I was thinking of is, okay, we do 10,000 year climate simulation or 1,000 year climate simulation. We have that set, and then you'd want to go see what can I do to mitigate the end results or speed up the mitigation. So you come up with some idea, like you're going to spray the atmosphere or you're going to sequester all your carbon, and then you can start that maybe in 2 years, and then you want to rerun the climate simulation with your mitigations in place for 100 years or whatever it happens to be. But you do that many, many times. And I'm not sure I understand how the interaction of the massive climate simulation people want to run with the years of simulated information and scale and size, and how that interacts with the other ways that we would want use cases to be defined for this system, because it has to be used for multiple things, not just the one climate simulation. So if that's going to occur some other time, that's great, but I don't understand what the use cases are at the moment. And you don't have to answer if I didn't do a good job like Torsten in answering and asking my question. That's fine too. So
I'm just taking the input from the climate modelers, and they say how large the ensemble size is and how quickly they need that turned around in order for it to be practical. So I'm just taking it from, I'm taking them at face value that for the a 5 to 10 year climate target, that this is how fast they want things turned around.
Right, and how many times do they want to turn around?
And how many times they want to turn around
and things like that.
Exactly. So it's not upon me, unlike Torsten, it's not upon me to tell them that the answer should be one simulated year per day. I'm taking their input at face value.
Sure, okay, but maybe sometime there'll be some ideas about how the interactions of all the different uses that could go on turn into the specifications for a full system or a complete system. You do. Okay, thank you.
I guess also I want to say perhaps that we've been approaching this more from an adaptations than from a mitigation perspective. So, and that's, I guess, just how we've thought about this. So the use would be for adaptation. I don't know. Anyway, so yeah.
I haven't got as big a list as Hurley, but I've got a couple of things. One is actually, if I was going to bite my tongue on this, but if we're the community that's trying to take these things forward, then we could try and be more accurate in our language. So 1 kilometre grid length isn't 1 kilometre resolution, and 1 kilometre grid length doesn't resolve clouds. Just a fact. So we might go down to those scales and we might capture some things that are quite good, and we might get our scale interactions, but we're not resolving individual clouds. There's nothing magical, as we've already said, about 1 kilometre. 3 might be fine. So we can be pragmatic on those. We've seen that in NWP. We know that you can run at 4 or 1 and it sort of gets a bit better. You switch deep convection off, so you're explicitly representing it. So we can be pragmatic in that space. I think my main question, and I think maybe it was probably I think the answer is probably that's for debate, but it was like that last point. It was almost the same as the last point, but maybe slightly specifically. The question we're going to answer is going to determine the complexity of the simulations that we want to do. And we've been going round without, and I don't know where these numbers have come from, but yeah, if we are doing the carbon cycle, we talked about it's for mitigation. And so we've got drivers in that space. Do we need a coupled ocean? Are we doing a coupled ocean? Why do we need a coupled ocean if we don't, but before we define that question and we really focus down, and I think it's probably through the debates through the week that we'll do this, we don't really know what components we need in the model and how we're going to run it, how long we're going to run it. Because if it's for mitigation, we don't need so long runs. So if you're doing 100 years, we heard about paleo earlier and how that's one of the big. So Tim suggested quite rightly, I believe, that the most important reason for running at these higher resolutions in our global models is to tackle long-standing biases that we haven't been able to deal with in the global climate circulation when we've been doing that. If that's what we're trying to do, then we're going to have to tune these models in the same models that have got those long-standing biases in, which are fully coupled, at least relatively complex physical climate models. So through this week, I'm hoping we're going to define what these simulations are going to be so we understand how complex they need to be. But if that's a bias we're tackling, we see these in the CMIP-like simulations, of course.
All right, John.
Yeah, I want to interrupt. I've been trying to get actually a comment from online from one of our remote participants. John England indicated, as a stakeholder, integrating actual observations and improving the surface observations are critical in strategizing, modeling hardware and software frameworks. A perfect example is what extreme precipitation and rainfall we see in MRMRS that is completely missed by the limited 15-minute and hourly surface observations in the US. And I don't know, John, if you want to expand on that, if we haven't waited too long to get your comment in. I can't see the participant list, so I don't know.
Well, does anybody want to answer?
I don't know if anyone wants to speak to that.
He's talking about the MRMS radar data set.
Yeah.
Right?
Yeah, our observation, even in the US, we have a very dense gauge system. We don't capture those really intense peak rainfall. I think, Haley, you had a similar study in the UK showing same things.
Do you want me to make a comment? So we did a study a while ago looking at a comparison of radar data for Germany and the UK actually against gauge data. At hourly, actually, it wasn't 15 minutes. You'd miss even more at 15 minutes, I reckon. But I think only 15% of extreme, say top, I can't remember what we looked at, but say it was like 95th percentile events or something, wet events, were picked up by the gauges. So it's staggering how much is missed, but then, you know, they're really localized events. We know that. That's why we're interested in high resolution. So, yeah.
Yeah.
Okay, I'll save my stakeholder comments for tomorrow in the breakouts, but just a general comment. This, it may be really obvious to everybody, so I apologize if it is, but I feel like we're dancing around the topic, and I'm just going to say it very plainly that when we're talking about an opportunity to again think about the intersection between weather and climate. We're really trying to solve a climate problem, but we're running models where we do weather and have done for quite a while. And I just want to encourage everybody in their breakouts to be thinking about this all the time. And I'm not saying we're going to necessarily break down all the barriers that have led to us really never being able to put those two things together cleanly or without a lot of difficulty and working with legacy systems, but we're sort of in a blank paper state right here. We can be thinking about doing some things, leaning into it. Again, not to support the weather community, that's what I'm saying, but to learn from the weather community. And the one thing I think that's a lot of things I've heard today, that we have the frameworks to do this in weather, which is called data assimilation. And that is a Bayesian problem, that is a machine learning problem. So all I wanted to say was, as we're going through it, two things, think about that at every step of the way. I think we'd be remiss not to, culturally from a use case, and that's what I'll be bringing to the table tomorrow. But also from an infrastructure standpoint, because I don't know if this is still a problem, it may not be, I haven't been that close to it the last few years, but I've seen in my career models that were built to run climate models that really stunk at doing weather problems that included data simulation, for example. So that's just something to think about in the architecture part of it.
Time, or else running out of time. Yeah, so in this sort of use case category, and that was a nice comment there too. You know, if we are trying to get to the point of running climate projections, 30, 40-year climate projections, we know from experience, it takes a long time, a lot of integrations to get a good climate model. To build CSM, it took us 260 or 270, 50 to 100-year simulations to get something we were confident with. And, you know, we're hoping that as we go to climate scale, we're going to resolve these biases, as John pointed out, and maybe features are just going to show up and work out really well, but we really have never done this yet, right? We've only had maybe 10 years maximum. We've never gone to even be able to assess an ENSO. So we just don't know where we're going to get. And so it could be easier or it could be way harder. And so we need the 10 years per day if we're going to have any chance of doing that. If we have to scale back to 1 year per day, we'd never be able to prove that we can get a good ENSO. So that's maybe just something to keep in mind as we go forward.
One more from
yeah.
So I want to go back to the politics for a moment, because I find myself thinking we're doing what the old joke says about bringing a knife to a gunfight. So if you think about ITER, the International Fusion Project, The official price tag of ITER is 28 billion. The actual cost is probably more like 50 to 60. And we're still a decade away before we hope to see ignition. And those are big projects compared to what we're talking about, but they're small compared to major scale initiatives, right? I mean, the US dropped $1 trillion on the COVID pandemic. So the question, I'll go back to politics again, is I'll say it this way. I actually don't think the science matters. I mean, and I say that to be provocative. It really does. We got to get it right. Don't misunderstand. But compared to making a case and going back to engaging users and real humans in a way that they see the compelling reason for investment, that's the real hurdle, folks. Because given money, the problems John's talking about, they can be fixed. You drop $1 billion here, $1 billion there, they're solved, right? They're interesting problems, but you can fix them with money. But you got to get money to be able to do those things and to marshal the talent. So how do we tell this story in a way that engages people, that they say, my God, we got to do this? That to me is the overarching question. And I'll climb off my soapbox.
I just wanted to make a comment. The person before Dan who commented about the amount of iterative science that has to happen. That's why you have to save the data, and the access rates to that data need to be sufficient for that kind of science, because otherwise you're just doing a computational experiment, right? Not science. So that's my caution, is think about the data, because that's what really matters.
Right. Excellent. Well, let me ask you to thank all the folks in this session. It was fabulous. Really great discussion, great provocative questions. And I'm going to try to do a quick summary. But Tim Palmer, I think, is in his jammies right now. It's 11 o'clock where he's at. And Tim, we're not going to turn your video on. Thank you very much, please. But we've talked a lot about uncertainty quantification, and Tim, of course, he's just an amazing force of nature in how he puts things together and explains things, and he's going to talk to us for a little bit on why models are uncertain and how this uncertainty can best be quantified. So, Tim, welcome. Great to have you here. Thank you for your earlier contributions. And Tim, as we know, I'll go ahead and run your slides here, but go ahead, Tim. It's all yours.
Thank you so much, Kelvin. And I've been listening to a lot of the conversation. I might have missed bits of it, but the reason I wanted to give this talk, and I'm very grateful, Kelvin, for you to give me a few minutes to do it, is that and actually this just came up. I noticed this came up in the questions just now. But, you know, I've been involved in a few of these meetings. You know, actually, we had the first one back in 2008 at ECMWF. We called it the World Climate Modeling Summit, which Jay Shukla and I organized, trying to make the case for high resolution. But the issue which comes up, and it's just come up, and it'll come up, you know, it always comes up, is people say, well, you know, it's a good thing that CMIP has all these models. I think in CMIP 6 we have over 100 models now. It's a good thing because it means we have model diversity, and you know, and that's important if we're to have reliable predictions with credible estimates of error or uncertainty, credible error bars. And putting all your eggs, you know, in 1 kilometer scale modeling basket is a dangerous thing. And, you know, that's a kind of a powerful argument, but I think ultimately it's an incorrect argument. So I want to give a talk. It'll be a little bit maybe polemic about my own feeling about this, because this is an important topic, model uncertainty. And for sure, going to kilometer scale is not going to get rid of model uncertainty. That's for sure. It's hopefully going to improve the accuracy of our models, but we still need to be able to estimate model uncertainty. So I want to kind of just take this just for a few minutes at a somewhat theoretical level, because this is important. So could I have the next slide, Kelvin? Yeah. You know, we're solving partial differential equations that we believe correctly represent the laws of physics, such as Navier-Stokes. And these equations have certain properties. And a particularly important property of Navier-Stokes is something called scaling symmetry. And you can find it discussed in mathematical books on Navier-Stokes, such as Maida and Bertozzi. But it's basically a symmetry that means if you look at like a turbulent fluid like I've got up there, and you kind of zoom in, you see much the same sort of structures in the zoomed in scale. So now, in some sense, you can't really tell what scale you're looking at when you look at a turbulent fluid. And that, of course, underpins mathematically the plentiful observations of power law structure in turbulence in general and in the atmosphere in particular. So there's the left bottom is the famous Nystrom gauge power law structure. So, you know, these are properties of the partial differential equations. So if I could have the next slide, please. The problem comes because we can't solve these equations, you know, with a pencil and paper. We have to put them on computers, big computers. The problem comes that to actually solve them on the computer, then we have to introduce truncation scales and, you know, parameterize the stuff that is not resolved. Now, it's the imposition of this truncation scale that, in a sense, is the origin of model error and model uncertainty. Because once you do that, you violated this scaling symmetry, at least on this, you know, around the scale of the truncation scale. Can I have the next slide, please? I wrote about this in an article in Physics Today just a couple of months ago. But essentially, you know, these violations of the scaling symmetry at the truncation scale will propagate upscale. And, you know, if they're random errors, it'll give you random errors on the large scale. But if you do something systematically wrong near the truncation scale, it'll lead to systematic errors on the large scale. And in a sense, that is the real problem, that we have these systematic errors. And they're ultimately due to the fact that we have to impose this truncation scale on our computational equations to solve them. Could I have the next slide, please? So, you know, the world that we would like to think exists, and it's the world in which parameterizations are based, is that we have this kind of ensemble of subgrid processes which are somehow small, or there are many of them within a grid box. And so we're kind of drawn by the ideas in statistical mechanics, where we derive, you know, molecular diffusion and molecular viscosity from an Avogadro's number of molecules in a macroscopic domain. That similar type of concept is used to derive parameterizations in our weather and climate models. But the problem is, this isn't how the world looks. If I have the next slide, the world looks like this. This is a consequence, if you like, of the scaling symmetries of Navier-Stokes. It's a consequence of the power law structure. We have these spectra of different scales, and in particular, the actual tendency of subgrid, of unresolved processes in a grid box, can be dominated by just one or two very large eddies, rather than by an ensemble. And in a sense, what this is saying is that I mean, in a sense, this is unparameterizable in the conventional sense of the word. You can't say there exists some formula that will give you the subgrid tendency when you have this kind of power law structure. Now, if I could have the next slide, this is actually, in my view, an important point. It's not it's not just a theoretical point, because we often think of you know, somehow there is a correct parameterization if only we knew it. You know, we don't have enough data, or, you know, the world is complicated. But somehow there is a parameterization, and even worse, you know, we don't know the value of individual parameters in the parameterization, but you know, there is a value. In other words, I mean, a philosopher would say that in this viewpoint, which I think is very commonplace in modeling studies, the uncertainty that exists in models is epistemic. It's due to our lack of knowledge of, you know, the true state of the world. But if what I'm saying is right about this violation of scaling symmetry, it's not an epistemic uncertainty. It's, you know, the other word they use is ontological or aleatoric. It's really the concept of parameterizations and the values of the parameters are actually ill-posed. And associated with that, the model uncertainty is really not specific to individual parameterizations. It's not because, you know, convection parameterization is not something we can parameterize. It's kind of, it's holistically spread across the range of processes. If you think about a convective storm, you know, it combines convection with boundary layer turbulence, with cloud microphysics, with cloud radiation, all the stuff, you know, gets is integrated holistically into that phenomenon we call a convective cloud. So the point I'm trying to make here is that although so-called multi-model ensembles or even perturbed parameter ensembles are very, very commonly used, in a sense, these are all inaccurate and, in some sense, inadequate representations of model uncertainty. In a sense, every single member of an MME or indeed a PPE is predicated on the fact that there is a way of closing the equations with a deterministic formula. And what I'm trying to say is that very concept is probably, well, I would say is incorrect. Could I have the next slide? And I think what this leads to is not so much that the CMIP multi-model ensembles are under-dispersive or over-dispersive, because they're depending on what variable you look at, you can see either. It's just that the spread of the ensemble is not actually giving us a very good estimate of uncertainty. So let me give you two examples. I mean, one is just global mean temperature. The picture on the left is from the IPCC AR5. Now, if you actually look at that little bar on the right-hand side, it gives the actual temperatures, the global mean temperatures in the CMIP model, and there's about a 3-degree spread between the warmest and the coldest. Well, it's certainly not the case that our uncertainty in global mean temperature is 3 degrees. If it weren't for climate change, global mean temperature would be an extremely stable quantity from one year, one decade to the next. So this is a case where the CMIP ensemble is like a kind of a blunderbuss. It's much too underconfident about the actual value. On the other hand, you can take things like, I mean, one of the things which concerns me a lot is long-lived weather regimes, anomalous weather regimes, where the models seem to do a poor job at simulating long-lived. By long-lived, I mean, you know, maybe weeks in duration, not days in duration. And this paper by Reinhard Schiemann shows that both CMIP5 and CMIP6 do a kind of pretty poor job in simulating the frequency of occurrence of long-lived blocks over the North Atlantic sector. So we end up, you know, with a cluster of points which are seemingly showing high confidence, but they're all off target, and so they're actually not high confidence at all. Could I have the next slide, please? Some people might, and I'm sure they do, think in their minds, you know, that I'm kind of sniping about CMIP from the sidelines. What do I know about the challenges of developing CMIP models? Well, let me tell you about something which I did work on, and so I feel I can criticize it without any You know, I'm only being rude to myself in some sense. Back in the 1980s, with two colleagues at the Met Office, Glenn Schutz and Richard Swinbank, we developed one of the first orographic gravity wave drag parameterizations. And these are used in some form or another in most weather and climate models, or at least some form of subgrid orography is now used in all NWP and climate models. Now, these parameterizations are unbelievably crude and simplistic because they're based on quasi-linear two-dimensional flow configurations that rarely happen in reality. They're kind of theoretical idealizations. And I would go as far as to say they're so bad that they should never be used in weather and climate models at all, except that the alternative of not having any representation of orographic gravity wave drag is worse still. So, you know, I know, because I've worked on the subject, that these GWD parameterizations are pretty damn crude, and much better would be to resolve the orographic gravity waves altogether than to parameterize them. And since we're talking about waves with wavelengths of 10 kilometers or so, it starts to become possible in a kilometer scale model. Could I have the next slide, please? So what is the alternative to multi-model ensembles and parameter ensembles? Well, again, with colleagues, particularly Roberto Buizzo and Martin Miller at ECMWF, we developed a so-called stochastic parameterization scheme, which very much is actually a holistic approach to representing model uncertainty, because the stochasticity is kind of multiplicative on the parameterized tendency. So the stochasticity tends to be larger in regions where the total parameterized tendencies are larger, and that's likely to be where these scaling violations are larger. And where this stochastic approach to model uncertainty has been tested, such as in seasonal forecasting by a colleague of mine, Antje Weisheimer, and medium range by another colleague, Linus Magnusson, then the stochastic approach actually does outperform the multi-model ensemble. And I notice, of course, in all these AI systems these days, the representations of model uncertainty are indeed done with stochastic types of terms. Could I have the next slide, please? And one of the big advantages of stochastic parameterizations over multi-model ensembles is that they can help reduce systematic errors. And I could give a whole talk about this, but I'll just show one example from my colleague, Hannah Christensen, when she was at NCAR on one of their fellowships. She looked at one of the NCAR coupled models, where the El Nino ENSO had a spurious, had spurious power at about the 3 to 4 years frequency compared to observations. And with stochastic parameterization in the atmosphere, that power, spectral peak pretty much vanished. And that's highly non-trivial because the temporal autocorrelation of the noise was only in days, whereas this is a reduction in power on the timescales of years. So this is a case where the high frequency was propagating upscale to reduce the power on multi-annual timescales. Multi-model ensembles can't reduce uncertainty that way. Yeah, so have that next slide, please. This is actually an important point, because ensemble forecasting, was developed because it can provide more reliable forecast information for decision making than deterministic forecasts can. But the whole thing is predicated on the fact that the probabilities from such ensembles must be reliable, and if they're not reliable, then the users could literally, the information could literally be worse than useless for decision making. People could make completely the wrong decisions. And we have shown with the multi-model ensembles for seasonal forecasting that can happen. The reason I just want to say again, the reason I'm saying this is because the argument that we need multi-model ensembles like CMIP with their hundreds of members to have model diversity, in my view, is a bogus argument. And I just stress again, because all the members of the ensemble themselves assume that the subgrid processes can be parameterized with a formula. The stochastic approach does not make that assumption. So this argument that sometimes is used to kind of close down the idea of some internationally coordinated work to develop a kilometer scale modeling system because we need multiple model ensembles, I think is a wrong argument. I'll just, I got 2 more slides and then I'll finish. Yeah, Kelvin, you mentioned in your talk this morning about this idea of a CERN for climate change, which I wrote about in 2011. Just this year, Physics World asked me to kind of revisit where are we with that idea. And I had to say, unfortunately, we haven't moved on a great deal, but nature has moved on. The floods, the droughts, the heat waves, the hurricanes, the extreme weather that we've seen in the last few years is now routinely out of sample of the CMIP type ensemble members. And I just find this a profoundly unsatisfactory state to be in. I think this is an ideal topic for international collaboration. We don't want, if we use Andreas's projection for CMIP, where we get to K-scale by 2055 or 2060, I just think that's completely unacceptable. We need this to be a reality in the next 5 to 10 years. And we've kind of said all these things, but we need to quantify regional climate change, and we can't at the moment with any great confidence. There's a lot of talk about tipping points. We can't use CMIP models to tell us about tipping points because they don't do them. And there's a great resurgence now about the possibility of Plan B geoengineering. But again, are we really going to seriously start spraying the stratosphere with aerosols if we don't know whether the monsoons are going to switch off or not? Well, how are we going to know if the monsoons are going to switch off or not if our models can't simulate the monsoons without these big biases? So this is not of academic interest. It's crucial and urgent to help society deal with climate change. If I could have the last slide. So yeah, so the question was asked, and it is a big question, and I hope it's discussed in your breakout groups. But one thing's for sure, going to K-scale is not going to remove the need for ensembles. It will still need to represent the unresolved processes. But do we need these large multi-model ensembles where individual groups do not have sufficient resources, and we end up with 100 what I would call inadequate models? Or do we go to K-scale and perhaps put a bit more effort into thinking about how we would stochastically parameterize model uncertainty in when I say single model, I mean, maybe a few models, but certainly not 100 models. Personally, given the successes of stochastic parameterization in medium range and seasonal timescales, and ECMWF uses them, Met Office uses them. I think there are other groups now, certainly in NWP, most NWP centers use some kind of stochastic parameterization these days. So we must not assume that continuing to support and develop multiple, by multiple, I mean like 50 or something, high-res models is either necessary or indeed desirable, given the finite resources we have in the world as we go to K-scale. So that's my input to some of the discussion that I'm sure you'll be having tomorrow about this topic. And it's an important one, I believe. Thank you so much for giving me the time to say this. I appreciate it very much. Thank you.
Great. Thank you, Tim. Appreciate that. Very, very interesting, very important. We got time for a couple of questions for Tim. If anyone has them, feel free to come up to the microphones. Anyone have questions? Okay. Well, let me just say, and Tim, again, thank you so much, and sleep well. Appreciate you staying up late.
I'll see you tomorrow.
Thank you. You'll be in the breakouts tomorrow if you have the opportunity.
Actually,
yep. Go ahead.
Is there still an opportunity for a question? Is Tim still online?
Yes. I'm sorry. Please. Yeah, Peter. Yeah.
Just a quick question about the analogy to CERN and the discussion about whether we need one model or multiple, right? When you look at CERN, it's one big facility that has, generates the particle beams. And then you have 4 experiments that sit on the same beamline. So essentially you have one part that is shared amongst everybody, and then you have pieces that are completely independent. So would the vision here be something similar? I mean, are we just, for a climate supercomputer, are we just talking about silicon that's shared amongst all the individual groups, and then everybody comes with a different model? Or are we talking about maybe some software infrastructure that's shared and sitting on top of this common silicon, and then it's whatever, the parameterizations or some other sub-models that are independent for each one of the groups? What's the thinking?
I personally hope it's not the former idea where we just have a big computer and everybody bids into it. I would like to see our community being a bit more organized and what's the word I want to use? Integrated somehow, so that we do try to refine down to a minimal set of models. And I just come back to my point in my talk that I think we can deal with model uncertainty in other ways through stochasticity rather than these humongously big multi-model ensembles. But the main point about CERN is that I mean, although there are different experiments, to be honest, everyone is working in a certain, they have a goal that used to be finding the Higgs boson or finding evidence for supersymmetry. And I think here the goal would be, developing K-scale global climate models.
Do you have a quick comment? Go ahead.
Yes, I do. First, I dispute the idea that there's actually 100 separate models in the CMIP ensemble. What you have is a lot of different flavors of certain very specific model codes in a lot of cases. I mean, my own institution submitted, I believe, 3 or 4 models that were very similar to CMIP 6. The other question is maybe an analogy to another effort. Back 25 years ago, we had a very healthy regional modeling effort here in the United States where there were a lot of different models and a lot of different innovation going on. And over time, there's a decision made that all the funding needs to go to one particular modeling effort in regional modeling. And since then, a lot of the innovation in regional modeling has slowed to a crawl to the point where one government agency in the United States is actually using the UKMO instead of an American-made model. So maybe that's a bit of a point in response to what we have here. I mean, certainly the CMIP models aren't adequate for a lot of things. I don't work on CMIP myself, in part because of those inadequacies. But I don't see a lot of value in simply just eliminating a lot of these models and coming back to the same idea of the size multi-model ensemble. If you say you have 100 models, you want to focus on 3. What are the people developing the other 97 models going to be doing?
On the first point, I mean, you're right. I mean, there are multiple versions. I think there may be about 50 genuinely, well, even depends what you mean by genuinely different, but there's many tens of different CMIP models. And now I'm definitely not saying people should not work on different ideas. Different maybe numerical schemes, different parameterizations, all that sort of stuff is to be encouraged. But 2 points. I mean, A, it can be done within a certain modeling framework, and B, I just don't think we need at the operational level when we actually come to do the integrations that will be creating the data for the various users, that we need all these independent models. I just don't think it's a useful use. It's an inefficient use of people's time. I mean, well, that's very strongly my view about that. Now, as far as I don't know what's happened with limited area model, the problem with limited area modeling is that, you know, you're still importing all of the biases from the course global models, and so you're not really eliminating those problems in the regional models. So maybe that's, you know, another reason why some of the regional modeling hasn't advanced as rapidly as one might have liked.
Yeah, good points. I'll take you back to what I said this morning, and we'll put the proposition that I stated up there tomorrow. But this is about balancing specialization of a system versus, you know, everybody can come and run their models. If we do the latter, we're right where we're at today. We just have to be honest. That just isn't going to be possible. When you look at the major telescopes that have been put out there, that didn't stop all the other telescopes all around the world that were quite expensive, right? So, like Tim said, we're not about, you know, killing off all these other modeling efforts. But if we're really going to address the challenges that we're talking about, as I said earlier, these are very expensive, very long-term propositions that one organization just simply can't do and do it like, I would say, ECMWF. They have basically a single modeling framework where they get a lot of diversity because it's a framework, it's not a model. And that's, if you go back and look at the value proposition I stated, that's exactly what we're talking about. So we're talking about finding that sweet spot between specialization of a system, which really doesn't mean customized only for a given model framework. It means specialized in the sense that if you want to run your model there, you can't just take your favorite Fortran code and boy, put it on there and it's going to sing. That just isn't possible. We've been doing that for years and years, and it isn't getting us where we need to go. And so this is the challenge that we're talking about here, is to figure out what that sweet spot is. If we can have a framework, a global framework that is this supermodel, and I'm talking about, you know, atmospheric science now, not people, but a supermodel that allows you to do a lot of these things that really empower the global community, just like ITER does, just like CERN does, but it doesn't completely displace all the other efforts that are out there that are wonderfully important for education and those sorts of things. But to solve these really big challenges, it's very difficult to imagine how 50 different groups around the world that participate in CMIP, by all of that separate activity, is going to get us to where we need to go. That's a question, okay? That's what we're here to talk about. And really, hopefully by Wednesday, resolve to say, as a global community, what is the approach we're going to take? It's not eliminating global ensembles at course resolution. It's not eliminating downscaling. It's not eliminating anything. It's adding to the portfolio. And if we all feel that's important, the question is, how do we do it and get there in a time scale of 5 years or so, which will allow us to address a lot of these really compelling challenges. To me, that's where the rubber kind of meets the road. So we'll put the proposition up there, and I encourage you to look at it tonight as well. When I kind of step back from today, one thing I really thought was fantastic was it wasn't, although it was sort of said and then quickly corrected, it's not AI versus physics-based models. It's working together. And I heard folks from Google, Stefan and others talking about the symbiotic relationship, but the fact that, you know, we really need to work together. I think that's extraordinary, because really, I wasn't quite sure coming into this how that was going to go. But I think this friendly collaboration, we all know, is what's needed to get us there. So I heard maybe 5 major things that really reflect the 5 questions I put up there this morning. One was this roadmap to kilometer scale, collaborating more between the traditional climate community, the traditional weather community. This collaboration needs to be done more effectively now. It needs to be organized and so on. And certainly the development of physics is critical, right? I mean, as it's been said multiple times, you can't just take the models to finer scales. There's a lot of physics research, a lot of development, but borrowing a lot from what we've learned in the NWP community can really save a lot of time. And so George Bryan is here. If you don't know George or his work, this guy has done, I think, some of the most important work on very fine resolutions down to like 50 meters, well within the inertial subrange, and asking the question, what resolution do we need? To Tim's point, it's maybe not the right question, because we will always need higher resolution. And I think John Shelf said it well, and others here, that it's getting to that point where we can sort of make that leap into, we're not resolving convection or clouds explicitly, but we are resolving the most energetic elements much better than we are now with non-hydrostatic physics. That is critically important, and you can read a lot about that in the literature. People at NCAR have published on that. So the second thing I would say was this issue of stakeholder engagement, applying information in ways that is useful, translating that, and so on. And somebody mentioned the National Climate Information Service, or international one, frankly, to think about that. Third point was administration and governance of how we bring the international community together. And I think Bjorn reinforced this, and Francina, or no, it was actually Maria put this up there to say, hey, let's spend our time not in the weeds of, is it this flavor of AI or whatever, but how do we as a global community come together? That I think is, I've always said it to all the people I've talked about, that's the most difficult challenge. It really is. Money, could we get $2 billion if that's what was needed? I really think we could. I don't think that's the issue. And it's not going to come from the federal government. That's not probably the best approach, right? It's coming from other sources. But how we organize as a global community and do the kinds of things we're talking about, to me, that's the biggest challenge. The fourth one is kind of software, hardware architecture, energy efficiency, and so on. Nothing I've heard today says this is just impossible. It's ridiculous. You guys shouldn't even be here. We heard about Green Flash 13 years ago, a tremendous amount of work done there. And talk to John, talk to other people that were there, like, well, we're not too far beyond where we were back then. But a lot has changed. A lot has changed technologically, scientifically, and politically, I think. So this, I think, is within our reach. And then finally, I would say that's 1, 2, 3, 4. Oh, collaboration within the AI and machine learning community. The need for physics-based models came through loud and clear. It's not that the AI community is saying, guys, we don't need you at all. It's how do we work together to maximize the value of AI and machine learning? And, I'm a physics-based modeling guy. I don't know a whole lot about AI, but I've been talking to a lot of folks who are way smarter than I am. And what I love is that they're saying, this is what AI can do. Here's what it can't do. But to Maria's point, it's moving so fast. It's hard to say, okay, this is the approach we ought to take. But we're in a renaissance time here, and the global community, this sounds a little hyperbolic, they're depending on us. They don't know we're here. Most people don't know. But, I think we could look back on this period 10 years from now and say, that meeting is where things really started to turn. And it's not because of what we've done. It's because of Eve and Destiny and all these incredible efforts globally that are happening. NICAM in Japan. We stand on the shoulders of giants, but we're about something slightly different here. We're about the computational and administrative coordination international framework to make this happen. And folks, I really think we can do this. So I encourage you tonight, we're putting the slides. Deanne has put the slides. They're in 2 parts because it's a 500 megabyte file. And then, of course, Bjorn was 250 megabytes. We haven't even put his up there yet. We'll get to that. But also the notes from today, all the other stuff that you submitted since we had that session with Dan and Barb. Was it Dan and Barb? Dan and whoever it was, Dan and somebody. John, well, whoever it was, I don't know. Maria. Okay. Yeah, it was Maria, the ever-present Maria. So we had this. She's now taken all the additional stuff and resynthesized it in ChatGPT. Deanne, I will give that to you and we'll put that up tonight. And Jim Hurl really wanted us to have the slides so you could kind of think about that for the breakout topics tomorrow. So as you have dinner tonight and after your third glass of wine, really think about the breakout questions for tomorrow. And you guys, I can't thank you enough. I love the provocative discussion. I love the challenging that's going back and forth. We're a wonderful community here, and I am just so blessed to have you spend part of your time here. And let's go figure out how to do this. So many people are depending on us to get this right and to figure out how to move forward. And it's up to us. I really believe that, plus all the other folks that aren't here today. So I hope you have a wonderful dinner. We do have a list of area restaurants on the Summit website. It takes you to a link because we can't put them on there lest we'd be looking like, as a public university, we're promoting private industry, which we can't do. So anyway, there's great places there. Some of us who are locals, be happy to tell you what places we like. And anything else, Deanne? Yeah, the slides are under the resources tab. And so we will reconvene at 8:30 tomorrow, 7:30 to 8:30 breakfast, which will be here earlier than it was today. And we'll do a quick recap and we'll dive right in. Tomorrow is all about spending time in discussion like we had today, but the breakout groups and the so-called challenge sets, which I will preview for you tomorrow in terms of what they are. But you have the handout. I encourage you tonight, look at the challenge sets if you would, and be thinking about the breakout topics. So have a great evening and enjoy your time in Shampoo Banana, as we call it. Go out and grab an ear of corn from the fields. Don't let anybody see you do that. But anyway, have a great evening. We'll see you here tomorrow. So thank you all very much.